We have always been explorers, looking to the horizon to find our place in the infinite. Today, our eyes in the sky, the most advanced telescopes and probes ever built, reach for the very edge of reality, capturing light from the dawn of time. But as we unravel the mysteries of an expanding universe and the dark forces pushing galaxies apart, a haunting question remains: is our journey unique? While we gaze at the stars, the Earth beneath us may be guarding its own silent secrets, traces of advanced civilizations that might have risen and fallen millions of years before the first human ever walked. From the farthest reaches of NASA's reach to the deep, forgotten history of our own planet, let's explore the ultimate mysteries of existence. What is the universe truly expanding into, and what if we weren't the first to call this world home? Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. In 1958, NASA turned its eyes to a new frontier. For most of human history, the edge of space was an invisible boundary. But for NASA, it wasn't just a poetic horizon. It was a real frontier, one that hides strange and powerful forces shaping our planet, our technology, and even our survival. At this razor-thin line between air and vacuum, satellites teeter, auroras dance like ghosts, and mysterious bursts of energy flash in silence. When NASA set out to study this region, the so-called edge of space, they expected thin air and starlight. What they found instead was a dynamic electric realm full of surprises, a place where Earth and space are in constant conversation. So what did NASA discover at the edge of the universe? The story of the James Webb Space Telescope began back in the 1990s. At first, the plan was simple: build it for about $1 billion and launch it into space by the year 2007. But that dream quickly turned into a long, twisting journey. Delays piled up, costs ballooned, and technical challenges kept sending the project back to the drawing board. Engineers and scientists faced problem after problem, some mechanical, some financial, and some simply the nature of doing something no one had ever done before. After years of waiting, redesigning, and testing, the moment finally came in December of the year 2021. The James Webb Space Telescope, or JWST, rode into the heavens aboard a rocket, marking the beginning of a new era in astronomy. Yet even then, its work did not begin right away. Over the following months, it slowly unfolded itself in space, stretching its massive sunshield, powering up its systems and testing every delicate piece of hardware before daring to open its golden eyes to the universe. This giant of science weighs around 6,500 kilograms, about the weight of a large school bus. Its sunshield, a shimmering silver masterpiece, is roughly 14 meters by 21 meters, about the size of a tennis court. The main mirror, the heart of the telescope, is 6 times larger in area than the one on the famous Hubble Space Telescope. This means it can catch far more light, more photons, from the faintest, most distant corners of space, allowing it to produce images so sharp they feel almost unreal. James Webb carries an arsenal of cameras and scientific instruments designed to see in the infrared spectrum. This ability is not just a technological marvel, it is absolutely necessary. Because of the expansion of the universe, the light from the most distant galaxies has been stretched, or redshifted, until it is now all in the infrared range, no matter what it was when it first left those galaxies billions of years ago. That means an ordinary visible light telescope would see nothing but darkness where these galaxies glow. Infrared vision also allows James Webb to peer through thick clouds of cosmic dust that would block Hubble's view entirely. This makes the telescope not just a replacement for Hubble, but a partner. While Hubble mostly sees invisible light and some ultraviolet, James Webb focuses almost entirely on infrared and cannot detect certain colours of visible light at all. Instead of competing, the two telescopes complement each other, two sets of cosmic eyes working together to give us a deeper, richer view of the universe than either could alone. But enough about the hardware. Let's see what James Webb can really do. We will begin our journey in our own galaxy, then move outward, step by step, until we reach the far edge of the knowable universe. The sights along the way are nothing short of spectacular. Our first stop is a breathtaking region called the Cosmic Cliffs, part of a stellar nursery officially known as NGC 3324 in the Carina Nebula, about 7,600 light-years from Earth. What you see here are towering walls of gas and dust, each peak rising nearly 7 light-years high, vast enough to dwarf anything in our solar system. And this is only a small slice of the nebula. The entire structure is much larger, with a hollow centre where powerful stellar winds from young stars have swept away the surrounding dust, leaving behind a bubble-like cavity. Astronomers are drawn to this place because it holds clues to one of the greatest mysteries in astronomy: how stars are born. The intense winds push dust and gas into dense knots where gravity can take over, pulling the material together until nuclear fusion ignites and a new star begins to shine. But the process is shrouded in mystery, literally, because the same dust that helps form the stars also hides them from view. It's like trying to watch a bird hatch inside a closed egg. This is where James Webb's magic comes in. Using its mid-infrared instrument known as MIRI, the telescope can pierce through the dust, revealing details invisible to Hubble. The difference is astonishing. Where Hubble sees hazy outlines, Webb shows crisp detail, revealing the hidden structures and baby stars nestled inside. This new clarity will give scientists years' worth of data to study, helping them piece together the puzzle of star formation. If the cosmic cliffs show us the birth of stars, our next stop reveals the end of their lives. Closer to home, we turn our gaze to NGC 3132, better known as the Southern Ring Nebula. On the left, we see the nebula as captured by Webb's near-infrared camera. On the right, we see it through MIRI. At first glance, the term planetary nebula might make you think planets form here, but that is a misnomer. The name comes from early astronomers who thought these round clouds looked like planets through their telescopes. In truth, a planetary nebula forms when a dying star expels its outer layers into space, creating a glowing shell of dust and gas. Knowing what this ejected material is made of is essential for understanding the cosmic recycling process. The elements and compounds floating in these nebulae will one day become part of new stars, planets, and perhaps even life. Webb's ability to peel back the dust allows us to see the star systems inside with unprecedented clarity. We now know that the second star in this system has not yet expelled its own outer layers, meaning another nebula will eventually form here in the future. Webb also shows how the gravitational pull of the two stars stirs the nebula's dust into delicate, swirling patterns. From here, we will venture even farther, beyond our galaxy, to witness other stellar nurseries and cosmic wonders. But for now, you have seen how the James Webb Space Telescope reveals both the first breaths and the final size of stars, painting a story of the universe that was invisible to us before. Around 161,000 light-years away from our planet lies a celestial wonder called the Tarantula Nebula. Astronomers named it so because its sprawling clouds of gas and dust resemble the legs of a giant tarantula sprawled across an invisible silken web spun in the depths of space. While its beauty is enough to make any stargazer pause, scientists prize this nebula for another reason. It mirrors a chapter in the universe's distant past known as the Cosmic Noon. This era, which researchers believe occurred about 1 billion years after the universe first came into existence, was the most prolific period of star formation in cosmic history. Back then, stars were being born at an astonishing rate, and the Tarantula Nebula offers a living laboratory that may look much like that ancient, long-vanished time. Thanks to the James Webb Space Telescope, astronomers have been able to witness stars here in their infancy, mere cosmic newborns, making it an extraordinary place to study the earlier stages of stellar life. If we push our gaze further out into the universe, individual stars fade from sight, and we begin to see grander patterns, whole galaxies moving in a cosmic ballet. One such spectacle is Stefan's Quintet, a group of 5 galaxies. In truth, one of them only appears to be close to the others from our perspective on Earth, but 4 of them are genuine neighbours in space. This grouping became famous after appearing in the classic film It's a Wonderful Life. Astronomers think those 4 true companions are destined to collide in the far future, In fact, two of them are already in the process of merging, their immense gravitational pull flinging out waves of scorching hot dust as they twist and whirl around each other. The forces at play here are almost beyond human comprehension, and the energy released is staggering, a dance so vast that only the universe itself could provide the stage. The image of Stefan's Quintet that we see today is not a single snapshot. It is a painstaking mosaic, stitched together from nearly 1,000 separate images taken by James Webb. This method gives the final result breathtaking clarity, allowing astronomers to pick out fine details that would otherwise be lost. Now, let us venture even farther. We reach a point where even the mighty James Webb begins to strain at the limits of what it can see. One of its most famous achievements is an image called Webb's First Deep Field. The region captured here is so tiny that, if you held a single grain of sand at arm's length against the night sky, that grain would completely cover it. At this incredible scale, almost nothing you see is a star. Most are entire galaxies, each one holding billions of stars within it. Some of the shapes appear stretched or warped due to gravitational lensing, where massive objects closer to us bend and distort the light from more distant galaxies lying far beyond them. In this image lies one of the oldest galaxies humanity has ever spotted. It is so unimaginably far away that the light it emitted when it first formed, just after the dawn of the universe, has only now arrived at Earth. By studying the faint reddish glow of this tiny speck, scientists can measure how much the light has been shifted by the expansion of space. This redshift tells them its distance, about 13.1 billion light-years away. Considering the universe itself is believed to be around 13.7 billion years old, this little galaxy is one of the earliest we will ever hope to see. You might be surprised, even disappointed at how small and faint it looks, but there's a reason for hope. When we compare this image to one taken by the Hubble Space Telescope of the same spot in the sky, Webb's advantage becomes clear. Hubble needed to stare at this region for 10 days straight to collect enough light for its version of the image. James Webb captured its own version in only half a day, a mere 1/20th of the time. Imagine what it could reveal if given the same amount of observing time as Hubble. That tiny red dot may only be the beginning. These images are not just scientific goldmines, they're also works of art painted by the cosmos itself. They left me in awe, but patience will be key. The James Webb Space Telescope has only just completed its delicate calibrations, allowing its instruments to cool to the perfect temperatures and ensuring every system works flawlessly. Over the next 5 to 10 years of its expected mission life, competition for its time will be fierce. Every second is precious, and scientists around the world are lining up to use it. Webb will be hunting for signs of life-friendly atmospheres on distant exoplanets, peeling back the veils of nebulae to watch stars being born, and comparing the sprawling ancient galaxies of today with the youthful, chaotic galaxies that filled the universe shortly after the Big Bang. With a tool as powerful as James Webb, we cannot yet imagine all the wonders it will reveal. The universe still holds its secrets, but for the first time we may finally be close enough to listen. Far away in the constellation of Scorpius lies one of the most breathtaking and mysterious objects in our sky, NGC 6302. Astronomers also call it the Bug Nebula, the Butterfly Nebula, or Caldwell 69, because its sprawling wing-like shape resembles either a delicate butterfly in flight or a strange cosmic insect. This nebula is what scientists call a bipolar planetary nebula, meaning it has two giant lobes of material streaming away from its centre, giving it an hourglass-like shape. The structure inside this nebula is among the most intricate ever seen in any planetary nebula, filled with glowing walls of gas, dense knots of material, and razor-sharp edges that look almost sculpted. At the heart of the Butterfly Nebula lies its central star, one of the hottest stars ever discovered, with a surface temperature of more than 250,000 degrees Celsius. This searing heat means the star it came from must have once been truly enormous. But today, this central star is a shrunken white dwarf, the burned-out core left after the outer layers were thrown off into space. Astronomers identified this hidden star in the year 2009 using the newly upgraded Wide Field Camera 3 aboard the Hubble Space Telescope. It has a present mass of about 0.64 times the mass of our Sun and is wrapped in a dense dark ring of gas and dust. This thick ring has acted like a cosmic funnel, forcing the star's outflows into its striking bipolar, hourglass-like shape. NGC 6302 has been known to science for well over a century. It appears in the New General Catalogue, which means astronomers were aware of it by at least the year 1888. The earliest detailed study came in 1907, when astronomer Edward Emerson Barnard sketched and described its beauty. After the final servicing mission to the Hubble Space Telescope in September of 2009, the Butterfly Nebula appeared in some of the first spectacular images released, dazzling both scientists and the public. Its structure is more complex than it first appears. It has two main lobes, but there is evidence of an older second set of lobes, the ghostly remains of a previous eruption when the star was losing mass. Cutting across the middle of the nebula is a thick, dark lane that completely hides the central star from view at all wavelengths of light. One of the most dramatic features is its prominent northwestern lobe, which stretches about 3 arc-minutes away from the central star. Astronomers believe this lobe was created by a violent eruption roughly 1,900 years ago. Its walls are expanding outward in a curious way. Each part moves faster the farther it is from the star. At a distance of 1.71 arc-minutes from the centre, gas in the lobe races away at 263 km per second. At the very edge, this speed soars past 600 km per second. The western edge of this lobe seems to have slammed into older clumps of gas, distorting its shape. The central star remained unseen for decades because of 3 obstacles. Its extreme heat means it shines mainly in ultraviolet light. The surrounding dust absorbs much of that light, and the nebula itself glows brightly, masking the faint star. Only when Hubble's new camera offered greater sensitivity and sharper vision did astronomers finally spot it. Its temperature is measured at about 200,000 Kelvin, and its mass is again confirmed at 0.64 solar masses. The original star was much heavier, but most of its mass was hurled into space when the nebula formed. It has now stopped nuclear fusion and is fading at a predicted rate of about 1% each year, slowly settling into its final life as a white dwarf. The dark lane in the middle has proven to be chemically fascinating. It contains unusual crystalline silicates, grains of crystalline water ice, and even quartz. Some features have been interpreted as the first detection of carbonates beyond our solar system, though this is controversial, since carbonates are usually formed in water-rich environments, which this nebula lacks. The debate remains unresolved. One of the most puzzling traits of the dust in NGC 6302 is that it contains both oxygen-rich silicate molecules and carbon-rich compounds called polycyclic aromatic hydrocarbons, or PAHs. Usually, a dying star is either oxygen-rich or carbon-rich, switching from one to the other late in life due to changes deep inside. This nebula belongs to a rare group where carbon-based molecules seem to have formed in an environment still rich in oxygen, a mystery that continues to intrigue astronomers. In the constellation of Ophiuchus, about 2,100 light-years from Earth, lies one of the most breathtaking cosmic sights ever captured, the object known as M29. Astronomers often call it the Butterfly Nebula, because its 2 elegant wings stretch into space like the delicate patterns of a butterfly in flight. But there is another, even more fitting nickname, the Twin Jet Nebula, which hints at its dramatic and powerful nature. When you look closely, M29 doesn't just resemble a butterfly. Its shape looks remarkably like 2 giant exhaust streams blasting away from an invisible engine. These jets are not just for show. The gas inside them is racing through space at speeds greater than 200 miles every single second. That's far faster than any earthly aircraft, and it's why astronomers say the comparison to a supersonic jet engine is spot on. From years of careful observations, scientists have learned that the nebula is growing larger over time. This means the violent outburst that created its twin lobes must have happened relatively recently, only about 1,200 years ago, which is the blink of an eye on the cosmic timescale. At the very heart of M29 is not one, but 2 stars locked together in an extremely close and dangerous embrace. They orbit each other so tightly that it is possible one star is partially swallowing the other. The stronger star's gravity tugs at the outer layers of its weaker companion, stealing streams of gas and flinging them outward into a dense flattened disk that wraps around both stars like a cosmic skirt. This strange spinning disk, which stretches to a size about 10 times the width of Pluto's orbit, acts like the nozzle of a gigantic space engine. High-speed stellar winds from one of the stars crash into the disk, and because the disk blocks most of the wind's path, the gas is forced to escape in two opposite directions. The result is a perfectly shaped pair of narrow, high-velocity jets shooting out into space, forming the butterfly's wings. The process is strikingly similar to how a jet engine works here on Earth. Inside the engine, burning gases expand, then slam against the engine walls, and are squeezed through a nozzle, producing powerful, focused streams of hot air. In M29, however, the nozzle is made of gas and dust, and the engine is a pair of dying stars in their final dance. The Hubble Space Telescope's Wide Field and Planetary Camera 2 captured this extraordinary sight on the 2nd of August in the year 1997. In the image, different colours reveal different elements. Neutral oxygen shines in deep red, once ionised nitrogen glows green, and twice ionised oxygen blazes in bright blue. Together they paint a portrait of a celestial engine at work, beautiful, violent, and fleeting. High in the Milky Way, inside a glowing cloud of gas and dust called NGC 6357, lies a bright cluster of young massive stars named Pismis 24. At the heart of this cluster shines its brightest jewel, a stellar system known as Pismis 24-1, also catalogued as HD 319718. This remarkable object is located roughly 6,500 light-years away from Earth. For a time, astronomers believed Pismis 24-1 was a single colossal star, possibly the most massive star ever discovered. Later, with sharper observations, they found that it is not one star at all, but at least 3 separate stars packed closely together. Each of these stars is still among the hottest, most luminous, and most massive known in our galaxy. The story of its discovery stretches back many decades. First, Pismis 24-1 was recorded under its HD catalogue number. Astronomers then realised that it should be separated into 2 different stars, Pismis 24-1 and a dimmer neighbour, Pismis 24-16. The bright nebula NGC 6357, which surrounds them, was already well known, but the tight cluster Pismis 24 itself was not recognised until the year 1959. In 1973, astronomers studied the cluster in detail and found 15 individual stars within it, of which 12 were judged to be true members of the group. The brightest of all was numbered first, Pismis 24-1, and it was initially suspected to be a gigantic supergiant star. Later observations revealed an even more complicated reality. The star was in fact a very close pair, an O3.5 supergiant in a spectroscopic binary system, and an O4 giant star orbiting about 500 astronomical units away. Even more precise imaging showed that Pismis 24-1 can be visually split into 2 main components, called NE, northeast, and SW, southwest, based on their positions. The NE component is slightly brighter and hotter than the SW component, and the NE itself is a spectroscopic binary, meaning 2 stars orbit so close together that they cannot be seen separately, but reveal their presence through the shifting of their spectral lines. This was unexpected, because the way the star's light is classified suggests they should each be brighter than they appear. Astronomers think that the NE pair's interaction might be affecting how its light is interpreted, or perhaps the SW star also hides a close companion of its own. Pismis 24-1 is also an eclipsing binary, with its brightness dipping every 2.4 days as one star passes in front of the other. The eclipses seem to come from the NE component, though scientists have not yet separated the light curves of the 2 main components. The eclipses are symmetrical, which suggests the orbit is nearly circular, and the 2 stars that cause them are almost twins in both mass and temperature. Star catalogues also note that Pismis 24-1 has 2 fainter companions, lying 5.5 and 16.4 arc-seconds away, which is not unusual given that the entire cluster spans only about 1.5 arc-minutes across. The NE pair cannot be individually resolved, but the way their eclipses behave shows that they are nearly identical, each with a temperature of about 42,000 kelvins. Together, They shine with nearly 800,000 times the light of our Sun, meaning each one alone is likely under 400,000 solar luminosities. The combined spectrum shows them as an O35 if type, a rare, massive star with strong nitrogen emission lines. And since no separate spectral signatures can be seen, both stars are thought to share the same type. As a single object, their combined mass would be about 74 times that of the Sun, but individually they are less massive. The system also produces intense X-ray radiation, probably caused by the fierce collision of stellar winds from the two supergiants. The SW component appears to be a single O4 giant star, about 40,000 kelvins hot, with emission lines of ionized nitrogen, silicon, and helium. It blazes with roughly 650,000 times the Sun's luminosity, has a radius about 17 times larger than the Sun's, and a mass around 66 times greater. Even though it is called a giant based on its spectrum, such hot O-type stars can show these features while still in the prime of life, burning hydrogen in their cores because of their intense convection and powerful stellar winds. When astronomers first modelled Pismis 24-1, before they knew it was actually multiple stars, they thought it might weigh over 300 times the Sun's mass, which is more than theory says should be possible for a single star to form naturally. As better telescopes and improved models of stellar atmospheres became available, this estimate dropped. The discovery that it was a binary and then a triple brought its total mass into a range that fits comfortably within what astrophysicists expect from star formation without needing exotic explanations. For a while, astronomers thought that one of the stars here, Pismis 24-1, was the single most massive star ever found, nearly 300 times the mass of the Sun. But sharper observations revealed it was actually at least 3 stars, each still a staggering 100 solar masses. This star cluster is part of a larger structure, the nebula NGC 6357, a cosmic nursery where new stars are born. Inside, dense clouds of dark gas hide young protostars, the earliest phase of a star's life, as they slowly gather material from their parent molecular clouds. Others are wrapped in expanding cocoons of gas, making the whole region feel like a giant living organism in the process of creation. Next, we push much farther, to 60,000 light-years away, where we meet the globular cluster Palomar 12. Unlike most other globular clusters in the Milky Way, its stars are about 30% younger. The reason is that Palomar 12 didn't actually originate in our galaxy. It was born in the Sagittarius dwarf elliptical galaxy, and only joined the Milky Way after a dramatic galactic encounter. Around 1,700,000,000 years ago, the Milky Way's gravity tore Palomar 12 away from its home galaxy. Even now, that galaxy is slowly being pulled apart by our own. When galaxies pass close or collide, gravity can twist them into bizarre shapes and steal their stars, exactly what happened here. But Hubble's reach extends much farther still. 30 million light-years away lies the Sombrero Galaxy, seen here edge on. From this angle, we can clearly see its flat, disc-like shape, something common in spiral galaxies. The reason galaxies often take this form is because they spin, and the conservation of angular momentum causes matter to flatten into a disk over time. At the center of the Sombrero Galaxy shines a blindingly bright core, surrounded by lanes of cosmic dust that swirl outward like the brim of a hat, hence its name. 65 million light-years away, we find something stranger still. The diffuse galaxy NGC 1052, DF2. Its ghostly, see-through appearance comes from the fact that you can see distant galaxies shining right through it. Even more mysterious, it appears to have no dark matter at all, making it the first known galaxy of its kind. Scientists still aren't sure why. Travelling more than 300 million light-years, we arrive at the Coma Cluster, a gravitationally bound collection of over 1,000 galaxies. This cluster is also one of the first places where evidence for dark matter was found. Here, countless globular clusters float between galaxies, not bound to any single one but to the cluster as a whole. Far out in the depths of space, astronomers have found a truly remarkable star. Its official name is MAX J1149 Lensed Star 1, but most people know it by its more poetic nickname, Icarus. This star is a blue supergiant, an enormous and extremely hot type of star, and it was spotted not by ordinary means, but with the help of one of the universe's most fascinating tricks, gravitational lensing. Icarus holds a special place in astronomical history because it is the 7th most distant single star ever detected, following other far-off stars nicknamed Arendelle, Godzilla, Mothra, Quilla, Star 1, and Star 2. It lies about 14 billion light-years from Earth. For scientists, this measurement is linked to something called redshift, in this case z equals 1.49, which helps determine how far back in time we're looking. In terms of the universe's timeline, the light we see from Icarus began its journey roughly 9,340,000,000 years ago, when the cosmos itself was only about 4,400,000,000 years old, not long after the Big Bang in cosmic terms. Astronomer Patrick Kelly, one of the co-discoverers, explained just how extraordinary this find was. Icarus is at least 100 times farther than the most distant non-exploding star ever seen before it, a star named SDSSJ 1229 + 1122. It was also the first individual star to be spotted at such a distance, thanks to the powerful magnifying effect of gravitational lensing. The discovery took place in April and May of the year 2018 while scientists were studying a supernova called SN Refstal using the Hubble Space Telescope. Patrick Kelly from the University of Minnesota led the research team, and their groundbreaking findings were published in the journal Nature Astronomy. Although astronomers had been gathering images of SN Refstal since 2004, it was only when they looked back through the data that they noticed something unusual. In pictures from 2013, a faint point of light appeared, and by 2016, it had grown dramatically brighter. This tiny point was not a galaxy, nor a quasar, nor a supernova. It was a lone star, magnified by more than 2,000 times by the bending of the light through gravity. This magnification came in 2 stages. First, the entire galaxy cluster Max J, 114, 9.5 + 2, 2, 2, 3, located around 5 billion light-years from us, boosted the star's brightness by a factor of about 600. Then something even smaller and denser, possibly a star or a black hole about 3 times the mass of our Sun, drifted in front of the star's light path, producing an extra boost through a process known as gravitational microlensing. This second event, which peaked in May of 2016, made Icarus appear roughly 4 times brighter still. Interestingly, there was also a second brightness peak, which could mean Icarus is actually part of a binary star system. Normally, only vast cosmic objects like entire galaxies, blazing quasars, or the spectacular explosions of supernovae can be detected from such an incredible distance. But here, thanks to gravitational lensing, we could see a single steady star. Its temperature measurements confirmed that it was a blue supergiant. However, because the light we receive is stretched, or redshifted, by its long journey, Icarus does not appear blue to our eyes today, but instead shows a reddish or pinkish hue. When this light first left Icarus, the universe was only about 30% of its current age of 13,800,000,000 years. Kelly and his team believe that similar microlensing events could one day help us identify the very first stars that ever shone in the cosmos. The name Max J 1149 comes from the Massive Cluster Survey, and refers to the star's coordinates based on the J2000 astronomical epoch. While Kelly had initially wanted to call the star Warhol, as a nod to Andy Warhol's famous saying about everyone having 15 minutes of fame, the team eventually settled on the name Icarus, inspired by the mythical Greek figure who dared to fly too close to the sun. The discovery of Icarus has opened an exciting new window into the early universe. It shows that by combining the colossal gravitational lensing effect of massive galaxy clusters with the more delicate microlensing from smaller objects inside those clusters, astronomers can not only study ancient stars but also test theories about dark matter and catch glimpses of rare, high-energy events in galaxies that existed when the universe was still young. When Hubble spotted it, it was the farthest star ever observed. The light we see from Icarus began its journey when the universe was only about 30% of its current age. At that moment, it was at least 100 times farther away than the nearest star to us. And yet, we can still go farther, into distances so great they challenge the very limits of our understanding. Far away in the constellation of Cetus, there lies a star with a name that sounds like it was pulled straight from a fantasy tale, Arendelle. Officially called WHL 0137LS, it was spotted in the year 2022 by the Hubble Space Telescope. This is not just any star. It is the farthest and earliest star ever seen by human eyes, its light travelling for nearly 13 billion years before finally reaching us. Yet, because the universe has been stretching and expanding all this time, Arendelle's true location today is a staggering 28 billion light-years away. Before Arendelle's discovery, the record was held by another distant star known as Max J, 1149 Lensed Star 1, nicknamed Icarus. Found by Hubble in the year 2018, Icarus sat at a comoving distance of about 14.4 billion light-years. Arendelle, however, shattered that record. The only reason we can see stars like Arendelle at such impossible distances is because of a cosmic trick called gravitational lensing. In simple terms, massive galaxy clusters between us and the star bend and magnify its light, acting like a giant natural telescope. In Arendelle's case, the galaxy cluster WHL 013708 sits perfectly in the way, focusing the star's ancient light toward Earth. Simulations suggest its brightness was boosted by anywhere between 1,000 and an astonishing 40,000 times. Hubble's camera first caught Arendelle's light on 4 separate occasions: the 7th of June 2016, the 17th of July 2016, the 4th of November 2019, and the 27th of November 2019. The official announcement came later, on the 30th of March 2022. The name Arendelle comes from Old English, meaning morning star or rising light. But there's also a wink to literature here. Arendelle is a heroic half-elven character in J.R.R. Tolkien's The Silmarillion, who sails the heavens carrying a brilliant jewel that shines like a star. NASA astronomer Michelle Thaler confirmed the Tolkien reference was very much intentional. Arendelle's home galaxy, WHL 0137ZD1, got its own nickname, Sunrise Arc, because the gravitational lensing stretched its light into a graceful glowing crescent. Both Hubble and the James Webb Space Telescope have continued watching Arendelle, hoping to learn more. Webb, with its greater sensitivity, can study the star's light in detail to see whether it is a lone star or perhaps 2 stars in orbit. By looking at its spectrum, scientists can also detect if the star contains any elements heavier than hydrogen and helium. On the 30th of July 2022, Webb captured its first image of Arendelle. A little over a year later, on the 8th of August 2023, both Hubble and Webb recorded its colours. Webb's observations revealed that Arendelle is a massive blue-white B-type star, more than twice as hot as our Sun, and about 1 million times brighter. There are even hints that it might have a cooler, redder companion star. However, in early 2025, a new scientific paper suggested the magnification might actually be only 43 to 67 times, far less than the original estimate, which could mean Arendelle may not be a single star after all. The light we see from Arendelle began its journey just 900 million years after the Big Bang. Its redshift, a measure of how much the light has been stretched by the expansion of space, is 6.2, meaning that it took 12.9 billion years for that light to reach us. Today, the universe has placed Arendelle at an unimaginable 28 billion light-years away from Earth. If it truly is a single star, its surface temperature lies somewhere between 13,000 and 16,000 Kelvin, and it blazes with a luminosity of between 600 and 31,000 and nearly 4 million times that of our Sun. But there's a puzzle. The way its light behaves suggests it might actually be 2 stars, one a hot blue star at around 34,000 Kelvin, and the other cooler at about 9,000 Kelvin. The data is still too limited to say for sure, and if there are indeed 2 stars, each might be magnified differently, making the mystery even deeper. Far beyond the cold, stormy blue world of Neptune lies a vast and shadowy realm, a cosmic wilderness where the frozen relics of our solar system's birth have drifted undisturbed for billions of years. Here, in the frigid blackness, these ancient fragments are perfectly preserved by the deep freeze of space, untouched since the earliest days of the Sun and planets. To reach this lonely and mysterious frontier from Earth, we would have to travel outward step by step. First, we would pass the rocky worlds, Mercury, Venus, Earth, and Mars. Beyond Mars, we would sail past the swirling clouds of Jupiter, the largest planet of them all, and then past Saturn with its majestic rings. Further still, we would leave behind the pale blue giants Uranus and Neptune. Only then, after this long voyage, would we arrive at our destination, the Kuiper Belt, a gigantic ring of icy debris that circles the Sun like a frozen halo. But the Kuiper Belt is not simply a distant scattering of frozen rocks. It is a time capsule, a vault of untouched material from more than 4.5 billion years ago, the very building blocks from which our planets once formed. It holds dwarf planets, strange icy worlds, and mysterious objects that have puzzled astronomers for decades. Before we knew for certain that the Kuiper Belt existed, scientists had long suspected there was something out there. For many years, Pluto, everyone's favourite dwarf planet, was thought to be alone in the darkness beyond Neptune, but its tiny size and strange tilted orbit hinted that it might not be a lonely wanderer at all. In the year 1951, the Dutch-American astronomer Gerard Kuiper suggested that a belt of icy worlds might exist just beyond Neptune's orbit. The idea remained only a theory for decades, because no telescope at the time was powerful enough to spot such distant, faint objects. That changed in the year 1992 when astronomers David Jewett and Jane Liu discovered the first confirmed Kuiper Belt object, or KBO, which they named 1992 QB1. Pluto had been discovered much earlier, in 1930, and its largest moon, Charon, was found in 1978. Yet, only after the discovery of 1992 QB1 did scientists realise that Pluto and Charon were actually part of a much larger icy population. Since that historic find, thousands more Kuiper Belt objects have been identified, revealing a vast hidden frontier beyond Neptune. To picture the Kuiper Belt's place in our solar system, imagine we are travelling in a spaceship starting from the Sun and heading outward. First, we pass the inner rocky worlds, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter lies the asteroid belt, a thin ring of rocky fragments left over from planet formation. This asteroid belt sits about 2.2 to 3.2 astronomical units from the Sun, with 1 astronomical unit being the distance from the Earth to the Sun. Most known asteroids live here, from the giant Vesta, about 525 kilometres across, almost the distance from London to Belfast, to tiny space rocks only a few dozen kilometres wide. Yet, despite its size, the combined mass of all the asteroids in this belt is only about 3% of the mass of our Moon. Beyond the asteroid belt rise the great outer planets, Jupiter, Saturn, Uranus and Neptune, massive worlds that dominate the outer solar system. Then, at 30 astronomical units from the Sun, we finally cross into the Kuiper Belt. This frozen realm stretches from 30 to 50 astronomical units and is home to countless treasures, dwarf planets such as Pluto, Haumea, Eris, and Makemake, along with an uncountable number of smaller icy bodies. Like the asteroid belt, the Kuiper Belt is made of ancient debris from the earliest days of the solar system. Scientists believe these objects are some of the oldest surviving pieces of the swirling cloud of gas and dust, the solar nebula, that once formed the Sun and planets. Long ago, these frozen fragments might have merged into another planet, but Neptune's powerful gravity stirred up their orbits and kept them from coming together. Unlike the asteroid belt, which is made mostly of rock, the Kuiper Belt is rich in frozen methane, ammonia, and water ice, forming a thick donut-shaped ring of icy rubble. It contains hundreds of thousands of large icy bodies, more than 100 kilometers across, over 1 trillion comets, and countless smaller pieces of debris. The distances between these objects are staggering, on average between 0.02 and 0.1 astronomical unit apart, which is roughly 10 million kilometers. Out here, in the dim outer reaches of the solar system, these icy worlds drift almost silently, holding vital clues about the birth of planets, the history of comets, and perhaps even the origins of life itself. And the Kuiper Belt is not the end of the story. Beyond its main region lies the scattered disk, where icy bodies are flung onto stretched and tilted orbits, some reaching nearly 1,000 astronomical units from the Sun. A few objects wander even farther still, on paths that may take them toward the most distant structure of all, the Oort Cloud, the farthest frontier of our Sun's domain. far beyond the planets we know, past the blazing sun, the rocky inner worlds, and the giant planets made of gas and ice, there lies one of the most mysterious structures in our cosmic neighbourhood, the Oort Cloud. This colossal sphere of icy debris surrounds our entire solar system like a ghostly shell. It is so unimaginably far away that even the most powerful telescopes ever built cannot see it directly. Astronomers believe the Oort Cloud begins roughly 2,000 astronomical units from the Sun, and may stretch all the way to 100,000 astronomical units, almost halfway to the nearest stars. To give some perspective, 1 astronomical unit is the distance from Earth to the Sun. That means the Oort Cloud begins more than 2,000 times farther away than Earth and the Sun, and at its edge it is 50 times farther than Pluto. Closer in, but still beyond Neptune, lies another great realm, the Kuiper Belt. This vast, icy region is thousands of times nearer to the Sun than the centre of the Oort Cloud. The Kuiper Belt is shaped like a giant flattened ring, or donut, while the Oort Cloud is thought to be a perfect sphere, like a gigantic bubble of frozen fragments drifting in space. Despite their differences in shape and distance, these two regions share something in common. They are the birthplaces of comets. The Oort Cloud sends us many of the so-called long-period comets, which take thousands or even millions of years to complete an orbit around the Sun. The Kuiper Belt, on the other hand, is home to short-period comets, which swing around the Sun in less than 200 years. The Kuiper Belt that exists today is only a shadow of its former self. In the early days of the solar system, astronomers believe it held between 7 and 10 times the mass of Earth. But as the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, shifted their orbits, their immense gravity flung most of that material into space, or toward the Oort Cloud. Now, the Kuiper Belt contains only about 10% of Earth's mass. Even now, the Kuiper Belt is slowly eroding. From time to time, icy bodies collide, shattering into smaller pieces. Some fragments become dust that the solar wind blows out of the solar system. Sometimes Neptune's gravity nudges objects onto a new path, sending them toward the Sun to become short-period comets. As these comets draw close to the Sun, its heat causes their icy surfaces to vaporize, creating the spectacular glowing tails we can see from Earth. Some of the most famous comets we know come from the Kuiper Belt or its nearby scattered disk. One example is Halley's Comet, which has an average orbital period of 76 years. Another is Comet Shoemaker-Levy 9, which famously broke apart and slammed into Jupiter in the year 1994, the first collision between 2 solar system bodies ever witnessed by humans. Jupiter, of course, survived the blow, but the scars of the impact were visible from Earth for weeks. Not long ago, the news carried reports of a near-Earth asteroid named 2024 Y4. While there is an extremely tiny chance of it hitting our moon, and an even smaller chance of striking Earth, astronomers assure us that short-period comets from the Kuiper Belt pose no threat to us for at least the next 100 years. The Oort Cloud remains beyond our reach, but the Kuiper Belt is a different story. While most of what we know about it comes from Earth-based telescopes and the Hubble Space Telescope, only one spacecraft has ever been there: NASA's New Horizons. In 2015, New Horizons made history with its breathtaking flyby of Pluto, capturing the most detailed images ever taken of the dwarf planet and its moons. But the mission did not end there. On New Year's Day of 2019, New Horizons flew past a small Kuiper Belt object called 2014 MU69, later named Arakoth, a word meaning sky in the Powhatan and Algonquian languages. This was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto. The spacecraft came within about 3,500 kilometers of Arakoth's surface. Arakoth turned out to be unlike anything scientists had seen before, a contact binary made of 2 icy lobes joined together into one body. It looks like a flattened snowman, about 35 kilometers long, 20 kilometers wide, and 10 kilometers thick. Though it is tiny compared to planets, Arakoth carries clues about how the building blocks of planets, called planetesimals, formed in the early solar system. Before this encounter, 2 main theories existed: hierarchical accretion, which suggested that small objects smashed together at high speeds to form bigger ones, and local cloud collapse, which proposed that nearby material slowly came together under its own gravity. The smooth surface of Arakoth and the absence of violent collision marks strongly support the second theory. In the words of planetary scientist Alan Stern, the New Horizons leader, the evidence decisively solved a multi-decade debate about how planetesimals form. And of course, there is Pluto, the Kuiper Belt's most famous resident. New Horizons revealed its stunning heart-shaped region, called Tombor Regio, after Pluto's discoverer Clyde Tombor. The western half of this heart is Sputnik Planitia, a vast glacier made of nitrogen ice that stretches about 1,000 kilometers across and sinks roughly 4 kilometers deep, making it the largest known glacier in the solar system. Data from New Horizons showed that Pluto is far more complex than scientists once thought, with hints that a hidden ocean of water ice might exist beneath its frozen surface. That icy heart may not just be a charming shape, it might be the clue to one of Pluto's greatest secrets. A recent scientific investigation, led by astrophysicist Harry Valentine from the University of Ben, has offered an intriguing new explanation for one of Pluto's most famous features, its giant pale heart. For years, people wondered why this heart-shaped mark appeared on Pluto's icy surface. Now researchers believe that the answer might be a slow but powerful cosmic collision. According to Valentine's team, the western side of Pluto's heart may have been formed when a large object slammed into the dwarf planet at a low speed and from a slanted angle, not head-on. Imagine tossing a water balloon across a dry sidewalk, the way you might skip a flat stone across a calm pond. Instead of bursting in a neat circle, the balloon scrapes the ground, bursts, and leaves an elongated splash of water. In much the same way, this angled impact could have left an enormous splatter pattern on Pluto's surface, shaping the left half of its famous heart. But Pluto wasn't the only world to amaze scientists during NASA's historic New Horizons mission. The spacecraft also captured breathtaking close-up images of Charon, Pluto's largest moon. One of Charon's most striking features is its immense equatorial tectonic belt, a rugged scar stretching across its middle. This gigantic geological feature hints at a dramatic past. It may be evidence of a long-vanished ocean of liquid water ice hidden beneath Charon's crust billions of years ago. The story of exploration does not end here. New Horizons is expected to leave the Kuiper Belt, that vast ring of icy worlds beyond Neptune, sometime between the years 2028 and 2029. As of now, NASA has no confirmed destination for another close flyby, but it remains possible that a new, intriguing target will be found. In the meantime, powerful tools like the James Webb Space Telescope could help scientists study the chemistry and surface features of Kuiper Belt objects from afar. And perhaps, in the distant future, humanity might send a robotic probe to land on one of these mysterious frozen bodies, or even bring back a sample to Earth. This far-off region of space remains a vast frozen frontier full of secrets. As technology improves, future missions will journey deeper into the Kuiper Belt, unveiling its ancient mysteries one icy world at a time. Who knows what strange and wonderful discoveries still await us in this distant wilderness at the edge of our solar system. In the year 1977, two daring explorers set out on what might be one of the greatest adventures in the history of space travel. These were not astronauts in shiny suits, but two robotic pioneers, Voyager 1 and Voyager 2, each carrying humanity's curiosity far beyond our home. Their mission was bold, to unravel the cosmic mysteries of our solar system and discover more about our place in the vast universe. They did far more than anyone expected. They sent back some of the very first and clearest pictures we had ever seen of the giant planets in the outer solar system. Colossal worlds like Jupiter, Saturn, Uranus, and Neptune, along with their strange and beautiful moons. And even now, after more than 47 years and over 24 billion kilometers of travel, they are still whispering to us from the dark, cold reaches of interstellar space. Voyager 1 and Voyager 2 are not just collections of metal, wires, and instruments. They are symbols of what humanity can achieve at its very best. Curious, fearless, ambitious, and resilient. They did not merely take breathtaking close-up portraits of the gas giants, they captured the hearts and imaginations of millions back on Earth. These are the farthest travelled human-made objects in history, true trailblazers venturing into territory where no one and nothing has gone before. Their journey takes them far beyond the reach of any rescue, into a lonely darkness where no other machine or human has ever wandered. As Edward Stone, the Voyager mission's project scientist, once reflected, "When I look back, I realise how little we actually knew about the solar system before Voyager. Time after time we discovered things we did not even know were there to be discovered. It is a curious twist of fate that the most important discoveries at the very edge of our solar system are not being made by shiny new technology, but by these aging explorers from the 1970s. Their computers have less memory than the chip inside a modern car key fob. They still use 8-track magnetic tape to store data, technology older than many of the people reading this. That is the strange reality of deep space exploration. The vast distances and decades-long travel times mean that by the time a spacecraft arrives at its destination, its technology is considered ancient back on Earth. When they launched in 1977, Voyager 1 and Voyager 2 were never intended to reach interstellar space. They were designed for a 5-year mission to study Jupiter, Saturn, and their largest moons. This was only possible thanks to a rare planetary alignment that occurs just once every 176 years, an alignment that last happened when Napoleon Bonaparte ruled France. This cosmic lineup allowed each probe to slingshot from planet to planet, using the immense gravity of each world to boost its speed without burning precious fuel. After their work at Jupiter and Saturn was done, Voyager 2's mission was extended to include visits to Uranus and Neptune, making it the only spacecraft to have ever visited those two ice giants. Once these flybys were complete, NASA set them on an even grander adventure, the Voyager Interstellar mission. This final stage would carry them to the farthest edges of the Sun's influence, into mysterious regions like the termination shock and the turbulent heliosheath, before finally breaking through the heliopause into the true emptiness of interstellar space. How did they achieve so much more than originally planned? The secret lay in the brilliant, forward-thinking design choices made by NASA's engineers. Each Voyager carries 11 scientific instruments, many with backup systems that can be switched on if the primary ones fail. For navigation, the probes have gyroscopes for stability, special reference sensors, and 16 hydrazine thrusters, 8 of which are backups. This redundancy proved invaluable. After 37 years in space, Voyager 2's main thrusters failed, and its backups, untouched for 4 decades, were activated. Incredibly, they worked perfectly. Powering each probe is a radioisotope thermoelectric generator, or RTG, which turns the heat from the slow decay of plutonium-238 into electricity. At launch, each generator produced about 157 watts, enough to power a small laptop and charge a phone, and while the output decreases by half roughly every 87 years, it was enough to keep the Voyagers alive well into the 21st century. NASA expects they will still be able to send back data until around the year 2025. The Voyager's computers, though primitive by today's standards, were cutting edge in their time. Their wide-angle and narrow-angle cameras are controlled by an onboard command system capable of fault detection and automatic corrections. Every feature was built to last because once launched, there would be no way to fix or upgrade them. And so, with their ancient but trusty technology, these two golden messengers continue their long voyage into the dark, carrying not only humanity's instruments, but also humanity's hopes. One of the greatest secrets behind the Voyager mission's success lay in their computers. Each probe carried a special brain called the Attitude and Articulation Control Subsystem. And no, despite its name, it wasn't there to scold the spacecraft for having a bad attitude. In space talk, attitude simply means the way the spacecraft is positioned in relation to Earth. Without this precise orientation, the Voyager probes would not have been able to point their large, high-gain antennas toward our planet, and they would have been unable to send or receive even the faintest signals from NASA's deep space network. This was absolutely vital because the probe's radio transmitters were incredibly weak, putting out about the same power as the tiny light bulb inside your refrigerator. At such mind-boggling distances from Earth, those signals fade into whispers so faint that only the most sensitive antennas on Earth can detect them. For the Voyagers to talk to their team, and for the team to talk back, the probe's antennas had to be aimed with pinpoint accuracy at our planet, and the Deep Space Network also had to know exactly where in the heavens the probes were. Without this careful alignment, they would have been as hopelessly lost as a single needle, hidden somewhere inside a haystack stretching 287 billion kilometers across. Each Voyager carried a 3.7-meter wide antenna for sending information in real time, and an 8-track digital tape recorder for saving data to transmit later. This tape recorder could store 536 megabits of information, enough to hold about 100 photographs. At the time, this was a huge leap forward compared to the earlier Pioneer probes, which had no ability to store data on board. Of course, by today's standards, it's tiny. Your smartphone probably holds thousands of times more information. But what the Voyagers lacked in storage, they made up for in toughness. The company that built their tape recorders, Odetics, claimed that each unit could run through more than 4,000 kilometers of tape without showing any wear. These devices were designed to survive the harshest and most unforgiving conditions in space, extremes that had never been tested before, and they proved themselves. The Voyager's tape recorders worked flawlessly, without losing data or breaking down, until they were finally shut down to save power. Not bad for machines that were already 12 years older than the World Wide Web when that moment came. Durability was a top priority during the Voyager's planning. Space is full of unknown dangers, and to reach Jupiter, both spacecraft would have to pass through the asteroid belt. In the early days, scientists feared this belt might be so packed with rocks and debris that any spacecraft trying to cross it would be torn to pieces. But when Pioneers 10 and 11 successfully passed through, Voyager's team gained the confidence to try the same route. Failure would have meant the mission ending before it even reached its first destination. Thankfully, both Voyagers sailed through the asteroid belt unharmed, teaching us that this region is, in fact, mostly vast empty space. Even with these victories and better-than-expected performance, another challenge loomed: the bitter cold of deep space. NASA had fitted the probes with heaters to keep their systems warm, but as the power supply slowly weakened over the decades, some heaters had to be switched off. When the heater for one of Voyager's cosmic ray detectors was turned off just 2 years ago, its temperature plunged by 70 degrees Celsius. Everyone assumed the instrument would soon fail. After all, you can't send a repair crew 23 billion kilometers away. But astonishingly, it kept running perfectly. The fact that these probes have been working for 45 years is a shining tribute to their engineering and endurance. So, with all this technology in place, what did they see? To answer that, let's rewind to the very start of their journey. On the 20th of August, 1977, NASA launched Voyager 2 from Cape Canaveral, Florida. Its twin, Voyager 1, lifted off exactly 2 weeks later, on the 5th of September. Even though both were headed for Jupiter, Voyager 1's route was shorter and faster, so launching it second made perfect sense. It soon overtook Voyager 2 on the 15th of December, 1977, and became the first to leave the asteroid belt. Together, this daring pair of explorers was about to capture a breathtaking gallery of photographs unlike anything the world had ever seen. Just 13 days after launch, Voyager 1 sent back its very first picture. Taken from a distance of 11.6 million kilometers, it showed our planet and its lone moon hanging together in the blackness of space. It was a sentimental starting point for the mission, reminiscent of the famous Earthrise photograph taken by the Apollo 11 crew just 8 years earlier. Our fragile blue home glows softly against the endless dark, a hauntingly beautiful image, especially when you consider how far the probe had already travelled and how much more it would see in the decades to come. From there, the wait began. It would take almost 2 years for Voyager 1 to reach its first destination, Jupiter. Not bad, considering the gas giant lies 714 million kilometers from Earth. Voyager 1 arrived first on the 5th of March, 1979, cruising at 17 kilometers per second, about 2 kilometers per second faster than Voyager 2, which, despite launching first, reached Jupiter 4 months later, on the 9th of July, 1979. Voyager 1 was not the first spacecraft to meet Jupiter. Pioneer 10 had done so 7 years earlier, in 1972. But while Pioneer gave us valuable science, it didn't capture the public's imagination in the same way. Voyager's images did. The photos were so sharp and vibrant that they seemed almost unreal, as if they were paintings rather than actual photographs. In one stunning image, Jupiter's swirling clouds dominate the frame, with 2 of its moons visible, Io, glowing yellowish on the left, and Europa, pale and beige on the right. Voyager 1 even documented its approach to Jupiter in motion. By taking photographs every 10 hours, exactly one Jupiter day, it captured the planet from the same point in its rotation each time. These 66 images were stitched together into a mesmerizing time-lapse video, showing the spacecraft's journey from the 6th of January to the 3rd of February, 1979, as it closed the gap over a span of 27 million kilometers. One of the very first things that left scientists absolutely astonished was the atmosphere of Jupiter. They had expected to find the planet's air flowing in neat east-west and west-east winds, each confined to its own atmospheric zone like well-behaved stripes. But the reality was far more chaotic and mesmerizing. What the Voyager spacecraft revealed was a world of roaring turbulence, towering plumes, and swirling rotational patterns so vivid that they almost seemed alive in the images. You could instantly tell that Jupiter's atmosphere is one of the most dynamic and restless environments in the solar system. Scientists had long suspected that Jupiter's most famous feature, the colossal Great Red Spot, was a vast counterclockwise spinning storm. Voyager's instruments confirmed this suspicion beyond doubt, but that was only the beginning. The spacecraft also revealed that the Great Red Spot was far from alone. Jupiter's skies were teeming with other whirling tempests. One example was a large white storm swirling just beneath the Great Red Spot, an unexpected find that hinted at countless other hidden tempests. It turns out Jupiter's atmosphere is absolutely littered with these monster storms, and until Voyager's visit, we had no idea they even existed. When most people hear the word rings, they think of Saturn. But data from earlier missions like Pioneer had hinted that Jupiter might have its own set of rings too. Voyager not only confirmed their existence, it became the first spacecraft to actually photograph them. The images showed 4 delicate, faint Jovian rings, captured as Voyager was departing the planet. In the photograph, the rings appear as a glowing orange line stretching from the planet's edge, delicate yet majestic. Before leaving Jupiter's realm, Voyager delivered what was perhaps its most jaw-dropping revelation, the astonishing volcanic activity on its moon Io. Before this, planetary geologists were convinced Io would be much like our moon, scarred with countless craters from ancient impacts. And indeed, Voyager did spot circular features on Io's surface, but they weren't craters. They were something far more dramatic, volcanic calderas and lava lakes. The spacecraft revealed that Io had lava flows less than 1 million years old, which in planetary terms is incredibly recent. In fact, Io turned out to be the most geologically active world in the entire solar system. The surprise was unimaginable. Scientists had expected a frozen, lifeless moon, but instead found a hellish landscape bursting with activity. Some of the volcanoes erupted with such force that blue-hued plumes of material and gas were launched 100 kilometers into space. These eruptions happened relentlessly, sometimes every few hours, providing Voyager with several breathtaking snapshots of a truly alien world. Just beyond Io lies Europa, a moon that could not be more different. Voyager 1 was the first to show that Europa's surface is covered in strange scratch-like markings, long dark lines that scientists believe are fractures in a thick sheet of surface ice. The spacecraft's data also hinted at something even more tantalizing. Beneath Europa's icy crust, there might be a hidden, swirling ocean. Today, we believe that this subsurface ocean could potentially harbour the conditions necessary for life. At present, we know of 95 moons orbiting Jupiter. But before the year 1979, astronomers had only identified 13. Voyager's sharp-eyed cameras discovered 3 more, Thebe, Metis and Adrastea, raising the total count at the time to 16. Unfortunately, the newly found moons were too faint for Voyager to capture in detail, but later observations have given us clearer images. After 21 months of travel through space, Voyager 1 reached Saturn in November of 1980, with its twin Voyager 2, arriving 9 months later in August of 1981. And of course, when you think of Saturn, you think of rings. Before Voyager's flyby, scientists believed Saturn had only 5 major rings, but the spacecraft revealed that each of those rings is actually made up of hundreds of narrow ringlets, like threads woven into an intricate cosmic tapestry. Voyager also discovered a brand new ring, now called the G ring, and provided our first close look at the F ring, first detected by Pioneer 11 in 1979. To everyone's amazement, the F ring was not a smooth, single structure. It was kinked, braided, and made up of multiple strands. Voyager even spotted two tiny shepherd moons, Prometheus and Pandora, whose gravity helps keep the F ring's material from drifting away. Another bizarre discovery came from Saturn's B rings, which appeared to contain ghostly, spoke-like patterns, broad, radial streaks that seemed to float across the ring system. Up until 1980, scientists thought the shapes and movements of Saturn's rings were controlled entirely by gravity. But these mysterious spokes did not follow the rules of orbital mechanics. The leading theory now suggests that they are caused by electrostatic forces, with tiny dust grains being charged and lifted away from the ring surface. Yet not all of Voyager's findings were cheerful. The data suggested that Saturn's rings are slowly disappearing, with gravity pulling icy particles into the planet as a fine, dusty rain. According to NASA's calculations, the rings could vanish entirely in about 300 million years, a mere blink in cosmic time. The mysteries uncovered by Voyager were so compelling that, in the 1990s, NASA launched a dedicated mission to Saturn, the Cassini probe. Launched in 1997, Cassini spent 13 years orbiting the ringed planet, revealing even more about its complex system. Voyager also expanded our knowledge of Saturn's moons. Before its arrival, 14 were known, but Voyager found 3 more, bringing the total to 17. Among the most intriguing were Titan and Enceladus. Pioneer 11 had been the first to photograph Titan, but Voyager revealed that this enormous moon possesses a thick, nitrogen-rich atmosphere, the only moon known to have such an atmosphere outside Earth. Enceladus, on the other hand, turned out to be a small but astonishingly active world. From a great distance, Voyager photographed a faint icy plume rising from its surface, an eruption of water vapor. This tiny moon ejects about 300 kilograms of vapor every second, shooting it up to 10,000 kilometers high, 20 times its own diameter. These plumes create a donut-shaped cloud that feeds one of Saturn's icy rings. Although Voyager's data suggested this activity, it would take Cassini decades later to confirm it in spectacular detail. Further geological evidence and high-resolution images have revealed something unexpected about the icy moon Enceladus. Its surface is not uniform at all. Instead, it is a fascinating mix of ancient and young terrains. The left side, smooth and relatively unscarred, is clearly the newer region. The right side, however, is covered in a dense field of impact craters, marking it as much older. This contrast shows that Enceladus is far more geologically active than scientists once believed. Before these findings, no one thought this little moon had such a restless and changing surface. But before we can head toward the strange tilted world of Uranus, we must bid farewell to Voyager 1. After its historic flyby of Saturn's majestic rings and the haze-covered moon Titan, the probe's path was bent upward and away from the flat plane in which most planets orbit, a cosmic exit ramp that sent it toward interstellar space. It would take another 32 years before it finally crossed that boundary, but that is a story for later. Its twin, Voyager 2, took a different route. It swung around Saturn in a precise gravitational slingshot maneuver, using the planet's immense pull to propel it onward toward Uranus and then Neptune. These would become the very first, and still the only, close encounters humanity has ever had with these distant ice giants. 5 years after arriving at Saturn, Voyager 2 reached Uranus in January of the year 1986. At its closest approach, the spacecraft passed within 81,500 kilometers of the planet's upper cloud tops. What it saw was surprising. Unlike Jupiter and Saturn, Uranus showed almost no obvious cloud formations. Instead, it displayed a calm, pale, and nearly featureless atmosphere, challenging scientists' ideas about how gas giant atmospheres work. In a false color image, subtle differences could be seen between Uranus's polar regions, which are themselves tilted on a wild 98-degree axis. But there was another tilt that left scientists stunned: the planet's magnetic field. Before Voyager 2's visit, no one even knew if Uranus had a magnetic field. The probe revealed that not only did it have one, but it was tilted an incredible 59 degrees away from the planet's rotational axis. On Earth, The difference between our magnetic and rotational poles is only about 12 degrees. This extreme misalignment shattered previous models of how planetary magnetic fields are supposed to work. Because of this tilt, Uranus's magnetosphere, the bubble of space shaped by its magnetic field, wobbles and lurches as the planet spins, almost like a poorly thrown American football. Scientists still cannot fully simulate how this works, but Voyager's data gave them their first real clues. The spacecraft also provided the first close-up images of Uranus's dark and dusty rings, as well as the discovery of 2 new rings and 2 small shepherd moons that help keep one of those rings in place. In a photo taken from 4 million kilometers away on the 21st of January 1986, the outermost ring can be seen faintly glowing against the blackness. Voyager 2 also greatly expanded our knowledge of Uranus's moons. Before its arrival, astronomers knew of only 5. The probe sent back the first ever close-up images of these original moons, while also discovering 11 new ones, increasing the total to 16. Today, we know that Uranus has 27 moons in all. The 5 original moons are Oberon, Umbriel, Titania, Ariel, and Miranda. Oberon and Umbriel, photographed on the 24th of January 1986, are dark, heavily cratered, and appear geologically inactive. Titania, the 4th farthest of the 5, is marked by enormous faults and deep canyons, hinting at past tectonic activity. Ariel is the brightest and possibly the youngest looking of them all. A close photo taken from just 129,000 kilometers away revealed a surface scarred by fault valleys and streaked with icy flows, clear signs of a dramatic geological past. But the greatest surprise was Miranda, the innermost of the large moons, second only to the tiny moon Puck in proximity to Uranus. Voyager 2 flew past Miranda on the 4th of January 1986, at a distance of only 30,000 kilometers. What it saw was astonishing, a patchwork world shaped by a chaotic history. Huge canyon-like troughs plunge 20 kilometers deep. Oval, racetrack-shaped markings stretch across its surface like cosmic fingerprints. There are bright and dark regions, smooth and cratered areas, and bizarre chevron patterns suggesting that Miranda's crust had been ripped apart and then reassembled, piece by piece. 3 weeks later, on the 25th of January, Voyager 2 took a final farewell shot of Uranus from 1 million kilometers away before heading toward its last planetary target, Neptune. After 3 more years of travel, racing through the void at 54,000 kilometers per hour, Voyager 2 finally arrived. On the 25th of August 1989, just over 12 years after leaving Earth, it came within 5,000 kilometers of Neptune's North Pole, the closest any spacecraft has ever come to the blue giant. It revealed that Neptune's atmosphere is mostly hydrogen, with enough methane to give it its striking blue color. The probe also measured astonishing winds, the fastest in the entire solar system, with speeds near the equator reaching almost 1,100 kilometers per hour. Neptune had one more surprise in store, a revelation that showed just how wild, restless, and downright ferocious its weather systems could be. Among the planet's many marvels, scientists spotted a gigantic storm that they fittingly named the Great Dark Spot. This swirling behemoth rotated in a counterclockwise direction, much like Jupiter's famous Great Red Spot, but it had a far darker and more mysterious appearance. What was even more astonishing was its sheer power. The winds raging inside it reached staggering speeds of up to 2,400 kilometers per hour, making them the fastest winds ever recorded anywhere in the entire solar system. NASA analyst Ken Bollinger, reflecting on the Voyager 2 discoveries back in the year 1989, summed up the excitement perfectly. Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling. There's changes going on constantly on Neptune that happen very, very fast. And Neptune's surprises didn't end there. For the first time in history, Voyager 2 managed to capture images of the planet's elusive rings. Up until the year 1986, astronomers suspected Neptune might have a ring system, but no one could be completely sure. When the truth was finally revealed, it came with a twist. Rather than being solid, continuous bands like Saturn's, Neptune's rings were strange, dusty, and incomplete, existing in the form of several partial arcs. These arcs puzzled scientists, raising big questions about how they formed and how they managed to remain stable instead of simply dispersing into space. Of course, no visit to Neptune would be complete without paying a call to its largest moon, Triton, a frozen and otherworldly realm. Triton holds the record as the coldest known planetary body in the solar system, yet it is far from lifeless. Voyager 2 revealed a cracked and fractured landscape dotted with erupting geysers that shot plumes into the thin atmosphere. Over its southern pole lay a strange pinkish nitrogen ice cap, giving the moon a ghostly beauty. Scientists even spotted dark streaks on the surface, possibly the telltale signs of cryovolcanoes, volcanoes that erupt ice instead of lava. As if that were not enough, Voyager 2 discovered 6 new moons orbiting Neptune during its flyby. Then, with its mission at Neptune complete, the spacecraft turned its camera around for one final farewell snapshot of Neptune and Triton before its trajectory, bent by the planet's gravity, sent it diving downward out of the ecliptic plane, the flat, disk-like region in which most planets orbit the Sun. From there, it set course for the great unknown of interstellar space, just as its twin, Voyager 1, had done 9 years earlier. Speaking of Voyager 1, by the year 1980, only 1 year after Voyager 2's close encounter with Neptune, it was already about 6 billion kilometers from Earth. To save precious power for the long and lonely journey into interstellar space, mission planners intended to shut off its cameras forever. But famed astronomer Carl Sagan had another idea. Why not turn the camera around and take one last look at home? And so, on the 14th of February 1990, Voyager 1 captured the most distant selfie in human history, the legendary pale blue dot photograph. From 6 billion kilometers away, Earth appeared as nothing more than a faint speck, a single pixel suspended in the deep black of space caught in a shaft of sunlight. Carl Sagan's poetic words about that tiny dot still echo through time. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. That message is just as powerful today as it was 33 years ago. But what happened after that? What awaited the Voyagers in the vast wilderness between the stars? In the year 1981, Voyager 1 broke free from the ecliptic, veering 35 degrees north of Earth's orbital plane. Voyager 2 would later take a different route, diving 48 degrees south. But these course changes were just the beginning of a much longer odyssey. To truly enter interstellar space, the probes would need to pass through several invisible but dramatic boundaries. First came the termination shock, the region where the Sun's supersonic solar wind slows down abruptly, colliding with the opposing flow of interstellar particles. Beyond that lay the heliosheath, where the solar wind becomes hotter and denser as it piles up. Finally, the Voyagers would reach the heliopause, the ultimate frontier, marking the boundary between the Sun's protective bubble, the heliosphere, and the space between the stars. Even beyond that, the solar system still isn't truly over. Astronomers estimate it will take Voyager 1 another 300 years just to reach the inner edge of the Oort Cloud, a vast bubble of icy objects that surrounds the solar system, and another 30,000 years to finally leave it behind entirely. While travelling through the heliosheath, the Voyagers made a discovery that forced scientists to rethink their understanding of this region. The Sun's magnetic field flips direction between its northern and southern hemispheres, creating a vast, wavy surface called the heliospheric current sheet, a little like ripples spreading outward after a stone is dropped into a pond. But when this sheet reaches the termination shock, it gets compressed, as if those ripples were suddenly hitting the edge of a pool. Voyager's instruments revealed that in this compressed state, the ripples actually break up into huge magnetic bubbles, meaning the outer boundary of the heliosheath is far messier and more turbulent than anyone imagined. Rather than a smooth, clearly defined frontier, it is a chaotic and ever-changing magnetic sea. This unexpected finding has completely reshaped scientists' models of the Sun's outermost reaches, proving once again that the Voyagers, even decades after launch, still have new secrets to share. On the 25th day of July in the year 2012, history was made. The Voyager 1 space probe, a lonely traveller launched decades earlier, became the very first human-made object to cross the invisible frontier of our Sun's influence, known as the heliosphere, and step into the vast wilderness of interstellar space. At that moment, it was racing through the darkness at an astonishing speed of about 540 million kilometers every year, the equivalent of 3.6 astronomical units annually. To give perspective, 1 astronomical unit is the distance from the Earth to the Sun, a staggering 150 million kilometers. Voyager 1 made this crossing at roughly 120 astronomical units from the Sun, a distance so far that sunlight takes more than 16 hours to reach it. This, in itself, was a revelation. Until then, nobody knew exactly where the heliopause, the boundary of the Sun's protective bubble, truly lay. Some early predictions had placed it as close as the orbit of Jupiter, while others imagined it far, far beyond. The heliopause is not a solid wall, but rather a region where two cosmic forces meet head-on, the Sun's solar wind and the interstellar medium. It is like the point where two mighty ocean currents crash into each other, churning and pushing in opposite directions. Solar wind is a constant outpouring of charged particles, electrons, protons, and alpha particles, hurled from the Sun's outer atmosphere at tremendous speeds. The interstellar medium, by contrast, is a ghostly blend of charged particles, gases, and fine cosmic dust, the leftovers from the Big Bang and the fiery deaths of ancient stars in supernova explosions. When these two streams collide, they form a shifting zone of balance, the heliopause. When Voyager 1 made its crossing, NASA scientists were thrilled, but also hesitant. The probe's instruments recorded a dramatic surge in plasma density, 80 times higher than what it had measured in the outer heliosheath, and a spike in galactic cosmic rays. This matched the predictions for entering interstellar space. And yet, something odd was missing. The ambient magnetic field did not change. This was puzzling because theoretical models predicted that the orientation of the magnetic field should shift once a spacecraft left the Sun's domain and entered a region influenced by the magnetic forces of other stars. But Voyager 1's magnetometer found no such shift. NASA's scientists were so perplexed that they waited almost an entire year before officially announcing the historic achievement. On the 5th of November, in the year 2018, Voyager 2, travelling at the slightly slower pace of 490 million kilometers per year, or 3.3 astronomical units, followed its twin into interstellar space. Its crossing also happened at a distance of 120 astronomical units from the Sun. And, like Voyager 1 6 years earlier, it too found no change in the magnetic field's direction. This was especially surprising because the Sun was at the peak of its 11-year solar cycle, a period when solar winds are at their strongest. According to earlier models, the heliosphere should have expanded during this active phase, meaning Voyager 2 should have crossed at a slightly greater distance than Voyager 1, but it did not. Both probes crossed at exactly the same point, proving that the old models were wrong. The lesson was clear. The heliosphere's edge is far more twisted, irregular, and unpredictable than anyone had imagined. One leading theory suggests that our Sun formed billions of years ago in a violent, superheated, and heavily ionized region, created by one or more nearby supernova explosions. This turbulent magnetic environment may still persist at the heliopause today. If true, the Voyagers might one day detect a change in magnetic orientation, but by then their instruments may have long gone silent, and indeed the signs of aging are already here. In early May of the year 2022, Voyager 1 began behaving oddly. Imagine being a NASA engineer sitting down at your desk ready to check the latest telemetry from your far-flung spacecraft. Signals from Voyager 1 now take 22 hours to reach Earth, like sending letters rather than text messages. But today's data makes no sense. instead of its usual precise reports on the positions of its thrusters and the exact angle of its enormous 3-meter antenna, Voyager 1 sends back lines of nonsense, endless strings of zeros or the number 377. These readouts imply that the probe is pointing in impossible directions. Yet, if that were true, you wouldn't be receiving its signal at all. And not only is the signal still coming in, it's just as strong as ever. Stranger still, the science data from Voyager 1's 4 remaining operational instruments, studying cosmic rays, magnetic fields, and the interstellar medium, remains perfectly normal. Over its long journey, the probe has had to shut down 5 of its 11 scientific instruments to save power, while 2 more have failed naturally from wear. Its energy source, 3 radioisotope thermoelectric generators fueled with plutonium oxide, has a half-life of 87 years. After 45 years in space, their output is declining. Experts expect Voyager 1 to fade completely by the mid-2020s, but none of this explains the current problem. The trouble lies in a single subsystem, the ACS, the Attitude and Articulation Control System. This is one of 3 computers aboard Voyager 1, and its job is critical. It keeps the probe's antenna locked on Earth. Without it, the spacecraft could fall silent forever, and yet, somehow, the RIS is sending gibberish, while apparently thinking that nothing is wrong. Voyager 1 has built-in safety protocols that put it into a kind of hibernation mode if something goes seriously wrong. But those have not triggered. It's as if your trusted mail carrier suddenly began speaking in an incomprehensible language every morning, yet still delivered the right packages to your door exactly on time. For NASA's engineers, the mystery was both frustrating and fascinating. The spacecraft was alive, still doing science, still talking to Earth, but its voice was garbled, and it didn't even know it. The question was clear: what exactly was going on, and could they fix it before Voyager 1's final chapter came to an end? In the middle of the year 2022, a single technical glitch might not have looked like a serious problem at first glance. But to those who understood the stakes, it hinted at the possibility that something deeper and far more dangerous might be wrong with other systems on board. If that were true, it could mean the end of the entire mission. By now, Voyager 1 was more than 23,800 million kilometers away from Earth. Any attempt to fix the problem had to be done through slow and careful deduction. Imagine playing a game of 20 questions with a friend on the other side of the solar system, except each question took 22 hours to reach them, and their answer took another 22 hours to get back. That was the reality for NASA's engineers trying to communicate with a distant spacecraft. They began by checking Voyager 1's other systems, and found that everything else seemed perfectly normal. That allowed them to rule out some of the stranger theories. No, this was not aliens playing cosmic pranks. Although NASA had always been open to the idea that the Voyager probes might one day be discovered by alien life, hence the famous golden records attached to them, the records were more of a symbolic hello than a serious attempt at conversation, and even if aliens were out there, this would be a rather odd way to say hi. The laws of physics had not suddenly collapsed either. Voyager 1 had not stumbled into a wormhole that scrambled its navigation, while still somehow keeping its radio signal intact. Since the scientific data being returned looked perfectly normal, the most likely suspect was the AACS, the Attitude and Articulation Control Subsystem, the part of the spacecraft responsible for pointing the antenna at Earth. For 4 months, scientists and engineers tested theory after theory, gently probing the problem and trying to find a solution that would fix it without making things worse. They could switch over to a backup system. Voyager 1 was designed with many redundancies, but that was not without risk. This was not even the first AX computer the spacecraft had used. A previous one had already failed years earlier. Another option was simply to ignore the problem, since the science data was still flowing in, even if some engineering information was garbled. But doing nothing risked overlooking a more serious issue. Eventually they discovered the cause. Out in the harsh, radiation-filled emptiness of interstellar space, something had caused Voyager 1 to start using that older, already broken AACS computer to send its data back to Earth. Because the computer was faulty, the information it sent became scrambled. Thankfully, the fix turned out to be simple. NASA just told Voyager 1 to start using the correct computer again. Once the command reached the spacecraft, the issue was solved. though it still took a couple of months for everything to return completely to normal. But Voyager's troubles were far from over. In November of the year 2023, another computer, the Flight Data Subsystem, developed a similar fault and stopped sending usable science and engineering information back home. It was not until June of the year 2024 that this issue was fully resolved. In July 2023, Voyager 2 had its own heart-stopping moment. A routine set of commands accidentally caused the spacecraft to turn its antenna just 2 degrees away from Earth. That tiny change was enough to completely sever communications across the vast gulf of space. NASA was suddenly deaf and blind to the probe. The only hope was to send a powerful shout from the Deep Space Network facility in Canberra, Australia, commanding Voyager 2 to point back toward home. Then came a tense 37-hour wait for the signal to travel to the spacecraft and for its reply to return. When the response finally arrived, confirming that contact had been restored, it was a moment of pure relief. One day, whether because of a malfunction, a fatal error, or simply running out of power, the Voyagers will fall silent forever. That ending is inevitable. But even when they stop speaking to us, their journeys will have only just begun. In roughly 40,000 years, Voyager 1 will pass near a star in the constellation Camelopardalis. Voyager 2, meanwhile, will drift about 1.7 light-years from the star Ross 248 in the year 296,000, and about 4.3 light-years from Sirius sometime after that. By then, Earth may be long gone, but these small, tireless explorers will still be wandering the Milky Way, lonely messengers of a species that once looked up and dreamed of touching the stars. The prevailing scientific theory that describes the origin and evolution of our universe is known as the Big Bang. It is crucial to understand that the Big Bang was not an explosion in space, but rather an expansion of space itself. Imagine a tiny, incredibly hot, an extremely dense point that contained all the matter and energy of the universe. From this initial state, space began to stretch and expand, carrying everything within it. This expansion has been ongoing for approximately 13.8 billion years, leading to the vast and complex universe we observe today. The very first moments of the universe, immediately after the Big Bang, are shrouded in extreme conditions that are difficult to comprehend. Scientists use theoretical models and particle physics experiments to piece together what might have happened. In the first tiny fraction of a second, an event known as cosmic inflation is thought to have occurred. During this period, the universe expanded exponentially, growing from a size smaller than an atom to roughly the size of a grapefruit in an unimaginably short time, perhaps 1/trillionth of a trillionth of a trillionth of a second. This rapid expansion smoothed out irregularities and stretched the universe to a nearly flat shape, which aligns with observations. During and immediately after inflation, the fundamental forces of nature, gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force, which were once unified, began to separate, taking on their distinct roles. As the universe continued to expand, it also cooled down. In the first few minutes after the Big Bang, the temperature was still incredibly high, billions of degrees Celsius. At these extreme temperatures, matter could not exist in its familiar forms. Instead, the universe was a hot, dense soup of elementary particles, quarks, leptons, like electrons and neutrinos, and photons, particles of light. As the universe cooled further, quarks began to combine to form protons and neutrons, the building blocks of atomic nuclei. This process occurred within the first few seconds to minutes. For example, by about 1 second after the Big Bang, the universe was cool enough for protons and neutrons to form and stabilize. Between approximately 3 minutes and 20 minutes after the Big Bang, a crucial event called Big Bang nucleosynthesis took place. During this period, the universe had cooled sufficiently for protons and neutrons to fuse together, forming the nuclei of the lightest elements. The most abundant element formed was hydrogen, consisting of a single proton. Helium nuclei, made of 2 protons and 2 neutrons, were also formed in significant amounts, along with trace amounts of lithium. However, the universe was still too hot for electrons to bind with these nuclei to form complete, neutral atoms. Electrons were still free, constantly scattering photons, making the universe opaque, much like a dense fog. Light could not travel freely through this plasma. For the next 380,000 years, the universe continued to expand and cool, but not much significant structural change occurred. It remained a hot, opaque plasma. Then, at about 380,000 years after the Big Bang, the temperature dropped to approximately 3,000 degrees Celsius. This temperature was cool enough for electrons to combine with the hydrogen and helium nuclei, forming the first stable neutral atoms. This event is known as recombination. When electrons became bound to nuclei, the universe became transparent to light. The photons that were previously trapped and scattering off free electrons were now free to travel across the cosmos. This ancient light, stretched and cooled by the universe's ongoing expansion, is what we now detect as the cosmic microwave background radiation. It is one of the strongest pieces of evidence supporting the Big Bang theory, acting as a direct snapshot of the universe when it was still very young. After recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies, and the universe was filled primarily with neutral hydrogen and helium gas. It was dark because there were no light sources other than the fading cosmic microwave background radiation. This period lasted for several 100 million years. However, gravity was slowly at work. Tiny variations in the density of the gas, remnants from the very early universe, began to pull matter together. Over time, these slightly denser regions accumulated more and more gas. Around 200 million to 400 million years after the Big Bang, the first stars began to form within these denser gas clouds. These first stars, known as population 3 stars, were massive, hot, and short-lived, composed almost entirely of hydrogen and helium. Their intense ultraviolet radiation began to reionize the neutral hydrogen gas in the universe, ending the Dark Ages and making the universe transparent to light once again. These first stars also began to produce heavier elements through nuclear fusion in their cores. When these massive stars exploded as supernovae, they scattered these newly formed heavier elements into space, enriching the cosmic gas. Over the next few billion years, gravity continued to pull together the gas and the newly formed stars, leading to the formation of the first galaxies. These early galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They merged and grew over time, forming larger and more complex structures. Galaxy clusters and superclusters, the largest structures in the universe, also began to form as gravity drew galaxies together into vast cosmic webs, interspersed with immense voids. Our own Milky Way galaxy, for example, is thought to have formed through a series of mergers of smaller galaxies over billions of years. The universe has continued to expand and cool since the Big Bang, and this expansion is still ongoing today. The Big Bang theory provides a comprehensive framework for understanding the universe's history, from its initial hot, dense state to the formation of all the structures we observe. It is a dynamic and evolving picture, constantly refined by new observations from powerful telescopes and advancements in theoretical physics. The Big Bang is not just a story of origin, it is a story of continuous transformation, from the simplest particles to the most complex cosmic structures, all driven by the relentless expansion of space itself. The idea that the universe is expanding is not a mere speculation. It is a conclusion drawn from concrete observational evidence. Two primary pillars support this understanding: the redshift of distant galaxies and the existence of the cosmic microwave background radiation. These phenomena provide compelling insights into the universe's dynamic nature and its origins in the Big Bang. The concept of redshift is fundamental to observing the universe's expansion. To understand redshift, it is helpful to first consider how light behaves. Light travels in waves, similar to sound waves or waves on water. The colour of visible light depends on its wavelength. For instance, blue light has a shorter wavelength than red light. When a source of waves moves relative to an observer, the perceived wavelength of the waves changes. This is known as the Doppler effect. A common example is the change in pitch of an ambulance siren as it approaches and then moves away from you. As the ambulance approaches, the sound waves are compressed, leading to a higher pitch. As it moves away, the sound waves are stretched, resulting in a lower pitch. The same principle applies to light. If a light source is moving towards an observer, the light waves are compressed, shifting towards the bluer end of the spectrum. This is called blue shift. Conversely, if a light source is moving away from an observer, the light waves are stretched, shifting towards the redder end of the spectrum. This is known as redshift. In astronomy, when astronomers observe the light from distant galaxies, they analyze its spectrum. A spectrum is like a barcode of light, showing specific lines that correspond to elements present in the light source, such as hydrogen or helium. These spectral lines appear at very precise wavelengths when observed in a laboratory. However, when observing light from distant galaxies, these familiar spectral lines are consistently found to be shifted towards the red end of the spectrum. This observed redshift indicates that these galaxies are moving away from us. The discovery of galactic redshift was a pivotal moment in cosmology. In the 1920s, American astronomer Edwin Hubble made systematic observations of galaxies. He measured their distances and their redshifts. His groundbreaking work, building on the earlier theoretical insights of Georges Lemaitre and the observational work of Vesto Slipher, revealed a profound relationship. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship is now known as Hubble's law. If a galaxy is twice as far away, its light is redshifted twice as much, meaning it appears to recede at twice the speed. This consistent pattern across vast cosmic distances is not what one would expect if galaxies were simply moving through a static, unchanging space. Instead, it strongly suggests that space itself is expanding, carrying the galaxies along with it. Every galaxy appears to be moving away from every other galaxy, not because they are all rushing away from a central point, but because the fabric of space between them is stretching. The second major piece of evidence for the Big Bang and an expanding universe is the cosmic microwave background radiation, often abbreviated as CMB. This radiation is a faint glow of microwaves that uniformly fills the entire sky. Its discovery was accidental but profoundly significant. In 1964, Arno Penzias and Robert Wilson, two engineers at Bell Labs, were working with a new antenna and kept detecting a persistent, annoying hiss of static that they could not eliminate. They tried everything, even cleaning pigeon droppings from the antenna, but the noise remained. It turned out they had stumbled upon the leftover radiation from the very early universe. The existence of such a background radiation had been predicted decades earlier by scientists working on the Big Bang theory. They theorized that the early universe, immediately after the Big Bang, was incredibly hot and dense, filled with a plasma of charged particles and photons. In this state, light could not travel freely because photons were constantly scattering off the free electrons. The universe was opaque, like a dense fog. As the universe expanded, it cooled. Approximately 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and helium nuclei to form neutral atoms. This event is called recombination. Once atoms formed, the electrons were no longer free to scatter photons, and the universe suddenly became transparent. The photons that had been trapped were now free to stream across space. These photons, released when the universe was only 380,000 years old, have been travelling ever since. As the universe has continued to expand over the past 13.8 billion years, the wavelengths of these photons have been stretched. This stretching has shifted their energy from visible light and infrared wavelengths to much longer microwave wavelengths. Therefore, the cosmic microwave background radiation is essentially the afterglow of the Big Bang, a fossil radiation from a time when the universe was a mere infant. Its temperature today is extremely cold, about 2.725 degrees above absolute zero, which is minus 270.425 degrees Celsius. The remarkable uniformity of the CMB across the entire sky indicates that the early universe was incredibly smooth and isotropic, meaning it looked the same in all directions. However, precise measurements by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have revealed tiny temperature fluctuations in the CMB. These minute variations, on the order of 1 part in 100,000, are incredibly important. They represent slight differences in the density of matter in the very early universe. These tiny density fluctuations acted as the seeds from which all the large-scale structures we see today, galaxies, galaxy clusters, and superclusters, eventually grew through gravitational attraction over billions of years. The pattern and scale of these fluctuations perfectly match the predictions of the Big Bang model, further solidifying its standing as the leading theory of cosmic origins. Together, the observed redshift of distant galaxies and the pervasive cosmic microwave background radiation provide overwhelming evidence for an expanding universe that originated from a hot, dense state. These observations are not isolated phenomena, but are consistent with each other and with the theoretical framework of the Big Bang, painting a coherent picture of our universe's dynamic and evolving nature. The concept of the universe expanding often leads to a fundamental question. What is it expanding into? This question arises from our everyday experience, where expansion usually means something growing larger within a pre-existing space. For instance, a balloon expands into the room, or a city expands into the surrounding countryside. However, cosmic expansion is fundamentally different and requires a shift in perspective. The universe is not expanding into anything. Rather, space itself is stretching and growing. To grasp this, it is essential to understand that the universe, in the context of cosmology, is defined as everything that exists. This includes all of space, all of time, all matter, and all energy. If the universe is everything, then there is no outside for it to expand into. The expansion is not like an object moving through a fixed, larger container. Instead, it is the container itself, the very fabric of space, that is stretching and becoming larger. Imagine drawing a grid on a rubber sheet. If you stretch the rubber sheet, the lines of the grid move farther apart. The grid itself is expanding, and there is no external space that it is moving into. The universe's expansion works in a similar, albeit three-dimensional way. Consider the galaxies within the universe. They are not flying through space away from a central point, like fragments from an explosion. If that were the case, we would expect to see a concentration of galaxies in one direction, and fewer in others, and distant galaxies would appear to slow down relative to us. Instead, what we observe is that every distant galaxy appears to be moving away from every other distant galaxy, and the farther away a galaxy is, the faster it appears to recede. This uniform recession in all directions is a key indicator that it is space itself that is expanding. The galaxies are largely stationary within their local regions of space, but the space between these regions is stretching, increasing the distances between them. Think of it this way. If you were an ant on the surface of an inflating balloon, and other ants were also on the balloon, you would see all the other ants moving away from you. The farther away an ant was, the faster it would appear to move away. This is not because the ants are crawling away from you, but because the surface of the balloon, the two-dimensional space they inhabit, is expanding. From the perspective of any ant on the surface, all other ants would appear to recede, and the effect would be greater for those ants that are farther away. The balloon's surface is finite but has no edge, and it is not expanding into anything external to its surface. Our three-dimensional universe behaves analogously, but in three spatial dimensions. The expansion of space means that the distances between unbound objects, such as galaxies that are not gravitationally bound into clusters, are increasing over time. Within gravitationally bound systems like our solar system, or even our Milky Way galaxy, the expansion of space is negligible. The gravitational forces holding these systems together are much stronger than the stretching effect of cosmic expansion on those scales. For example, Earth is not expanding, nor is the solar system growing larger due to cosmic expansion. The atoms that make up our bodies are not expanding. The expansion of space is significant only over vast intergalactic distances, where gravity is too weak to counteract the stretching of space. This stretching of space also affects light. When light travels across vast cosmic distances from a distant galaxy to our telescopes, the space through which it travels expands. As space expands, the wavelength of the light wave also stretches. This stretching of the light wave causes it to shift towards the red end of the electromagnetic spectrum, a phenomenon known as cosmological redshift. This is different from the Doppler effect redshift, which is caused by an object's motion through space. Cosmological redshift is caused by the expansion of space itself between the emitter and the observer. The more space that light has to travel through, the more it is stretched, and thus the greater the observed redshift. This is why more distant galaxies show greater redshifts, not necessarily because they are moving faster through space, but because there is more expanding space between them and us. The expansion of the universe is a continuous process. It is not like a one-time event that happened and then stopped. Space continues to stretch, and the distances between widely separated galaxies continue to grow. Current observations indicate that this expansion is not only ongoing, but is also accelerating, meaning the rate at which space is stretching is increasing over time. This acceleration is attributed to a mysterious force or energy called dark energy, which appears to be pushing space apart. Understanding that the universe is expanding into itself, or that space is stretching, is a crucial conceptual leap in modern cosmology. It moves away from the intuitive but incorrect idea of a universe expanding into a pre-existing void. Instead, it posits that space is an active, dynamic entity that is itself growing. This perspective is fundamental to the Big Bang model, explaining how a universe that began from an incredibly dense state could evolve into the vast, diffuse cosmos we observe today, without needing an external outside to accommodate its growth. The expansion of the universe is a concept that often challenges our everyday intuition. When we hear that the universe is expanding, our minds naturally picture something growing larger within a pre-existing empty space. However, this mental image is misleading. The universe is not expanding into anything. Instead, space itself is stretching. To help visualize this complex idea, scientists often use the analogy of a balloon. Imagine a deflated balloon. Now, draw several dots on its surface with a marker. These dots represent galaxies. It is important to remember that these dots are drawn on the surface of the balloon, not inside it or floating above it. The surface of the balloon represents the three-dimensional space of our universe. We, as observers, are confined to this surface. We cannot perceive anything off the surface, nor can we look down into the balloon's interior or up into the air around it. Our entire reality exists on this two-dimensional surface. Now, begin to inflate the balloon. As the balloon inflates, its rubber surface stretches. What happens to the dots you drew on it? They move farther and farther apart from each other. If you were an ant living on one of these dots, you would observe that all the other dots are moving away from you. Furthermore, the dots that are farther away from your position would appear to be moving away at a faster rate than the dots closer to you. This is a crucial point. Every dot on the surface would observe the same phenomenon, that all other dots are receding, and the recession speed increases with distance. No single dot is at the center of the expansion. The expansion is happening uniformly across the entire surface. This analogy helps clarify several key aspects of cosmic expansion. First, it illustrates that the galaxies, dots themselves, are not moving through space. Instead, the space between the galaxies, the rubber surface, is stretching, carrying the galaxies along with it. The dots are relatively stationary on the surface, but the surface itself is growing. Similarly, galaxies are largely stationary within their local gravitational groups, but the vast stretches of space between these groups are expanding. Second, the balloon analogy addresses the common misconception of expansion into an outside. The surface of the balloon is a two-dimensional space. When the balloon inflates, its surface expands. There is no outside for this two-dimensional surface to expand into in terms of its own dimensions. The surface simply becomes larger. While the balloon itself is inflating into a three-dimensional room, the analogy specifically focuses on the two-dimensional surface as representing our universe. Our three-dimensional universe expands in a similar way, but in its own three dimensions. There is no fourth spatial dimension for it to expand into. The expansion is intrinsic to space itself. Third, the analogy helps explain why more distant galaxies appear to recede faster. In the balloon analogy, a dot that is twice as far away from your ant dot will have twice as much stretching rubber between it and you. Therefore, as the balloon inflates, that farther dot will appear to move away from you at twice the speed of a closer dot. This directly mirrors Hubble's law, which states that the recession velocity of a galaxy is proportional to its distance from us. The observed redshift of light from distant galaxies is a direct consequence of this stretching of space, as the light waves themselves are stretched as they travel through the expanding cosmic fabric. It is important to acknowledge the limitations of the balloon analogy. No analogy is perfect, and the balloon analogy has several points where it differs from the reality of the universe. For instance, the surface of a balloon is finite and has a positive curvature like a sphere. The actual universe might be infinite, or it might be finite but flat, or even have a negative curvature. The balloon has a centre of expansion, the point from which it is inflated, but the universe has no central point of expansion. The expansion is uniform everywhere. Also, the balloon expands into a third dimension, but our universe is thought to expand within its own 3 dimensions, without needing an external higher dimension. Furthermore, the analogy does not account for the role of gravity, which pulls galaxies together, or dark energy, which causes the expansion to accelerate. Despite these limitations, the balloon analogy remains a powerful tool for conceptualizing the universe's expansion. It effectively conveys the idea that space itself is stretching, that galaxies are carried along by this expansion rather than moving through a static space, and that the expansion appears uniform from any point within the universe. It helps to overcome the intuitive but incorrect notion of a universe expanding into an empty void, instead guiding us towards the understanding that the universe is the totality of space, and its expansion is the growth of that very space. When we talk about the universe expanding, it is easy to imagine galaxies moving away from each other through a pre-existing, unchanging, empty void. However, this common mental image is not accurate according to modern scientific understanding. Instead, the universe's expansion involves the very fabric of space itself stretching and growing. Space is not merely a passive, empty stage where cosmic events unfold. It is an active and dynamic entity that can bend, warp, and expand. This concept is central to Albert Einstein's theory of general relativity, which revolutionized our understanding of gravity and the nature of space and time. In general relativity, space and time are not separate entities but are interwoven into a single 4-dimensional continuum called spacetime. Imagine this spacetime as a flexible fabric, much like a stretched rubber sheet. The presence of mass and energy causes this fabric to curve or warp. This curvature is what we perceive as gravity. For instance, the Earth orbits the Sun not because an invisible force is pulling it directly, but because the Sun's immense mass has created a significant dip or curvature in the spacetime fabric around it. The Earth, following the straightest possible path through this curved spacetime, appears to orbit the Sun. This analogy helps to visualize how matter influences space, making it a dynamic participant rather than a static background. The expansion of the universe is a direct consequence of this dynamic nature of space-time. It is not galaxies flying through static space, but rather the space between the galaxies that is stretching. Think back to the analogy of a balloon with dots drawn on its surface. As the balloon is inflated, the dots move farther apart from each other. The dots themselves are not moving across the surface of the balloon, rather the surface itself is expanding, carrying the dots along with it. In this analogy, the surface of the balloon represents the fabric of space, and the dots represent galaxies. The galaxies are relatively stationary within their local regions of space, but the space between these regions is continuously expanding, increasing the distances between them. This stretching of space affects everything within the universe, though its effects are only noticeable over very large cosmic distances. Within galaxies, or even within galaxy clusters, gravity is strong enough to counteract the expansion. For example, the Earth is not expanding, nor is the solar system, nor is the Milky Way galaxy. The gravitational pull within these structures holds them together. It is only when we look at the vast voids between galaxy clusters that the expansion of space becomes evident. The light from distant galaxies, for instance, is stretched as it travels through expanding space, causing its wavelength to lengthen and shift towards the red end of the spectrum. This phenomenon, known as cosmological redshift, is a key piece of evidence for the expanding universe. It is not a Doppler effect caused by galaxies moving through space, but rather a stretching of the light waves by the expanding space itself. The Big Bang theory describes that the universe began from an extremely hot and dense state, and has been expanding ever since. This expansion started from a point where all of space, time, matter, and energy were compressed. From that initial moment, space-time itself began to inflate and stretch. The early universe was incredibly hot and dense, a plasma of fundamental particles. As space-time expanded, it cooled, allowing these particles to combine and form atoms, then stars, and eventually galaxies. The expansion continues today, pushing galaxies farther apart from one another. This means that the universe is not expanding into some pre-existing empty void outside of itself, because there is no outside in this context. The universe is everything, including all of space. The expansion is the growth of space itself. Consider what this implies for the concept of nothing. If space itself is expanding, then the idea of an empty void into which it expands becomes problematic. If there were an outside void, that void would by definition be part of the universe, or it would imply a boundary. But the current understanding suggests that space is not contained within something larger. It is the container itself. The expansion is therefore an intrinsic property of the universe, a dynamic process of its own growth. This is a challenging concept because our everyday intuition is built on experiences within a fixed three-dimensional space. We're used to objects moving within space, not space itself changing. The stretching of the fabric of space also has implications for the future of the universe. The rate of this expansion is not constant. Observations have shown that the expansion is actually accelerating, meaning that the stretching of space is getting faster over time. This acceleration is attributed to a mysterious force called dark energy, which appears to be an intrinsic property of space itself, pushing it apart. If dark energy continues to dominate, the stretching of space will eventually cause galaxies to become so far apart that they will be beyond each other's observable horizons, effectively isolating them. Even within galaxies, the expansion would eventually overcome local gravitational forces, tearing apart stars, planets, and even atoms in a scenario known as the Big Rip, though this is one of several hypothetical ultimate fates for the universe. The question of whether the universe has an edge is one that often arises when contemplating its vastness and expansion. Our everyday experience teaches us that objects have boundaries and spaces have limits. A room has walls, a country has borders, and even the Earth has a surface that, while curved, is finite. It is natural then to imagine the universe similarly, as a vast balloon or bubble, with a clear boundary beyond which there is nothing. However, according to current cosmological understanding, the universe does not have a physical edge or a wall that one could reach. The concept of an edge implies a boundary where the universe stops and something else begins. If such an edge existed, it would raise immediate questions. What is beyond the edge? What is it made of? And what would happen if you tried to cross it? These questions lead to logical paradoxes within the framework of modern physics. The prevailing view is that the universe is either infinite in extent, meaning it goes on forever without end, or it is finite but unbounded. The latter concept is particularly challenging to grasp, but is crucial for understanding why there is no edge. Imagine the surface of a sphere, like the surface of the Earth. If you were an ant walking on the surface of a perfectly smooth sphere, you could walk in any direction for an indefinite amount of time without ever encountering an edge or a wall. You would never fall off, and you would never reach a point where the surface simply stopped. Yet, the surface of the sphere is finite. It has a measurable area. It does not have a center on its surface, and it does not have an edge. This is a two-dimensional analogy for a three-dimensional, or four-dimensional, including time, universe that is finite but unbounded. In this analogy, the three dimensions of space in our universe are like the two dimensions on the surface of the sphere. Just as there is no edge to the surface of the Earth, there is no edge to the universe. If you were to travel in a straight line through space, you would theoretically continue forever, perhaps even eventually returning to your starting point, if the universe is indeed finite and positively curved, much like travelling around the Earth eventually brings you back to where you started. However, the distances involved are so immense that such a journey would take far longer than the age of the universe. The absence of an edge also implies that there is no centre to the universe. In the balloon analogy for expansion, every point on the surface of the balloon sees every other point moving away from it. No single point is the centre of the expansion. Similarly, in our universe, every galaxy observes other distant galaxies receding from it, and no galaxy occupies a special central position. The expansion is happening everywhere simultaneously, affecting the space between all distant objects. The shape of the universe is a key factor in whether it is finite or infinite, and whether it has an effective edge. Cosmologists consider three main possibilities for the overall geometry of the universe. 1. A flat universe. In a flat universe, parallel lines would remain parallel forever. This is similar to a flat sheet of paper extending infinitely in all directions. If the universe is perfectly flat, it would likely be infinite in extent and therefore have no edge. 2. An open universe. An open universe has a negative curvature, like a saddle shape. In such a universe, parallel lines would eventually diverge. An open universe would also be infinite in extent and unbounded, meaning no edge. 3. A closed universe. A closed universe has a positive curvature, like the surface of a sphere. In this scenario, parallel lines would eventually converge and then diverge. A closed universe would be finite in volume but unbounded, meaning it has no edge, just like the surface of the Earth. Current observations, particularly those of the cosmic microwave background radiation, suggest that the universe is very close to being flat. This implies that it could be infinite in extent, or at least so vast that it appears effectively infinite within our observable limits. Even if it is truly finite and closed, its curvature is so slight that it would be incredibly large, far beyond what we can currently observe. It is important to distinguish between the edge of the entire universe and the edge of the observable universe. The observable universe is the portion of the universe from which light has had enough time to reach us since the Big Bang. This is a sphere centered on us, and its edge is simply the limit of what we can see, not a physical boundary of the universe itself. Galaxies exist beyond our observable universe. Their light simply hasn't reached us yet, or they are moving away from us so fast that their light will never reach us. The observable universe does have a boundary, but it is a boundary of information, not of physical space. The concept of a universe without an edge challenges our intuitive understanding, which is shaped by our experiences in a finite, bounded world. However, the mathematical frameworks of general relativity and the observational evidence from cosmology strongly support the idea that the universe is either infinitely large or finite but without boundaries. This means that if you could travel fast enough and long enough, you would never encounter a wall, a barrier, or a point where space simply ends. The universe is a continuous, interconnected entity, and its expansion is the stretching of its own fabric, not its movement into some external void. The absence of an edge is a profound implication of our modern understanding of the cosmos, suggesting a universe that is boundless in its possibilities, even if its total volume is not infinite. When we look up at the night sky, we're observing only a small fraction of the entire universe. The portion of the universe that is accessible to our observations is known as the observable universe. This concept is distinct from the universe as a whole, which may be much larger, or even infinite. The observable universe is essentially a giant sphere centered on Earth, representing the maximum distance from which light and other forms of information have had enough time to reach us since the Big Bang. The primary reason for the existence of an observable universe and its finite size is the finite speed of light. Light, while incredibly fast, does not travel instantaneously. It moves at a constant speed of approximately 299,792 kilometers per second in a vacuum. This means that when we look at a distant galaxy, we're not seeing it as it is right now, but as it was when the light left it. For example, if a galaxy is 1 million light-years away, the light we receive from it today began its journey 1 million years ago. We are in essence looking back in time. The second crucial factor is the finite age of the universe. The Big Bang occurred approximately 13.8 billion years ago. Therefore, the oldest light we can possibly detect is light that has been travelling for 13.8 billion years. One might initially think that this means the observable universe extends for 13.8 billion light-years in every direction. However, this is not the case because the universe has been expanding throughout this time. As light travels towards us, the space it is travelling through is also stretching. This stretching effect means that the original location of the light source, which was 13.8 billion light-years away when the light was emitted, is now much farther away. Due to this ongoing expansion, the current estimated radius of the observable universe is about 46.5 billion light-years. This means that the light we are receiving today from the most distant observable objects started its journey 13.8 billion years ago, but the objects themselves are now 46.5 billion light-years away from us because of the expansion of space during that time. It is a common misconception that the observable universe is only 13.8 billion light-years in radius. The larger number accounts for the expansion that has occurred since the light left its source. The edge of our observable universe is not a physical barrier or a wall in space. Instead, it is a boundary of information. Beyond this boundary, there are galaxies and other cosmic structures that exist, but their light has not yet had enough time to reach us. It's like standing in a vast, foggy field. You can only see as far as the fog allows, but you know there's more field beyond the visible limit. As time progresses, and light from increasingly distant regions has more time to travel, our observable universe slowly expands. However, due to the accelerating expansion of the universe driven by dark energy, some very distant galaxies are moving away from us so quickly that their light may never reach us, even given infinite time. The most distant edge of our observable universe in terms of time is the cosmic microwave background radiation. This faint glow of radiation fills the entire sky and is the oldest light we can detect. It originated about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine and form neutral atoms. Before this time, the universe was an opaque plasma, and light could not travel freely through it. The cosmic microwave background radiation is essentially a snapshot of the universe when it was very young and hot, and it forms a spherical surface of last scattering around us, representing the earliest moment from which we can receive direct light. It is important to understand that the observable universe is centered on us because we are the observers. An observer in a galaxy far, far away would have their own observable universe, also a sphere centered on them. Their observable universe would overlap with ours, but it would also contain regions that are currently unobservable to us, and vice versa. This concept highlights that the observable universe is a personal horizon, not a universal boundary. The existence of an observable universe means that there are vast regions of the universe that are currently beyond our direct knowledge. These regions contain galaxies, stars, and planets, just like those in our observable part. They are governed by the same laws of physics and are part of the same continuous cosmic fabric. We simply cannot see them yet, or perhaps ever, depending on the future dynamics of the universe's expansion. This limitation does not mean that the universe itself is finite or has an end. It simply means that our ability to gather information about it is constrained by the speed of light and the universe's age and expansion. The study of the observable universe allows cosmologists to infer properties about the universe as a whole. By observing the distribution of galaxies, the cosmic microwave background, and the rate of expansion within our observable sphere, scientists can develop models that describe the entire cosmos. While we may never see the entire universe if it is infinite, the observable universe provides a rich laboratory for understanding the fundamental principles that govern all of existence. It is a window into the past and a guide to the possible future of the cosmos, constantly revealing new insights as our observational capabilities improve. The universe is vast and our ability to observe it is limited. We often speak of the observable universe, which is the portion of the cosmos from which light has had enough time to reach us since the Big Bang. This boundary is not a physical wall or an edge to the universe itself, but rather a horizon defined by the speed of light and the age of the universe. Beyond this horizon lie regions of the universe that are currently beyond our view. These unseen parts exist, but their light has not yet had sufficient time to travel across the immense cosmic distances to reach our telescopes, or they are receding from us so rapidly due to the expansion of space that their light will never reach us. To understand why parts of the universe are beyond our view, consider the finite speed of light. Light travels at a constant speed of approximately 299,000 792 kilometers per second in a vacuum. While incredibly fast, this speed is not infinite. The universe began about 13.8 billion years ago with the Big Bang. This means that the oldest light we can possibly detect has been travelling for nearly 13.8 billion years. Any object or event that is so far away that its light would take longer than 13.8 billion years to reach us is, by definition, beyond our observable horizon. It is important to note that the observable universe is much larger than 13.8 billion light-years in radius. This is because the universe has been expanding during the time the light has been travelling. A galaxy whose light we see today, which left that galaxy 13.8 billion years ago, is now much farther away due to the expansion of space. Calculations indicate that the current distance to the edge of our observable universe is approximately 46.5 billion light-years in every direction. This means that the diameter of the observable universe is roughly 93 billion light-years. The expansion of the universe is a key factor in defining what we can and cannot see. Space itself is stretching, carrying galaxies along with it. This is not like galaxies moving through a static space, but rather the fabric of space growing between them. The farther away a galaxy is, the faster it appears to be receding from us due to this expansion. This phenomenon is known as Hubble's law, named after astronomer Edwin Hubble, who observed in the 1920s that distant galaxies are moving away from us, and the speed of their recession is proportional to their distance. The rate of this expansion is quantified by the Hubble constant. A more profound aspect of this expansion is the accelerated expansion of the universe, discovered in the late 1990s. Observations of distant supernovae revealed that the expansion is not slowing down due to gravity, as once expected, but is actually speeding up. This acceleration is attributed to a mysterious force called dark energy, which acts as a repulsive force, pushing space apart. This accelerated expansion has significant implications for what we can see. Some galaxies are receding from us at speeds greater than the speed of light, not because they are physically moving through space faster than light, but because the space between us and them is expanding so rapidly. For these galaxies, their light, even if emitted towards us, will never reach us because the intervening space expands faster than the light can travel. This creates a cosmic horizon beyond which communication is impossible, even in principle. Therefore, the regions beyond our view are not just those whose light hasn't reached us yet due to time constraints, but also those whose light never will reach us due to the accelerating expansion. As time goes on, more and more distant galaxies will cross this event horizon and become permanently unobservable. This means that our observable universe, while expanding, is also becoming increasingly isolated from the most distant parts of the cosmos. Galaxies that are currently visible to us will eventually recede beyond this horizon, their light redshifted beyond detectability, or simply unable to bridge the ever-widening gap of expanding space. The existence of these unseen regions implies that the universe is likely much, much larger than what we can observe. Our observable universe is merely a cosmic bubble centered on Earth, defined by the limits of light travel and expansion. Every point in the universe has its own observable universe, and these observable universes overlap. An observer in a galaxy billions of light-years away would have their own observable universe, which would include many galaxies that are currently beyond our view and exclude many that are within our view. This illustrates that the edge of our observable universe is not a universal boundary, but a personal horizon. The question of what lies beyond our view also touches upon the possible overall size and topology of the universe. Current cosmological models suggest that the universe could be infinite in extent, or it could be finite but unbounded, like the surface of a sphere or a torus, where there is no edge, but it still has a finite volume. If the universe is infinite, then there are infinitely many galaxies and structures beyond our observable horizon. If it is finite but unbounded, then the universe might eventually curve back on itself, but the distances involved would be so immense that we would never reach an edge or loop back to our starting point within our lifetime, or even the lifetime of the universe. In either case, the observable universe is just a fraction of the total cosmos. Understanding the parts of the universe beyond our view is crucial for a complete cosmological picture. It reminds us that our current knowledge is based on observations from a limited perspective. While we can infer the existence and properties of these unseen regions through theoretical models and the consistency of our cosmological framework, they remain fundamentally inaccessible to direct observation. The light from these regions may have been emitted, but the relentless expansion of space acts as a cosmic veil, preventing those ancient photons from ever reaching our detectors. This concept underscores the dynamic nature of spacetime and the profound implications of an expanding and accelerating universe. The concept of nothing is deceptively simple, yet profoundly complex, especially when discussed in the context of the universe's origin and expansion. Philosophically and scientifically, nothing can mean different things, and distinguishing between these meanings is crucial for understanding the universe. Is nothing merely the absence of something, or is it a state of absolute non-existence? One common understanding of nothing is simply empty space, a vacuum. In classical physics, a vacuum is a region devoid of matter and energy. If you were to remove all air from a container, you would create a vacuum. However, even this classical vacuum is not truly nothing in the absolute sense. It still possesses properties like volume, shape, and the ability to be influenced by gravitational fields. Light can travel through it, and it can contain virtual particles that briefly pop into and out of existence, as quantum mechanics describes. Therefore, even what we commonly perceive as empty space is not an absolute void. It is a stage upon which physical phenomena can occur, rather than the complete absence of everything. Another interpretation of nothing is the absence of matter and energy. This is a step closer to a complete void. If we could somehow remove all particles, all radiation, and all forms of energy from a region, would that be nothing? Even then, the space and time within that region would still exist. The dimensions of length, width, height, and the progression of moments would still be present. This kind of nothing is what science fiction often depicts as the vast, cold emptiness between galaxies, a space largely devoid of ordinary matter, but still very much a part of the universe's fabric. It is a state of extreme emptiness, but not absolute non-existence. The most profound and challenging idea of nothing is the absolute absence of everything. This means no matter, no energy, no space, and no time. It is a state where there are no dimensions, no physical laws, and no potential for anything to exist or happen. This concept is incredibly difficult for the human mind to grasp, because our entire experience is rooted in a universe that has space, time, matter, and energy. We cannot truly imagine a state where these fundamental components of reality are entirely absent. When we try to picture it, we often default to imagining an empty black void, but even that implies the existence of space and perhaps a backdrop of blackness. True absolute nothingness would lack even these qualities. The question of what was before the Big Bang often implicitly invokes this idea of absolute nothingness. If the Big Bang marked the beginning of space and time, then asking what existed before it becomes problematic, as the concept of before relies on the existence of time. In this view, there was no before in the temporal sense because time itself began with the universe. Therefore, the universe did not emerge from a pre-existing empty space, but rather space and time themselves emerged. This means the universe did not expand into something, because there was no something for it to expand into. The expansion is the creation and stretching of space itself. Consider the analogy of a balloon inflating. If you draw dots on the surface of a deflated balloon and then inflate it, the dots move farther apart. The surface of the balloon is analogous to space. The dots are analogous to galaxies. As the balloon inflates, the surface itself expands. There is no outside for the surface of the balloon to expand into. The expansion is intrinsic to the surface. If you ask what is outside the balloon's surface, you're referring to the three-dimensional air around it. But for the universe, there is no higher dimension for it to expand into. The expansion is the stretching of its own fabric. If the universe is finite but unbounded like the surface of a sphere, then there is no edge and therefore no outside to expand into. The expansion is simply the increase in the sphere's radius. The idea of nothing also plays a role in discussions about the origin of the universe from a quantum perspective. Some theories propose that the universe could have emerged from a state of quantum nothingness, or a false vacuum. This is not absolute nothingness, but a state where the laws of quantum mechanics still apply, and where fluctuations could potentially lead to the creation of space, time, and energy. This is a highly speculative area of theoretical physics, but it suggests that nothing, in the quantum sense, is far from inert. The challenge of conceiving nothing highlights the limitations of human intuition when dealing with cosmological scales and fundamental origins. Our everyday experiences are confined to a universe that is full of something. To imagine a state utterly devoid of all attributes, including the very dimensions that define existence, requires a leap beyond our conventional understanding. When cosmologists say the universe is expanding into nothing, they typically mean that it is expanding into the absence of pre-existing space. The space itself is being created and stretched. It is not filling a void that was already there. The nothing is simply the ongoing absence of anything outside the universe's own self-contained and expanding reality. This distinction is crucial for avoiding misconceptions about the Big Bang and the nature of cosmic expansion. When we talk about nothing in the context of empty space, our everyday intuition suggests a complete void, an absence of everything. However, modern physics, particularly quantum mechanics, presents a radically different and counterintuitive picture of what seemingly empty space actually is. Far from being inert or truly empty, the vacuum of space is a bustling arena of activity, teeming with energy and fleeting particles. This concept is known as quantum nothingness, and it suggests that even the most desolate reaches of the universe are fundamentally alive with quantum phenomena. At the heart of quantum nothingness lies the Heisenberg uncertainty principle, a fundamental concept in quantum mechanics, formulated by Werner Heisenberg in the 1920s. This principle states that certain pairs of physical properties, like a particle's position and momentum, or its energy and the time over which that energy is measured, cannot both be known with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. Applied to energy and time, this means that for very short periods, the energy of a system can fluctuate. This allows for temporary violations of energy conservation, as long as these borrowed energies are paid back within the allowed time frame. This energy-time uncertainty leads directly to the phenomenon of quantum fluctuations. Even in a perfect vacuum, where there are no particles or fields in the classical sense, there are constant spontaneous fluctuations in energy. These fluctuations are not random noise in a pre-existing medium. They are an inherent property of the quantum vacuum itself. Imagine the vacuum not as a still, calm ocean, but as a turbulent, frothing sea where waves are constantly appearing and disappearing. These waves are manifestations of quantum fluctuations. One of the most striking consequences of quantum fluctuations is the existence of virtual particles. These are particles that briefly pop into existence from the vacuum and then almost immediately disappear back into it. They are called virtual because they cannot be directly observed or measured in the same way as real particles. They exist for such incredibly short durations and over such tiny distances that they fall within the limits allowed by the energy-time uncertainty principle. For example, an electron and its antimatter counterpart, a positron, might spontaneously appear out of the vacuum, exist for an infinitesimal moment, and then annihilate each other, returning their borrowed energy to the vacuum. This process is happening continuously, everywhere, all the time, even in the deepest, emptiest regions of space. These virtual particles are not merely theoretical curiosities, their effects have been experimentally verified. One of the most famous pieces of evidence is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and later confirmed by experiments. The Casimir effect describes a small attractive force that arises between two uncharged parallel conducting plates placed very close together in a vacuum. This force occurs because the presence of the plates restricts the types of virtual particles that can exist in the space between them, leading to an imbalance of quantum fluctuations inside and outside the plates. The pressure from the greater number of virtual particles outside the plates pushes them together. This effect demonstrates that the vacuum is not empty, but has a measurable energy density due to these quantum fluctuations. Another concept related to quantum nothingness is zero-point energy. According to quantum mechanics, even at absolute zero temperature, the lowest possible temperature, where all classical motion ceases, particles still possess a minimum amount of energy. This is because if they had absolutely no energy and were perfectly still, their position and momentum would be known with perfect certainty, which would violate the uncertainty principle. This inherent, irreducible energy of quantum systems extends to the vacuum itself. The quantum vacuum possesses a non-zero energy, often referred to as zero-point energy. This vacuum energy is a pervasive property of spacetime, permeating every cubic centimetre of the universe. The implications of quantum nothingness are profound. It means that the empty space between galaxies, or even within atoms, is not truly empty. Instead, it is a dynamic, energetic medium. This understanding challenges our classical view of a passive, inert vacuum. It suggests that the vacuum is a rich source of potential, capable of generating particles and influencing physical phenomena. This concept also has significant connections to cosmology. Some theories propose that the initial state of the universe before the Big Bang might have been a false vacuum, or a state dominated by quantum fluctuations. The immense energy density of the vacuum, as described by quantum field theory, is also a candidate for dark energy, the mysterious force causing the accelerated expansion of the universe. If the vacuum itself has an inherent energy, this energy could be responsible for pushing space apart. However, the theoretical value for the vacuum energy predicted by quantum mechanics is astronomically larger than the observed amount of dark energy, leading to one of the biggest unsolved problems in physics, known as the cosmological constant problem. This discrepancy suggests that our understanding of quantum nothingness and vacuum energy is still incomplete. Our everyday experience of the world is deeply rooted in three spatial dimensions: length, width, and height. We move forward and backward, left and right, up and down. These three directions allow us to pinpoint any location in space. To describe events, we also add a fourth dimension: time. We say something happened at a certain place, defined by its three spatial coordinates, at a specific moment in time. This four-dimensional framework of space and time, often referred to as spacetime, forms the basis of our understanding of the universe as described by Albert Einstein's theory of general relativity. However, modern physics, particularly theories attempting to unify all fundamental forces, suggest that our universe might possess more than these familiar four dimensions. These additional dimensions, if they exist, are not immediately obvious to us, leading to the concept of hidden or compactified dimensions. The idea of extra dimensions arises primarily from attempts to reconcile two major pillars of modern physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels. These two theories are incredibly successful in their respective domains, but they are fundamentally incompatible when applied to extreme conditions, such as the very early universe or inside black holes. String theory and its more comprehensive extension, M theory, are leading candidates for a theory of everything that could unify all forces, including gravity, with quantum mechanics. A central feature of these theories is that they require the existence of extra spatial dimensions beyond the three we perceive. In string theory, fundamental particles are not point-like objects, but rather tiny, one-dimensional vibrating strings. The different ways these strings vibrate correspond to different types of particles. For string theory to be mathematically consistent, it requires a universe with more than three spatial dimensions. The most common versions of string theory propose 10 spatial dimensions, and one time dimension, making a total of 11 dimensions in spacetime. Other variations might suggest 10 dimensions in total. The question then arises, if these extra dimensions exist, why do we not experience them? The most widely accepted explanation for the unobservability of these extra dimensions is that they are compactified, or curled up into incredibly small sizes. Imagine a garden hose viewed from a great distance. From afar, it appears to be a one-dimensional line. However, if you get closer, you can see that it has a second dimension, a small circular circumference around the hose. An ant walking on the hose can move along its length, the large dimension, and also around its circumference, the small curled-up dimension. Similarly, the extra dimensions are thought to be curled up so tightly, perhaps to a size smaller than a trillionth of a centimetre, the Planck length, that they are imperceptible to our current instruments, and even to the fundamental particles that make up our bodies. We are effectively stuck on the three large spatial dimensions, much like the ant is largely confined to the surface of the hose. These compactified dimensions are not empty. They are thought to have complex shapes, often described as Calabi-Yau manifolds, which are intricate geometric spaces. The specific way these extra dimensions are curled up could determine the fundamental properties of our universe, such as the masses of particles and the strengths of the fundamental forces. Different ways of compactifying these dimensions could lead to different sets of physical laws, potentially explaining why our universe has the specific properties it does. This concept is sometimes invoked in multiverse theories, where different universes might arise from different compactifications of these extra dimensions. Another way extra dimensions might manifest is if our familiar three-dimensional universe is actually a brane, a shortened term for membrane, floating within a higher dimensional space, often called the bulk. In this brane world scenario, matter and the electromagnetic force, which governs light, might be confined to our three-dimensional brane, meaning they cannot easily move into or interact with the extra dimensions. However, gravity, being a property of spacetime itself, might be able to propagate into these extra dimensions. This could explain why gravity appears to be so much weaker than the other fundamental forces. If gravity leaks into the bulk, its strength would be diluted in our three dimensions, making it seem weaker compared to the strong nuclear force, weak nuclear force, and electromagnetism. This idea has spurred experimental efforts to look for deviations from Newton's law of gravity at very small distances, which could be a sign of extra dimensions. The existence of extra dimensions could have profound implications for our understanding of the universe's structure and expansion. In the very early universe, during the Big Bang, these extra dimensions might have played a more significant role. Some theories suggest that cosmic inflation, the rapid expansion of the early universe, might have been driven by the dynamics of these extra dimensions. As the universe expanded and cooled, these extra dimensions could have compactified or stabilized, leaving only the three large spatial dimensions we observe today. The way they compactified could have influenced the initial conditions of our universe, affecting the distribution of matter and energy that eventually led to the formation of galaxies and large-scale structures. Furthermore, if our universe is a brane in a higher dimensional bulk, it opens up the possibility of interactions with other branes or other universes existing in the same bulk. Collisions between branes, for example, have been proposed as an alternative to the Big Bang, where the universe's beginning is not a singular point but a collision event in higher dimensions. This would mean that the nothing outside our universe might not be truly empty, but rather a higher dimensional space where other cosmic structures or even other universes exist, though they remain invisible to us because their matter and light are confined to their own branes. The concept of extra dimensions remains highly theoretical and has not yet been directly confirmed by experimental evidence. However, it provides a powerful mathematical framework for addressing some of the most challenging questions in physics, such as the unification of forces and the nature of gravity. Scientists continue to explore these ideas through theoretical calculations and by designing experiments that could potentially reveal subtle effects of these hidden dimensions, pushing the boundaries of our understanding of reality beyond our familiar four dimensions. When scientists discuss the shape of the universe, they are not referring to its appearance like a ball or a box in some larger space. Instead, they are talking about the overall curvature of space itself on the largest possible scales. This curvature is determined by the total amount of matter and energy present in the universe, which influences how spacetime is warped according to Albert Einstein's theory of general relativity. There are three main possibilities for the universe's global shape. It could be flat, open, or closed. Each shape has distinct geometric properties and implies a different ultimate fate for the universe. To understand these concepts, it is helpful to use a two-dimensional analogy. Imagine a two-dimensional surface, like the surface of a balloon, a saddle, or a flat sheet of paper. While these are only two-dimensional examples, they help us visualize the curvature that applies to our three-dimensional space. A closed universe has positive curvature, much like the surface of a sphere. If you were to draw two parallel lines on the surface of a sphere and extend them indefinitely, they would eventually converge and intersect. Similarly, if you draw a triangle on the surface of a sphere, the sum of its internal angles would be greater than 180 degrees. In a three-dimensional closed universe, this means that if you travelled in a straight line for a very long distance, you would eventually return to your starting point, much like circumnavigating the Earth. A closed universe is finite in size, meaning it has a limited volume, but it is unbounded, meaning it has no edge or boundary. This is similar to the surface of a sphere, which has a finite area but no edge. The density of matter and energy in a closed universe is greater than a critical value. If the universe is closed, the expansion, which began with the Big Bang, would eventually slow down, stop, and then reverse, leading to a big crunch, where the universe collapses back in on itself, potentially returning to a hot, dense state similar to its beginning. An open universe has negative curvature, resembling the surface of a saddle. On a saddle-shaped surface, two parallel lines, if extended, would diverge and move farther apart. If you draw a triangle on a saddle, the sum of its internal angles would be less than 180 degrees. In a three-dimensional open universe, space would be infinite in extent. You could travel in a straight line forever and never return to your starting point. The density of matter and energy in an open universe is less than the critical value. If the universe is open, its expansion would continue forever, never stopping. The galaxies would continue to move farther and farther apart, and the universe would become increasingly cold, dark, and empty, leading to a big freeze or heat death. If dark energy continues to accelerate the expansion, it could even lead to a big rip, where all structures from galaxies to atoms are eventually torn apart. A flat universe has zero curvature, analogous to a flat sheet of paper. In flat geometry, parallel lines remain parallel forever, never converging or diverging. A triangle drawn on a flat surface has internal angles that sum up to exactly 180 degrees. In a three-dimensional flat universe, space would also be infinite in extent. The density of matter and energy in a flat universe is exactly equal to the critical density. If the universe is flat, its expansion would continue forever, but it would slow down over time, approaching a speed of zero only after an infinite amount of time. Like an open universe, a flat universe would also lead to a big freeze as it expands and cools indefinitely, though the rate of expansion would be different. Scientists determine the shape of the universe by measuring its total energy density. This density includes not only ordinary matter, like stars, planets, and gas, but also dark matter and dark energy. The critical density is a specific value of energy density at which the universe would be flat. If the observed density is greater than this critical value, the universe is closed. If it is less, the universe is open. If it is exactly equal, the universe is flat. One of the most powerful tools for measuring the universe's curvature is the cosmic microwave background, CMB, radiation. The CMB is the faint afterglow of the Big Bang, a relic of the universe when it was only about 380,000 years old and first became transparent to light. The CMB is not perfectly uniform. It has tiny temperature fluctuations, or hot spots, and cold spots. The size of these fluctuations as observed from Earth depends on the curvature of space. If the universe were closed, these hotspots would appear larger than they actually are. If it were open, they would appear smaller. If it were flat, their apparent size would match their actual size. Satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have meticulously mapped the CMB with unprecedented precision. The data from these missions strongly indicate that the universe is remarkably flat. The measurements show that the total energy density of the universe is very close to the critical density. This finding suggests that our universe is either perfectly flat or so close to flat that any curvature is imperceptible over the vast distances we can observe. The discovery of dark energy in the late 20th century, which causes the universe's expansion to accelerate, further complicates the picture, but also helps to explain the flatness. Dark energy contributes significantly to the total energy density of the universe, making up about 68% of it. Dark matter accounts for about 27%, and ordinary matter only about 5%. The combination of these components adds up to nearly 100% of the critical density, supporting the flat universe model. The implications of a flat universe are profound. It suggests that the universe is infinite in spatial extent, and its expansion will continue forever, albeit at an accelerating rate due to dark energy. This leads to the Big Freeze scenario, where galaxies will eventually become so distant from each other that they will be beyond each other's observable horizons, and the universe will become cold, dark, and dilute as stars burn out and matter decays over unimaginable timescales. While the universe's shape is now largely understood to be flat, the precise nature of dark energy and its long-term effects on this expansion remain active areas of research. When we look out into the cosmos, we see billions of galaxies, each containing billions of stars, along with vast clouds of gas and dust. All of this visible matter, which emits or reflects light, makes up only a small fraction of the universe's total mass and energy. Scientists have accumulated overwhelming evidence that there is a significant amount of missing mass in the universe, a substance that does not interact with light or any other form of electromagnetic radiation. This mysterious, invisible substance is called dark matter. It is dark because it does not emit, absorb, or reflect light, making it impossible to observe directly with telescopes. However, its presence is inferred through its gravitational effects on visible matter. The concept of dark matter first emerged in the 1930s, when astronomer Fritz Zwicky observed the Coma cluster of galaxies. He noticed that the galaxies within the cluster were moving much faster than expected based on the amount of visible matter. For the cluster to remain gravitationally bound and not fly apart, it required far more mass than could be accounted for by the stars and gas that were observed. Zwicky concluded that there must be some unseen non-luminous matter, providing the extra gravitational pull. His findings were largely overlooked for decades. The evidence for dark matter became much stronger in the 1970s, primarily through the work of astronomer Vera Rubin and her colleagues. They studied the rotation curves of spiral galaxies. A rotation curve plots the orbital speed of stars or gas at different distances from the galactic center. Based on the visible matter in a galaxy, one would expect stars farther from the center to orbit slower, similar to how planets farther from the Sun orbit slower. However, Rubin and others consistently found that stars at the outer edges of galaxies were orbiting just as fast, or even faster, than stars closer to the center. This observation implied that there must be a large halo of invisible mass surrounding galaxies, extending far beyond the visible disk, providing the extra gravitational force needed to keep the outer stars in orbit. This invisible mass is dark matter. Further evidence for dark matter comes from observations of galaxy clusters. Like the Coma cluster, many other galaxy clusters show similar discrepancies between their visible mass and their gravitational effects. Three key pieces of evidence from galaxy clusters support the existence of dark matter. First, the speeds of galaxies within clusters are too high. If only visible matter were present, the clusters would quickly disperse. Second, observations of hot gas in galaxy clusters, which emits X-rays, also indicate the presence of more mass than can be seen. The temperature and distribution of this gas suggest it is held in place by a much stronger gravitational field than visible matter alone could provide. Third, gravitational lensing provides compelling evidence. Gravitational lensing occurs when the massive gravitational field of a galaxy or galaxy cluster bends the light from more distant objects, distorting their images. By analysing the degree of distortion, astronomers can map the distribution of mass in the foreground cluster. These lensing maps consistently show that the total mass, including dark matter, is much greater and more extended than the visible matter. A famous example is the Bullet cluster, where two galaxy clusters collided. The ordinary matter, gas, collided and slowed down, but the dark matter passed right through each other, indicating that dark matter does not interact electromagnetically or strongly with itself or ordinary matter. The cosmic microwave background, CMB radiation, also provides crucial evidence for dark matter. The tiny temperature fluctuations in the CMB, which are the seeds for the large-scale structures we see today, are consistent with a universe containing a significant amount of dark matter. Without dark matter, ordinary matter alone would not have had enough time to clump together under gravity to form the galaxies and clusters we observe within the universe's 13.8 billion-year age. Dark matter provided the gravitational scaffolding upon which ordinary matter could accumulate. The properties of dark matter are inferred from these observations. It is non-baryonic, meaning it is not made of protons, neutrons, or electrons, which constitute ordinary matter. This is supported by Big Bang nucleosynthesis, which accurately predicts the abundance of light elements, hydrogen, helium, lithium, based on the amount of ordinary matter. If dark matter were ordinary matter, these predictions would be incorrect. Dark matter also does not interact with light, meaning it does not absorb, emit, or reflect photons, hence its darkness. It interacts primarily through gravity. It is also thought to be cold, meaning it moves relatively slowly, which is necessary for it to clump together and form the structures observed in the universe. What dark matter actually is remains one of the biggest mysteries in modern physics. Scientists have proposed several candidates for dark matter particles, but none have been definitively detected. The leading candidate is a class of hypothetical particles called weakly interacting massive particles, or WIMPs. These particles would be massive, but they would interact very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. Billions of WIMPs could be passing through Earth and our bodies every second without us noticing. Other proposed candidates include axions, which are very light hypothetical particles, and sterile neutrinos, which are a type of neutrino that interacts even more weakly than the known neutrinos. Scientists are actively pursuing various experimental approaches to directly detect dark matter. Underground laboratories, shielded from cosmic rays, house detectors designed to observe the rare occasions when a WIMP might collide with an atomic nucleus in the detector material, producing a tiny recoil. Large particle accelerators, like the Large Hadron Collider, LHC, at CERN, are also searching for signs of dark matter particles being produced in high-energy collisions. Additionally, astronomers are looking for indirect evidence of dark matter, such as gamma rays or other particles produced when dark matter particles might annihilate or decay in dense regions of space, like the galactic center. Despite decades of intense research, dark matter has not yet been directly detected. However, the cumulative astrophysical evidence for its existence is so strong that it is considered a fundamental component of the universe. Dark matter is estimated to make up about 27% of the total mass-energy content of the universe, while ordinary matter accounts for only about 5%. The remaining 68% is dark energy. Understanding the nature of dark matter is crucial for a complete picture of the universe's composition, its evolution, and its ultimate fate. It represents a significant frontier in our quest to comprehend the fundamental constituents of reality. Dark energy represents one of the greatest mysteries in modern cosmology, the study of the universe as a whole. It is a peculiar, invisible component of our universe that scientists believe is responsible for a surprising phenomenon, the accelerating expansion of space. Unlike gravity, which pulls things together, dark energy acts like a repulsive force, pushing the fabric of the universe apart, causing galaxies to recede from one another at an ever-increasing speed. To understand dark energy, it is helpful to first distinguish it from dark matter, another enigmatic component of the cosmos. Dark matter is a type of matter that does not interact with light or other forms of electromagnetic radiation. We cannot see it, detect it through light, or feel it. Its presence is inferred only through its gravitational effects on visible matter. For example, observations of how galaxies rotate and how galaxy clusters hold together suggest there is far more mass present than can be accounted for by the visible stars and gas. This unseen mass is what we call dark matter. Dark matter exerts a gravitational pull, similar to ordinary matter, and thus contributes to slowing down the expansion of the universe. It clumps together, forming invisible halos around galaxies and large-scale structures, influencing their formation and dynamics. Dark energy, however, behaves in an entirely different manner. Instead of pulling things together, it pushes them apart. It is not something that clumps. Rather, it appears to be uniformly distributed throughout space, almost like an intrinsic property of space itself. As space expands, more of this dark energy comes into existence, or its effect becomes more pronounced, leading to an increasing push. This constant, pervasive, repulsive force is what overcomes the gravitational attraction of matter and dark matter over vast cosmic distances, causing the universe's expansion to accelerate. The standard model of cosmology, known as the lambda CDM model, suggests that dark energy makes up the largest portion of the universe's total mass energy content. According to current estimations, approximately 68% of the universe is composed of dark energy. Dark matter accounts for about 27%, and all the ordinary matter that makes up stars, planets, and everything we can see and touch amounts to only about 5%. This means that nearly 95% of our universe is made of components we cannot directly observe or fully understand. The dominance of dark energy implies that it is the primary driver of the universe's large-scale behavior today. The dark in dark energy refers to its invisible nature. Like dark matter, it does not emit, absorb, or reflect light, making it undetectable by conventional astronomical instruments. Its existence is inferred solely from its gravitational effect on the overall expansion of the universe. If there were no dark energy, the universe's expansion would be continuously slowing down due to the mutual gravitational pull of all matter and dark matter within it. The surprising discovery of accelerating expansion, which we will discuss in more detail, necessitated the introduction of a new component, dark energy, to explain this unexpected behavior. The effect of dark energy becomes noticeable primarily on very large cosmic scales. Within galaxies, the gravitational pull of stars and dark matter is strong enough to hold them together, preventing them from being torn apart by dark energy. Similarly, galaxy clusters remain bound. However, when we consider distances between galaxy clusters, where the average density of matter is much lower and gravitational forces are weaker, the constant, pervasive push of dark energy begins to dominate. It ensures that these vast regions of space continue to expand, and do so at an increasing rate. One of the leading theoretical explanations for dark energy is that it is linked to the cosmological constant, a concept first introduced by Albert Einstein in 1917. Initially, Einstein added this term to his equations of general relativity to allow for a static universe, as that was the prevailing view at the time. After Edwin Hubble's discovery of the universe's expansion, Einstein reportedly called the cosmological constant his biggest blunder. However, it has been resurrected in modern cosmology to explain accelerated expansion. In this interpretation, the cosmological constant represents the energy inherent to empty space itself, often referred to as vacuum energy. As space expands, more empty space is created, and with it, more of this vacuum energy, leading to a constant energy density that drives the acceleration. The precise nature of dark energy remains an unsolved puzzle. It is not like ordinary energy that can be converted from one form to another, nor is it a form of matter. It acts more like a constant negative pressure, or an intrinsic property of space that uniformly exerts a repulsive force. This property is what differentiates it from everything else we know in physics. Understanding dark energy is crucial for comprehending the past, present, and future evolution of the universe. It challenges our fundamental understanding of gravity and the very fabric of spacetime, making it a frontier of scientific inquiry and a target for numerous ongoing cosmological experiments and observations. The mystery of dark energy continues to drive research as scientists strive to uncover its true identity and integrate it into a more complete picture of the cosmos. For many decades, astronomers largely assumed that the expansion of the universe, initiated by the Big Bang, must be slowing down. This was a logical assumption based on the understanding that gravity, the attractive force between all matter, would act to pull everything back together or at least decelerate the outward rush. It was expected that the expansion would either eventually halt and reverse into a big crunch, or continue forever but at an ever-decreasing pace. However, A groundbreaking discovery in the late 1990s overturned this long-held expectation and revolutionized our understanding of the cosmos. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, announced a truly astonishing finding. The expansion of the universe is not slowing down, but is actually speeding up. This discovery was completely unexpected and fundamentally changed the field of cosmology. The lead scientists from these teams, Saul Perlmutter, Brian Schmidt, and Adam Riss, were awarded the Nobel Prize in Physics in 2011 for their work. The discovery was made by observing a specific type of cosmic explosion called a Type Ia supernova. To understand why these particular events were so crucial, we need to know what they are and how they are used. A Type Ia supernova occurs in a binary star system where a white dwarf star, the dense remnant of a star like our Sun, is orbiting another star. The white dwarf slowly siphons matter from its companion. As it accumulates more mass, it eventually reaches a critical limit, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. At this point, the white dwarf becomes unstable and undergoes a thermonuclear runaway, resulting in a colossal explosion that briefly outshines an entire galaxy. The key property of Type Ia supernovae that makes them invaluable for cosmological measurements is their remarkably consistent peak brightness. Because they all explode when they reach roughly the same critical mass, they are believed to have a very similar intrinsic luminosity, meaning they all emit roughly the same amount of light at their brightest point. This makes them what astronomers call standard candles. If you know how truly bright an object is, and you can measure how bright it appears from Earth, you can calculate its distance. For example, if you see two identical light bulbs, and one appears fainter than the other, you know the fainter one is farther away. Type Ia supernovae act as these standardized light bulbs spread across the cosmos. The astronomers observed dozens of these distant Type Ia supernovae. For each supernova, they did two main things. First, they measured its apparent brightness to determine its distance. Second, they measured its redshift. Redshift is the stretching of the light waves from distant objects as space expands, causing the light to shift towards the red end of the spectrum. The greater the redshift, the faster the galaxy containing the supernova is moving away from us, and generally the farther away it is. By combining these two measurements, distance from brightness and recession velocity from redshift, astronomers could map out the expansion history of the universe. What they found was contrary to all expectations. The distant supernovae were fainter than they should have been if the universe's expansion was slowing down. If the expansion were decelerating, these ancient explosions should have appeared closer and thus brighter. The fact that they appeared fainter meant they were farther away than predicted by a decelerating universe model. This implied that the universe's expansion had not been slowing down, but had instead been speeding up over the course of cosmic history. This was a monumental and deeply puzzling revelation. The implications of this accelerating expansion were profound. It meant that there had to be some unknown force or energy pushing space apart, counteracting gravity's pull. This mysterious force was dubbed dark energy. Without it, the observed acceleration could not be explained within the existing framework of cosmology. The discovery of accelerating expansion forced scientists to revise the standard model of the universe, incorporating dark energy as a dominant component. This acceleration also has significant implications for the future of the universe. If dark energy continues to dominate and its influence remains constant or grows, galaxies will continue to move away from each other at an ever-increasing rate. Eventually, distant galaxies will recede so fast that their light will never be able to reach us, effectively moving beyond our observable horizon. Over incredibly long timescales, even galaxies within our own local group might become gravitationally unbound from one another, leading to a big freeze scenario where the universe becomes cold, dark, and empty, with individual galaxies isolated in vast, expanding voids. In a more extreme Big Rip scenario, if dark energy's repulsive force strengthens sufficiently, it could eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. Before the discovery of accelerated expansion, scientists understood that in the very early universe, the presence of matter and radiation was very dense, and their gravitational pull was much stronger. This meant that for the first several billion years after the Big Bang, the universe's expansion was actually slowing down or decelerating. It was only later, when the universe had expanded sufficiently that matter and radiation became diluted, that dark energy's constant density, or increasing influence, became the dominant factor, causing the expansion to switch from deceleration to acceleration. This transition occurred roughly 5 or 6 billion years ago, which is about 7 or 8 billion years after the Big Bang. The discovery of the universe's accelerating expansion completely reshaped modern cosmology. It introduced dark energy as the most significant unknown in our cosmic inventory and opened up entirely new avenues of research. Scientists are now striving to understand the fundamental nature of dark energy, its origins, and its ultimate implications for the universe's destiny. The accelerating expansion of the universe, revealed by observations of distant supernova, points to the existence of a mysterious component called dark energy. While we can observe its effects, the true nature of dark energy remains one of the most profound unsolved puzzles in physics and cosmology. Scientists have put forward several leading ideas to explain what dark energy might be, each presenting its own set of challenges and implications. The most widely accepted and simplest explanation for dark energy is that it is directly related to the cosmological constant, often denoted by the Greek letter lambda. This concept has a fascinating history. It was first introduced by Albert Einstein in 1917 as a term in his equations of general relativity. At the time, the prevailing scientific view was that the universe was static, neither expanding nor contracting. Einstein added the cosmological constant to his equations to counteract gravity's pull and allow for a stable, unchanging universe. However, when Edwin Hubble later discovered that the universe was, in fact, expanding, Einstein reportedly discarded the cosmological constant, calling it his biggest blunder. Fast forward to the late 1990s, with the discovery of accelerated expansion, the cosmological constant was resurrected. In its modern interpretation, the cosmological constant is understood as the intrinsic energy of empty space itself, often referred to as vacuum energy. According to quantum mechanics, even a vacuum, a region devoid of matter and radiation, is not truly empty. Instead, it is teeming with virtual particles that constantly pop into and out of existence, fluctuations in quantum fields. These quantum fluctuations impart a non-zero energy density to space. If this vacuum energy is constant and uniform throughout the universe, it would exert a constant outward pressure, effectively acting as the repulsive force we attribute to dark energy. As space expands, more empty space is created, and therefore more of this vacuum energy emerges, maintaining a constant energy density and driving the accelerating expansion. However, a major problem arises when physicists try to calculate the theoretical value of this vacuum energy from quantum field theories. These calculations predict an energy density that is astronomically larger than the observed value of dark energy. The discrepancy is staggering. The theoretical prediction is greater than the observed value by a factor of about 10 to the power of 120, or a 1 followed by 120 zeros. This is arguably the largest disagreement between theory and observation in the entire history of science. This enormous mismatch, known as the cosmological constant problem, suggests that our current understanding of quantum mechanics or gravity, or both, is incomplete when applied to the vacuum of space. While the cosmological constant remains the simplest and most elegant mathematical solution to describe dark energy's effects, this profound theoretical challenge means it might not be the final answer. Another leading candidate for dark energy is a dynamic energy field, often referred to as quintessence. Unlike the cosmological constant, which implies a fixed energy density of space, quintessence proposes that dark energy is a form of energy that changes over time and varies in space. It would be a new type of fundamental field, similar to scalar fields, that are thought to have driven cosmic inflation in the very early universe. This hypothetical field would permeate all of space and exert a negative pressure, causing acceleration. The appeal of quintessence models lies in their flexibility. If dark energy is a dynamic field, its energy density could have evolved differently throughout cosmic history. potentially explaining why it only became dominant relatively recently, about 5 or 6 billion years ago, allowing for an earlier period of decelerated expansion driven by matter. Depending on the specific properties of this quintessence field, its behavior in the future could also vary. For instance, if the energy density of quintessence decreases over time, the universe's acceleration might eventually slow down. Conversely, if its energy density were to increase, it could lead to the extreme Big Rip scenario, where the universe accelerates so violently that even atoms are eventually torn apart. However, quintessence remains purely hypothetical, and there is no direct observational evidence for such a field. Its existence would require the discovery of new fundamental particles or forces. Beyond the cosmological constant and quintessence, other more speculative ideas about dark energy exist. Some theories propose that dark energy is not a new form of energy or matter at all, but rather a manifestation of modifications to Einstein's theory of general relativity at very large cosmic scales. This would imply that gravity behaves differently on vast distances than it does on smaller local scales. Another highly speculative idea involves the influence of extraspatial dimensions that are hidden from our view. In such models, the effects of these hidden dimensions might manifest as what we perceive to be dark energy in our four-dimensional spacetime. However, these modified gravity theories and extra-dimensional models face significant challenges in reconciling with existing observations and are often more complex than the cosmological constant. Scientists are actively pursuing various observational programs to try and determine the true nature of dark energy. These efforts involve highly precise measurements of the universe's expansion history and its large-scale structure. Projects like the Dark Energy Survey, the upcoming Euclid Space Telescope, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory, formerly LSST, are designed to map billions of galaxies and supernovae, providing more accurate data on how the universe has expanded over cosmic time. By studying the precise rate of acceleration, how dark energy's density might change, and how it affects the clustering of galaxies, astronomers hope to distinguish between the cosmological constant, quintessence, or perhaps entirely new explanations. While dark energy remains an enigma, the quest to understand it is at the forefront of cosmological research, promising to unlock deeper secrets about the fundamental nature of our universe. The concept of the multiverse is a theoretical framework suggesting that our universe, the one we inhabit and observe, might not be the only universe. Instead, it proposes the existence of many universes, perhaps an infinite number of them, existing alongside or beyond our own. This idea challenges the traditional view of the universe as a singular, all-encompassing entity. The term multiverse does not necessarily imply that these other universes are spatially located next to ours in a way we could simply travel to. Rather, it often suggests that they are separate realities, perhaps disconnected from our own space-time, or existing in higher dimensions inaccessible to us. The notion arises from various branches of physics and cosmology, often as a consequence of theories developed to explain phenomena within our own universe. One of the primary motivations for considering a multiverse arises from the fine-tuning problem observed in our universe. Scientists have discovered that many fundamental physical constants and laws, such as the strength of gravity, the mass of an electron, or the precise value of dark energy, appear to be exquisitely tuned for the existence of life as we know it. If these constants were even slightly different, stars might not form, atoms might not be stable, or complex chemistry necessary for life would be impossible. For example, if the strong nuclear force were a few percent weaker, atomic nuclei would not hold together, preventing the formation of elements heavier than hydrogen. If it was slightly stronger, hydrogen would have fused into helium too quickly in the early universe, leaving insufficient hydrogen for long-lived stars like our Sun. The probability of these constants aligning so perfectly by chance seems incredibly small. The multiverse hypothesis offers a potential explanation. If there are many universes, each with different physical laws or constants, then it is not surprising that we find ourselves in one where the conditions are just right for life. In this scenario, our universe is simply one of the lucky ones that can support observers. Another significant source of the multiverse idea comes from modern cosmological theories, particularly the theory of cosmic inflation. Inflation describes a period of extremely rapid, exponential expansion in the very early universe, occurring a tiny fraction of a second after the Big Bang. This theory was proposed to solve several puzzles about the universe, such as its remarkable flatness and uniformity on large scales. Some models of inflation, known as eternal inflation, suggest that inflation, once it starts, might not stop everywhere at once. Instead, it could continue indefinitely in some regions, while in other regions it ends, forming bubble universes. Each of these bubbles would then expand and evolve into a separate universe, potentially with different physical laws, constants, or initial conditions from its neighbouring bubbles. Our universe would simply be one such bubble within this eternally inflating larger multiverse. These bubble universes would be causally disconnected from each other, meaning that light or any other information from one bubble could never reach another. Quantum mechanics, the theory describing the behaviour of matter and energy at the atomic and subatomic levels, also provides a conceptual pathway to the multiverse. The many-worlds interpretation of quantum mechanics, proposed in the 1950s, suggests that every time a quantum measurement is made, and there are multiple possible outcomes, the universe splits or branches into as many parallel universes as there are outcomes. For instance, if a quantum particle has a 50% chance of being in one state and a 50% chance of being in another, then upon measurement, the universe splits into two branches, one where the particle is found in the first state and another where it is found in the second. In this interpretation, all possible quantum outcomes are realized in some universe. These parallel universes are not physically interacting with each other after the split, but they all originate from the same initial quantum state. This interpretation eliminates the need for a collapse of the wave function, a concept in standard quantum mechanics, where a quantum state seemingly randomly chooses one outcome upon observation. The multiverse concept also appears in theories that attempt to unify gravity with quantum mechanics, such as string theory, or its more encompassing framework, M theory. These theories propose that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings, or higher dimensional objects called branes, short for membranes. In some versions of M theory, our universe could be a three-dimensional brane existing within a higher dimensional space, often referred to as the bulk. Other branes, representing other universes, could exist parallel to our own in this higher dimensional space. These branes might occasionally collide, and such collisions have been theorized as a possible mechanism for triggering new Big Bangs. In this brane multiverse scenario, the other universes would be literally beyond our current three spatial dimensions, making them inherently unobservable by conventional means. It is important to emphasize that the multiverse idea remains a theoretical concept. There is currently no direct observational evidence to confirm the existence of other universes. Scientists are actively exploring potential indirect ways to test these theories, such as searching for subtle imprints or gravitational effects that another universe might have left on our own, or looking for specific predictions that these models make about the properties of our universe. For example, some eternal inflation models predict certain characteristics in the cosmic microwave background radiation. However, these are extremely challenging experiments, and the evidence, if found, would likely be indirect. Philosophically, the multiverse idea has profound implications. It challenges the notion of our universe's uniqueness, and raises questions about the very nature of reality. If there are countless other universes, each potentially with different physical laws, does that diminish the significance of our own existence? Or does it expand our understanding of what is possible within the vastness of reality? The multiverse concept pushes the boundaries of our imagination and our scientific inquiry, prompting us to consider possibilities far beyond our immediate cosmic horizon. While speculative, it provides a powerful framework for addressing some of the deepest questions about the universe's origin, its fundamental properties, and our place within it. The concept of a multiverse is not a single, unified theory, but rather an umbrella term for several distinct theoretical models, each proposing different ways in which multiple universes might exist. These models arise from various branches of physics and cosmology, offering different mechanisms for the creation and nature of these other realities. One prominent type is the eternal inflation multiverse, often leading to the idea of bubble universes. This model stems from the theory of cosmic inflation, which posits a period of extremely rapid, exponential expansion in the very early universe, occurring a tiny fraction of a second after the Big Bang. In some inflationary scenarios, inflation does not end uniformly across all of space. Instead, it might continue indefinitely in certain regions, while in other regions it bubbles out of the inflating background and inflation stops. Each of these bubbles then expands and cools to form a separate universe, much like our own. The space between these bubbles continues to inflate, creating more and more bubbles over time. These bubble universes are essentially distinct regions of spacetime causally disconnected from each other. This means that no light or information can travel between them, because the space between them is expanding faster than light can traverse it. Each bubble universe could potentially have different physical constants, different elementary particles, or even different dimensions, depending on the specific way inflation ended within that bubble. Our universe would simply be one such bubble in this vast, ever-generating cosmic foam. Another significant type is the many worlds interpretation of quantum mechanics, which posits a quantum multiverse or parallel universes. This interpretation suggests that every time a quantum event occurs, and there are multiple possible outcomes, the universe splits or branches into multiple parallel universes, with each universe representing a different outcome. For example, if a quantum particle has a 50% chance of spinning up and a 50% chance of spinning down when measured, then in one universe, the particle is found to be spinning up, and in another parallel universe, it is found to be spinning down. All possible outcomes of every quantum measurement are realized in some universe. These parallel universes are not spatially separated in the way bubble universes might be. Instead, they are thought to coexist in a kind of abstract, higher dimensional space, continually branching off from each other. The key feature is that these universes are causally disconnected, meaning there is no interaction or communication between them once a split occurs. From our perspective within one branch, the other branches are unobservable. This interpretation provides a deterministic view of quantum mechanics, avoiding the concept of wave function collapse, where a quantum state randomly settles into a single outcome. A third category is the brane multiverse, which arises from theories like string theory and M theory. These theories propose that the universe has more than the three spatial dimensions we perceive plus time. These extra dimensions are thought to be curled up very tightly, making them unobservable at our scale. In some versions of M theory, our entire universe is envisioned as a three-dimensional brane, a shortened term for membrane, existing within a higher dimensional space, often called the bulk. Other branes, which represent other universes, could exist parallel to our own in this bulk. These branes might be separated by tiny distances in the extra dimensions, or they might be very far apart. Collisions between these branes have been theorized as a possible mechanism for the Big Bang, where the energy released from the collision could have ignited the expansion of a new universe. In this model, other universes are literally beyond our three spatial dimensions, existing in a different part of the higher dimensional bulk. The properties of these other brane universes could vary significantly, depending on their specific characteristics within the bulk. The cyclic or bouncing multiverse is another theoretical possibility. This idea suggests that the universe undergoes an endless cycle of expansion and contraction. Our current universe expands to a certain point, then gravity eventually pulls it back together in a big crunch, collapsing into an extremely hot, dense state similar to the beginning of the Big Bang. From this big crunch, a new Big Bang then occurs, giving rise to a new universe. Each cycle could be considered a new universe, potentially with different physical laws or initial conditions. This model offers a way to avoid the question of what came before the Big Bang, as the universe would have always existed in some form, continuously cycling through periods of expansion and contraction. A more abstract concept is the mathematical multiverse, proposed by physicist Max Tegmark. This idea suggests that all mathematically consistent structures correspond to a real, existing universe. If a universe can be described by a consistent set of mathematical equations, then it exists. This implies that there could be universes where the laws of physics are completely different from our own, as long as they are mathematically coherent. This is a very broad and philosophical definition of a multiverse, encompassing all possible mathematical realities. Finally, the simplest form of multiverse, often called the infinite universe or Hubble volume multiverse, arises if the universe is truly infinite in spatial extent, and if matter is distributed uniformly on sufficiently large scales. If the universe is infinite and there are only a finite number of ways particles can arrange themselves within a given volume, then eventually, every possible configuration of particles must repeat. This means that beyond our observable universe, there would be other regions of space that are exact copies or near copies of our own region, including other Earths, other versions of ourselves, and other galaxies. These are not separate universes in the sense of being disconnected from our space-time, but rather distant regions within the same infinite universe that are beyond our current observable horizon. Each of these multiverse concepts addresses different puzzles in physics and cosmology, from the fine-tuning of our universe's constants to the interpretation of quantum mechanics. While they remain theoretical and lack direct observational evidence, they represent active areas of scientific inquiry and philosophical debate, pushing the boundaries of our understanding of reality. The vastness of the universe naturally leads to one of humanity's most profound questions. Is there life beyond Earth? Given the immense number of stars and galaxies, the possibility of other planets hosting life, even intelligent life, seems compelling. Our understanding of the universe's scale provides a strong statistical argument for this possibility. The search for life beyond Earth primarily focuses on planets orbiting other stars, known as exoplanets. The discovery of exoplanets has revolutionized our understanding of planetary systems. The first exoplanet orbiting a Sun-like star was confirmed in 1995. Since then, thousands of exoplanets have been detected using various methods such as observing the slight dimming of a star as a planet passes in front of it, the transit method, or detecting the wobble in a star's motion caused by the gravitational tug of an orbiting planet, the radial velocity method. These discoveries show that planets are common throughout our galaxy, suggesting that the conditions for planet formation are widespread. When searching for life as we know it, scientists often focus on the concept of a habitable zone, sometimes called the Goldilocks zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Liquid water is considered essential for life because it acts as a solvent, allowing chemical reactions necessary for biological processes to occur. If a planet is too close to its star, water would evaporate. If it is too far, water would freeze. The size and temperature of the star determine the location and width of its habitable zone. For example, a smaller, cooler star would have a habitable zone closer to it than a larger, hotter star like our Sun. Many of the exoplanets discovered so far fall within their star's habitable zones, making them potential candidates for hosting life. Beyond liquid water, the fundamental building blocks of life are also crucial. Life on Earth is primarily carbon-based, relying on elements like carbon, hydrogen, oxygen, and nitrogen to form complex organic molecules such as proteins, nucleic acids, and carbohydrates. These elements are not unique to Earth. They are among the most abundant elements in the universe, formed inside stars and dispersed into space through stellar explosions. This cosmic abundance suggests that the raw materials for life are readily available across the galaxy, increasing the probability that life could arise elsewhere. The question of how many intelligent technological civilizations might exist in our galaxy was famously formalized by astronomer Frank Drake in the 1960s with the Drake equation. While it is not a formula to be solved precisely, it serves as a framework for considering the various factors that would need to align for such civilizations to arise. These factors include the rate of star formation, the fraction of stars with planets, the average number of planets that could support life, the fraction of those planets where life actually arises, the fraction of those where intelligent life develops, the fraction of intelligent civilizations that develop technology capable of interstellar communication, and the length of time such civilizations release detectable signals into space. Each term in the equation involves significant uncertainty, but it highlights the many steps required for a communicative civilization to emerge. Despite the seemingly high probability suggested by the vastness of the universe, we have not yet found definitive evidence of extraterrestrial life, especially intelligent life. This lack of evidence is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Several explanations have been proposed for this paradox. One idea is the Great Filter, which suggests that there is some extremely challenging step or series of steps in the evolution of life that prevents it from reaching a technologically advanced, spacefaring stage. This filter could be in our past, e.g., the very rare emergence of life or complex life, or in our future, e.g., self-destruction or catastrophic events. Another challenge is the immense distances involved. Even if life is common, the sheer scale of the galaxy means that civilizations could be so far apart that communication is practically impossible. Light, the fastest thing in the universe, takes years, decades, or even centuries to travel between stars. Sending and receiving signals across such distances would require enormous amounts of time and energy. Furthermore, civilizations might be very short-lived on cosmic timescales, making the window for detection very brief. The search for extraterrestrial life takes various forms. The search for extraterrestrial intelligence, or SETI, primarily involves listening for artificial radio signals from space. Large radio telescopes scan the skies, hoping to pick up a message from another civilization. So far, no confirmed artificial signals have been detected. Another approach involves looking for biosignatures in the atmospheres of exoplanets. Future space telescopes will be designed to analyze the light passing through exoplanet atmospheres, searching for gases like oxygen, methane, or ozone that are strongly associated with biological activity on Earth. The presence of these gases in significant quantities could be an indirect indicator of life. The types of life we might find could vary greatly. It is generally thought that simple microbial life, similar to early life on Earth, might be far more common than complex multicellular organisms or intelligent civilizations. Microbes are incredibly resilient and can thrive in extreme environments. If life exists elsewhere, it might be confined to subsurface oceans on icy moons, or within the clouds of gas giants, rather than on planetary surfaces. The possibility of life forms based on different chemistries or principles, not reliant on carbon and water, also exists, though our search methods are currently biased towards life as we understand it. Ultimately, the question of life beyond Earth remains one of the most exciting and unanswered questions in science. The universe's vastness and the growing number of discovered exoplanets strongly suggest that Earth is unlikely to be the only place where life has arisen. However, the challenges of detection are formidable, and the answer awaits future scientific advancements and continued exploration. The ultimate fate of the universe is a profound question in cosmology, with scientific theories suggesting several possible scenarios for its eventual end. These scenarios depend critically on the amount of matter and energy in the universe, particularly the mysterious component known as dark energy, which drives the accelerated expansion. Based on current observations, two leading possibilities for the universe's demise are the Big Freeze, also known as heat death, and the Big Rip. Both scenarios depict a universe that expands forever, but with different ultimate consequences for its structures. The Big Freeze, or heat death, is the most widely accepted ultimate fate for our universe, given the current understanding of its composition and expansion. This scenario predicts that the universe will continue to expand indefinitely, becoming progressively colder, emptier, and more diluted. The expansion means that galaxies will move further and further apart from each other. Eventually, beyond our local group of galaxies, all other galaxies will recede at speeds greater than the speed of light, making them unobservable and effectively isolating our local galactic cluster. Stars, which are the universe's primary sources of light and heat, have finite lifespans. Over immense timescales, all stars will exhaust their nuclear fuel. The smallest and longest-lived stars, red dwarfs, might shine for trillions of years, but even they will eventually fade. Larger stars burn out much more quickly, within millions or billions of years. As stars die, they leave behind stellar remnants, white dwarfs, neutron stars, and black holes. After all stars have ceased to shine, the universe will enter a truly dark era. White dwarfs will slowly cool down over quadrillions of years, eventually becoming cold, dark black dwarfs that emit no light or heat. Neutron stars and stellar mass black holes will persist, but they too will contribute little to the universe's overall energy budget. Over even longer timescales, perhaps a Google years, a 1 followed by 100 zeros, these stellar remnants will be gravitationally ejected from galaxies due to random encounters, or they will slowly spiral into supermassive black holes at galactic centers. The galaxies themselves will become increasingly diffuse, with their remaining objects scattered throughout ever larger volumes of space. The supermassive black holes, which reside at the centers of most galaxies, are the most robust structures in this dying universe. However, even black holes are not eternal. According to theoretical physics, black holes slowly evaporate over incredibly long periods through a process called Hawking radiation. This process is exceedingly slow for astrophysical black holes. A black hole with the mass of our Sun would take far longer than the current age of the universe to evaporate. A supermassive black hole with a mass of 1 billion suns might take 10 to the power of 100 years to evaporate completely. Once all black holes have evaporated, the universe will contain only a dilute soup of fundamental particles. Photons, neutrinos, electrons and positrons, all moving farther and farther apart. Protons, which are the building blocks of atomic nuclei, are currently thought to be stable, but some theories of particle physics predict that they too might decay over timescales far exceeding the age of the universe, perhaps 10 to the power of 34 years, or even 10 to the power of 49 years. If protons decay, then all remaining matter will eventually break down into even more fundamental particles and radiation. The final state of the Big Freeze is one of maximum entropy, or maximum disorder. All available energy will have been spread out uniformly throughout the universe, reaching a state of thermodynamic equilibrium. There will be no temperature differences, no energy gradients, and thus no capacity for work or any organized activity. The universe will be an incredibly cold, dark and empty expanse, with particles so sparsely distributed that interactions are virtually non-existent. This state is often referred to as heat death, because all useful energy has been dissipated and no further processes can occur. The expansion ensures that this state of maximum entropy is eventually reached, as it continuously dilutes the energy and matter, preventing any localized concentrations that could drive further evolution. The Big Rip is a more dramatic and less likely scenario for the universe's end, but it remains a theoretical possibility depending on the nature of dark energy. This scenario postulates that dark energy is not a constant force, but rather a form of phantom energy, whose density increases over time. If the density of dark energy were to increase, its repulsive effect, which drives the universe's expansion, would become stronger and stronger. This escalating repulsive force would eventually overcome all other fundamental forces, leading to the complete disintegration of all structures in the universe. In the Big Rip scenario, the expansion would accelerate so rapidly that it would begin to tear apart gravitationally bound systems. First, galaxy clusters would be pulled apart as the accelerating expansion overcomes the gravitational pull holding them together. This would happen billions of years before the final rip. Next, individual galaxies would be torn apart as the expansion becomes strong enough to overcome the gravitational forces holding stars within their galactic orbits. Stars would drift away from their galaxies, and the galaxies themselves would disintegrate into isolated stars. As the expansion continues to accelerate, the force of dark energy would become so powerful that it would overcome the electromagnetic and strong nuclear forces that hold atoms and even atomic nuclei together. Planets would be torn apart from their stars, and stars themselves would be ripped into their constituent atoms. Eventually, atoms themselves would be ripped apart as the electrons are pulled away from their nuclei and the protons and neutrons within the nuclei are separated. Even the subatomic particles, like quarks, might be torn apart from each other. The final moments of the Big Rip would involve the very fabric of spacetime being stretched to such an extreme that it would literally rip apart. This would mean that the fundamental forces that govern interactions would no longer be able to operate, and everything, down to the smallest particles, would be isolated in an ever-expanding, infinitely dilute void. The universe would end not in a cold, quiet fade, but in a violent, catastrophic shredding of all reality. The timeline for a big rip is much shorter than for a big freeze, potentially occurring within tens of billions of years from now, rather than quadrillions or Google years. However, current observations of dark energy suggest that its density is constant, not increasing, making the Big Rip a less favoured scenario. The critical factor for the Big Rip is a parameter called the equation of state of dark energy, often denoted as W. If W is less than -1, a Big Rip is possible. Current measurements indicate W is very close to -1, consistent with a cosmological constant which would lead to a big freeze. While current cosmological observations strongly suggest that the universe will expand forever, leading to scenarios like the Big Freeze or the Big Rip, an alternative ultimate fate that was once widely considered is the Big Crunch. This scenario describes a universe that eventually stops expanding and begins to contract, eventually collapsing back into an extremely hot and dense state, similar to the conditions at the very beginning of the Big Bang. The possibility of a Big Crunch depends critically on the total amount of matter and energy in the universe, specifically whether the gravitational pull of all matter is strong enough to overcome the outward push of expansion, including the effects of dark energy. For a Big Crunch to occur, the average density of matter and energy in the universe would need to be above a certain critical value. If the density is greater than this critical density, the universe is considered closed, meaning its geometry is positively curved, like the surface of a sphere. In such a closed universe, the collective gravitational attraction of all its contents would eventually halt the expansion and cause it to reverse. Imagine throwing a ball upwards. If you throw it with enough force, it will escape Earth's gravity and continue into space. But if you don't throw it hard enough, gravity will eventually pull it back down. Similarly, the Big Bang was like an initial outward push, and the Big Crunch would be the universe falling back in on itself due to its own gravity. In a universe destined for a Big Crunch, the first phase would be a slowing down of the expansion. For billions of years, galaxies would continue to recede from each other, but at an ever-decreasing rate. The influence of dark energy, which currently accelerates the expansion, would eventually be overcome by the cumulative gravitational pull of all matter and energy. As the expansion rate approaches zero, the universe would reach its maximum size. This point would represent the cosmic equivalent of the ball reaching the peak of its upward trajectory before falling back down. After reaching its maximum size, the universe would begin to contract. The distances between galaxies would start to shrink and galaxies would begin to move towards each other. This contraction would accelerate over time, much like the expansion accelerated in the early universe. As the universe shrinks, the density of matter and energy would increase. The cosmic microwave background radiation, which is now very cold and stretched out, would begin to blue shift, meaning its wavelengths would shorten and its energy would increase, making it hotter. As the contraction continues, galaxy clusters would merge, and then individual galaxies would collide more frequently. The night sky, which is currently dark and vast, would become increasingly bright as distant galaxies, now approaching us, would appear bluer and more luminous due to blue shift. The density of matter would rise dramatically, and the temperature would soar. Stars would begin to experience more frequent gravitational interactions and collisions within their increasingly crowded galaxies. Planets might be torn from their orbits or collide with other celestial bodies. In the final stages of the Big Crunch, the universe would resemble the early universe, but in reverse. The temperature would rise to billions of degrees, and the density would become immense. Atoms would be stripped of their electrons, forming a hot plasma. As the contraction continues, even atomic nuclei would be broken down into their constituent protons and neutrons. Eventually, all matter would be compressed into a super-dense, super-hot state, similar to the conditions just before Big Bang nucleosynthesis. The universe would become opaque again, filled with a searing hot soup of fundamental particles and radiation. The very last moments of the Big Crunch would see all of spacetime collapse into an infinitely dense singularity, a point of infinite temperature and density. This final state would be the inverse of the Big Bang singularity, where all of reality is crushed out of existence. The concept of a Big Crunch implies a closed universe, where the total amount of matter and energy is sufficient to reverse the expansion. However, current cosmological observations do not support the Big Crunch scenario. Measurements of the universe's expansion rate and its overall geometry, primarily through observations of distant supernovae and the cosmic microwave background radiation, indicate that the universe is flat, or very nearly flat. A flat universe implies that it will continue to expand forever, though the expansion rate will slow down and approach zero over infinite time rather than reversing. More importantly, the discovery of dark energy in the late 1990s provided strong evidence that the universe's expansion is not slowing down, but actually accelerating. This accelerating expansion acts as a repulsive force, counteracting gravity and pushing galaxies further apart. For a Big Crunch to occur, the influence of dark energy would have to diminish or reverse its effect, or there would need to be a significantly higher density of matter than currently observed, neither of which is supported by present data. While the Big Crunch remains a theoretically possible fate for the universe, it is not the favoured model based on current empirical evidence. The observed accelerating expansion driven by dark energy suggests that gravity will not win the cosmic tug-of-war, and the universe is more likely headed towards an endless expansion and cooling, rather than a fiery collapse. Nevertheless, studying the Big Crunch helps us understand the full range of possibilities for the universe's evolution and the delicate balance of forces that shape its destiny. The concept of universe rebirth refers to theoretical models that propose a cyclical nature for the cosmos, suggesting that the universe might undergo an endless series of Big Bangs and Big Crunches, effectively being reborn after each collapse. This idea, often termed a cyclic universe or bouncing cosmology, offers an alternative to a universe with a definitive beginning and end, instead presenting an eternal cycle of creation and destruction. Such models attempt to address some of the profound questions left open by the standard Big Bang theory, such as what existed before the Big Bang and what happens at the singularity. In a cyclic universe model, the Big Crunch is not the ultimate end but rather a transition point. After reaching a state of maximum compression and density, instead of collapsing into an infinitely dense singularity and ceasing to exist, the universe bounces back. This bounce initiates a new period of expansion, a new Big Bang giving rise to a new universe. This new universe would then expand, evolve, and eventually contract again, leading to another Big Crunch and another bounce. This process would repeat indefinitely, creating an eternal cosmic cycle. One of the primary motivations for cyclic models is to avoid the singularity problem inherent in the standard Big Bang and Big Crunch scenarios. A singularity represents a point where the laws of physics break down, making it impossible to describe what happens at or beyond that point. A bounce mechanism, however, would allow the universe to transition smoothly from contraction to expansion without encountering an infinite density or temperature. This would mean that the universe always exists in some form, either expanding or contracting, without a true beginning or end. Several theoretical frameworks have been proposed to explain how such a bounce could occur. One prominent idea comes from brane cosmology, which is an extension of string theory and ME theory. In these models, our universe is envisioned as a three-dimensional brane existing within a higher dimensional space, or bulk. Other branes, representing other universes, could exist in this bulk. A cyclic scenario in brane cosmology suggests that our Big Bang might have been caused by the collision of two such branes. After expanding, the universe would eventually contract, leading to another brane collision that triggers a new Big Bang, thus completing a cycle. This ekpyrotic or cyclic model proposes that the universe contracts slowly, then undergoes a rapid bounce, followed by expansion. The energy from the collision would manifest as the hot, dense state we associate with the Big Bang. Another approach to cyclic models involves modifications to gravity at very high densities. Standard general relativity predicts a singularity at the Big Bang and Big Crunch. However, some theories of quantum gravity, which attempt to unify general relativity with quantum mechanics, suggest that gravity behaves differently at extremely small scales and high densities. For example, in some models of loop quantum cosmology, a branch of loop quantum gravity, the fabric of spacetime is not continuous but is made of discrete loops. As the universe contracts and density increases, quantum effects of gravity become dominant, preventing the formation of a singularity. Instead, the universe reaches a maximum density and then bounces back into expansion. This quantum bounce would replace the Big Bang singularity with a smooth transition from a contracting phase to an expanding one. In a cyclic universe, each new cycle could potentially have different properties. For example, the values of fundamental physical constants, the amount of dark energy, or even the number of dimensions might vary from one cycle to the next. This variability could offer a solution to the fine-tuning problem, similar to how the multiverse idea does. If there are infinite cycles, and the physical laws or constants are slightly different in each cycle, then it is not surprising that we find ourselves in a cycle where the conditions are just right for life to emerge and evolve. However, cyclic universe models face significant challenges. One major difficulty is the entropy problem. If the universe undergoes endless cycles, and entropy, disorder, always increases in each cycle, then the universe should become progressively more disordered with each bounce. This would mean that earlier cycles would have had lower entropy, and later cycles would have higher entropy, leading to a situation where the universe would eventually become so disordered that it could no longer support complex structures or even fundamental particles. This implies that there must have been a beginning to the cycles, or some mechanism that resets the entropy at each bounce, which is not yet fully understood or proven. Some cyclic models propose mechanisms to dilute or reduce entropy during the bounce phase, but these are highly speculative. Another challenge is the observational evidence. Current cosmological data, particularly from the cosmic microwave background radiation and observations of distant supernova, strongly support a universe that is flat and undergoing accelerated expansion due to dark energy. This evidence points towards an ever-expanding universe, likely leading to a big freeze rather than a big crunch that would be necessary for a bounce. For a cyclic model to be viable, the nature of dark energy would need to be different from what is currently observed, perhaps fluctuating or eventually diminishing in strength to allow for a gravitational turnaround. Despite these challenges, the idea of universe rebirth remains an active area of theoretical research. It provides an elegant solution to the question of what came before the Big Bang and offers a vision of an eternal cosmos that continually renews itself. While not currently supported by direct observational evidence, cyclic models continue to push the boundaries of our understanding of spacetime, gravity, and the ultimate nature of reality, offering a compelling alternative to a universe with a single, finite lifespan. The question of what, if anything, existed before the Big Bang is one of the most profound and challenging inquiries in modern cosmology. To approach this question, it is essential to first understand what the Big Bang theory describes. The Big Bang is not merely an explosion of matter and energy into a pre-existing empty space. Instead, it is understood as the beginning of space and time themselves, along with all the matter and energy within them. According to this theory, the entire observable universe, and perhaps much more, originated from an extremely hot, dense state approximately 13.8 billion years ago. As such, the concept of before the Big Bang becomes problematic, as time as we understand it is thought to have begun at that very moment. If time itself originated with the Big Bang, then asking what happened before it is akin to asking what is north of the North Pole. The question assumes a temporal framework that may not have existed. Our everyday intuition about time, where events always precede or follow one another in a linear sequence, breaks down when applied to the very earliest moments of the universe. The Big Bang, in this view, represents the boundary of space-time, the point beyond which our current physical laws and models cease to apply or offer meaningful predictions. It is the beginning of the cosmic clock, so to speak. However, this does not stop physicists and cosmologists from exploring speculative ideas that attempt to address this profound question. These ideas often involve pushing the boundaries of known physics, particularly by incorporating principles from quantum mechanics, which governs the behavior of matter and energy at the smallest scales, and quantum gravity, a theoretical framework that seeks to unify gravity with quantum mechanics. One set of speculative ideas involves cyclic or bouncing universe models. In these scenarios, the Big Bang is not the absolute beginning, but rather a transition point from a previous cosmic era. For instance, Some theories propose that our universe might be the result of a big crunch of a previous universe. In this model, a universe expands for a certain period, then gravity eventually overcomes the expansion, causing all matter and energy to contract back into an extremely hot, dense state, similar to the initial conditions of our Big Bang. This crunch then bounces into a new expansion, giving rise to a new universe. This process could repeat endlessly, creating an eternal cycle of big bangs and big crunches. In such a model, there was always something before our Big Bang, namely the previous universe in the cycle. This avoids the need for an absolute beginning, but it shifts the question to what initiated the very first cycle, or if the cycle itself is eternal. Another prominent idea comes from eternal inflation theory. This is an extension of the cosmic inflation theory, which describes a period of extremely rapid, exponential expansion in the universe's infancy. In eternal inflation, once it starts, does not stop everywhere simultaneously. Instead, it continues indefinitely in some regions, while in other regions it ends, forming bubble universes. Our universe would be just one such bubble. The space between these bubbles continues to inflate, perpetually generating new bubble universes. In this framework, the multiverse is the larger, eternally inflating background, and our Big Bang was simply the moment when inflation ended in our particular region, allowing our universe to begin its expansion and cool. In this model, there might not be a beginning to the inflating background itself, or its beginning might be so far in the past that it is effectively eternal. This suggests that before our Big Bang, there was an inflating spacetime potentially giving rise to countless other universes. Quantum gravity theories offer another perspective on what might have existed before the Big Bang. Our current understanding of gravity, described by Albert Einstein's theory of general relativity, works exceptionally well for large-scale phenomena like planets, stars, and galaxies. However, general relativity breaks down at extreme conditions, such as the singularity at the heart of a black hole, or the initial singularity often associated with the Big Bang. At these points, matter and energy are compressed to infinite density, and the laws of physics as we know them no longer apply. This is where quantum mechanics, which governs the very small, must be incorporated. The challenge is that general relativity and quantum mechanics are fundamentally different in their descriptions of reality. General relativity describes space-time as a smooth, continuous fabric, while quantum mechanics describes particles and forces in terms of discrete probabilistic units. A theory of quantum gravity aims to reconcile these two frameworks. If successful, such a theory might describe a state of the universe where space and time themselves were not well defined in the way they are today. For example, loop quantum gravity, an alternative to string theory, suggests that space and time are not continuous, but are made up of tiny, discrete loops, or atoms of spacetime. In this framework, the Big Bang singularity might be replaced by a big bounce, where the universe did not begin from a point of infinite density, but rather from the collapse of a previous universe that reached a minimum size before bouncing back into expansion. This would mean that before our Big Bang, there was a contracting phase of a previous universe. String theory and M-theory also offer insights into the before the Big Bang question. These theories propose that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings or higher dimensional objects called brains. In some M-theory models, our universe could be a three-dimensional brain existing within a higher dimensional space, or bulk. Other brains, representing other universes, could exist parallel to our own. In this brain cosmology, the Big Bang might have been caused by the collision of two such brains, or by the interaction of our brain with another. In this scenario, before the Big Bang, there were these brains floating in a higher dimensional bulk, and their interaction triggered the creation of our universe. Another concept is that of a pregeometric state. Some theoretical physicists propose that before the Big Bang, there was no space or time as we understand them. Instead, there might have been a more fundamental abstract state, perhaps a quantum foam or a network of relationships from which space-time emerged. In this view, space and time are not fundamental, but are emergent properties of this deeper reality. This would mean that the question of before is truly meaningless, as the very concepts of space and time did not yet exist. It is crucial to emphasize that all these ideas are highly speculative and theoretical. They are not supported by direct observational evidence, and they often involve mathematics and concepts that are at the very edge of our current scientific understanding. The challenge of testing these theories is immense, as the conditions of the very early universe are inaccessible to direct experimentation. However, these theoretical explorations are vital for pushing the boundaries of our knowledge and for developing new frameworks that might one day provide a more complete picture of cosmic origins. The question of before the beginning forces us to confront the limits of our intuition and the profound mysteries that lie at the heart of existence. The quest to unify physics is one of the grandest challenges in modern science. It refers to the ambitious goal of finding a single, comprehensive theoretical framework that can describe all the fundamental forces and particles in the universe. Currently, physics operates with two highly successful but separate pillars: Albert Einstein's general relativity, which describes gravity and the large-scale structure of the cosmos, and quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic scales. The problem arises because these two theories, while incredibly accurate within their respective domains, are fundamentally incompatible when applied together. General relativity, developed by Einstein in 1915, revolutionized our understanding of gravity. Instead of a force pulling objects together, Einstein proposed that gravity is a manifestation of the curvature of spacetime, caused by the presence of mass and energy. Massive objects, like planets and stars, warp the fabric of spacetime around them, and other objects follow the curves in this fabric. This theory accurately describes phenomena such as the orbits of planets, the bending of light around massive objects, and the expansion of the universe. It is a classical theory, meaning it describes the universe in a continuous deterministic way, without the inherent uncertainties and probabilities of the quantum world. General relativity works exceptionally well for describing the universe on large scales, from the solar system to galaxy clusters. Quantum mechanics, developed in the early 20th century by scientists like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, describes the universe at its smallest scales. It reveals a world where energy, momentum, and other quantities are not continuous, but come in discrete packets called quanta. Particles behave both as particles and as waves, and their properties can only be described probabilistically. Quantum mechanics successfully describes the behavior of atoms, the emission of light, and the interactions of subatomic particles. It forms the basis for technologies like lasers, transistors, and nuclear energy. The standard model of particle physics, built upon quantum mechanics, describes three of the four fundamental forces: the strong nuclear force, the weak nuclear force, and the electromagnetic force, along with all known elementary particles. The fundamental incompatibility between general relativity and quantum mechanics becomes apparent when physicists try to apply them simultaneously to extreme conditions. For instance, at the center of a black hole, matter is compressed to an infinitely dense point called a singularity, where gravity becomes incredibly strong. Similarly, at the very beginning of the universe, during the Big Bang, all matter and energy were concentrated into an extremely small and dense state. In these environments, both gravity, requiring general relativity, and quantum effects, requiring quantum mechanics, are significant. However, when attempts are made to combine the mathematical frameworks of these two theories, they yield nonsensical results, such as infinite probabilities or energies. This indicates that our current understanding of physics is incomplete, and that a new, more encompassing theory is needed. The need for unification is crucial for several reasons. Firstly, understanding the Big Bang is impossible without a unified theory. The universe began from a state where all its matter and energy were compressed into a volume smaller than an atom. At such scales, quantum effects would have been dominant, yet the presence of all the universe's mass means gravity would also have been incredibly strong. To accurately describe the conditions and events of the universe's first moments, we need a theory that can seamlessly merge gravity with quantum mechanics. Without it, the Big Bang remains a point beyond which our current physics cannot fully explain. Secondly, A unified theory would allow us to understand the nature of black holes more completely. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. At their core lies a singularity where matter is infinitely dense. A theory of quantum gravity would be necessary to describe the physics at this singularity, and to understand phenomena like Hawking radiation, where black holes are theorized to emit particles due to quantum effects near their event horizons. Thirdly, a unified theory would provide a more complete picture of reality. Currently, we have 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The Standard Model successfully unifies the electromagnetic, strong and weak forces into a single framework at high energies, but gravity remains stubbornly separate. A theory of everything, TOE, would integrate gravity with the other 3 forces, explaining all fundamental interactions from a single set of principles. Such a theory might also explain why fundamental constants, like the mass of an electron or the strength of electromagnetic force, have the precise values they do. It could reveal deeper symmetries and connections in the universe that are currently hidden from us. Several theoretical approaches are being pursued to achieve this unification. String theory, which proposes that fundamental particles are tiny vibrating strings, is one of the most prominent candidates. It naturally incorporates gravity in a quantum framework. Another approach is loop quantum gravity, which attempts to quantize spacetime itself, suggesting that space and time are not continuous, but are made of discrete units. Other ideas include emergent gravity, where gravity is seen as an emergent phenomenon rather than a fundamental force, and various grand unified theories, JUTs, that aim to unify the strong, weak, and electromagnetic forces at even higher energies as a step towards a TOE. The search for a unified theory is not just an academic exercise. It represents the ultimate quest for understanding the fundamental nature of reality. It promises to unlock secrets about the universe's origin, its ultimate fate, and the very fabric of space-time. While experimental verification of these theories remains incredibly challenging due to the extreme energies and tiny scales involved, the pursuit of unification continues to drive theoretical physics forward, pushing the boundaries of human knowledge and imagination. String theory is a theoretical framework in physics that proposes a revolutionary idea about the fundamental building blocks of the universe. Instead of viewing elementary particles as zero-dimensional, point-like objects, string theory suggests that they are actually tiny, one-dimensional vibrating strings. Imagine these strings as incredibly small, much smaller than an atom, or even a proton or an electron. They are so small that they appear as points to our current observational capabilities, similar to how a distant power line might look like a single line rather than a collection of individual wires. The core concept of string theory is that the different ways these tiny strings vibrate give rise to the different fundamental particles we observe. Just as a violin string can produce different musical notes depending on how it vibrates, a fundamental string in string theory can produce different particles depending on its vibration pattern. For example, one vibration pattern might correspond to an electron, another to a photon, the particle of light, and yet another to a quark. This elegant idea provides a unified way to describe all known particles and forces. One of the most compelling aspects of string theory is its ability to naturally incorporate gravity into a quantum framework. In traditional particle physics, gravity is described by general relativity, which is a classical theory. However, all other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are described by quantum mechanics. The particle that is hypothesized to carry the gravitational force is called the graviton. In string theory, one of the vibration modes of these fundamental strings corresponds precisely to the properties expected of a graviton. This means that string theory inherently includes gravity, making it a strong candidate for a quantum theory of gravity, which is essential for understanding phenomena like the Big Bang and black holes. This is a significant achievement because combining gravity with quantum mechanics has been a persistent problem in physics for decades. A key feature of string theory is that it requires the existence of extra spatial dimensions beyond the 3 we experience: length, width, height, and the one dimension of time. Most versions of string theory require 10 or 11 spacetime dimensions in total. This means there could be 6 or 7 extra spatial dimensions that are currently hidden from us. The reason we don't perceive these extra dimensions is that they are thought to be compactified or curled up into incredibly tiny, intricate shapes at every point in our familiar three-dimensional space. Imagine a garden hose. From a distance it looks like a one-dimensional line, but up close you can see its two-dimensional surface. Similarly, these extra dimensions are so small that they are inaccessible to our current instruments. The specific way these extra dimensions are curled up could determine the fundamental physical constants and laws that govern our universe. Another important concept often associated with string theory is supersymmetry. Supersymmetry is a theoretical symmetry that proposes that every fundamental particle has a superpartner with a different spin. For example, if an electron, a matter particle with half-integer spin, has a superpartner, it would be a selectron, a force-carrying particle with integer spin. Similarly, a photon, a force-carrying particle with integer spin, would have a superpartner called a photino, a matter particle with half-integer spin. If supersymmetry exists, it would help to solve several problems in physics, such as the hierarchy problem, why the Higgs boson is so light, and could provide a candidate for dark matter. While no superpartners have been directly observed yet, supersymmetry is a common feature in many string theory models. String theory has evolved into a broader framework known as M-theory. M-theory unifies the 5 different consistent string theories that were discovered, and also includes higher dimensional objects called branes, short for membranes. These branes can have various numbers of dimensions, from 0-dimensional points to 9-dimensional objects. In some M-theory scenarios, our entire universe could be a 3-dimensional brane floating in a higher dimensional space, often referred to as the bulk. This brane cosmology opens up the possibility of a multiverse, where other universes could exist on other branes parallel to our own. The goals of string theory are ambitious. Its primary aim is to be a theory of everything, TOE, a single, comprehensive framework that can describe all fundamental particles and forces in the universe, including gravity. It seeks to resolve the inconsistencies between general relativity and quantum mechanics, providing a unified description of reality at all scales. Furthermore, string theory aims to explain the values of fundamental constants, the number of dimensions, and the very nature of space and time. Despite its elegance and mathematical consistency, string theory currently remains a theoretical framework. It has not yet been experimentally verified because the energies required to probe the string scale are far beyond the capabilities of current particle accelerators, such as the Large Hadron Collider. The strings are theorized to be so incredibly small that direct observation is impossible with present technology. However, physicists continue to develop string theory, exploring its mathematical implications and searching for indirect experimental signatures that could confirm its validity. It represents a frontier in theoretical physics, offering a compelling vision of a universe built from vibrating strings in higher dimensions. Loop quantum gravity is a theoretical framework in physics that attempts to reconcile 2 of the most successful, yet seemingly incompatible theories of the universe: Albert Einstein's general theory of relativity and quantum mechanics. General relativity describes gravity as the curvature of spacetime and works exceptionally well at large scales, explaining the motion of planets, stars, and galaxies. Quantum mechanics, on the other hand, describes the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. The challenge lies in describing gravity in a quantum way, especially in extreme environments like the very early universe or inside black holes, where both gravity and quantum effects are significant. Loop quantum gravity offers a unique approach to this problem by proposing that space and time are not smooth and continuous, but rather discrete and granular, made of tiny, indivisible units. The core idea of loop quantum gravity is that spacetime itself is quantized, meaning it is composed of fundamental, indivisible atoms, or loops of space. Just as matter is made of atoms and energy comes in discrete packets called quanta, loop quantum gravity suggests that space and time are also not infinitely divisible. Imagine a fabric that appears smooth from a distance, but upon closer inspection, you realize it is woven from tiny interlocking threads. In loop quantum gravity, these threads are the fundamental loops of space. These loops are incredibly small, on the order of the Planck length, which is approximately 1.6 times 10 to the power of minus 35 meters. This is an unimaginably tiny scale, far smaller than any atomic nucleus. At this scale, the very notion of smooth space breaks down, and its granular nature becomes apparent. In this theory, the geometry of space is described by networks of these loops, called spin networks. These spin networks are mathematical structures that represent the quantum states of space. The intersections of the loops represent tiny, discrete volumes of space, while the lines connecting them represent discrete areas. This means that quantities like area and volume are not continuous, but can only take on specific quantized values, much like energy levels in an atom. As these spin networks evolve over time, they form spin foams, which are like the four-dimensional history of a spin network, representing the quantum evolution of spacetime itself. This dynamic aspect is where time too becomes quantized, existing in discrete steps rather than a continuous flow. One of the significant implications of loop quantum gravity is its potential to resolve the singularity problem in general relativity. General relativity predicts that at the center of black holes and at the moment of the Big Bang, spacetime becomes infinitely curved and dense, leading to a singularity where the laws of physics break down. Loop quantum gravity, by quantizing space, suggests that there is a minimum possible size for space. This means that densities and curvatures cannot become infinite. Instead of a singularity at the Big Bang, loop quantum gravity models often predict a big bounce. In this scenario, the universe did not begin from an infinitely dense point, but rather from a previous contracting universe that reached a minimum size and then bounced into expansion. This offers a continuous history for the universe, avoiding the problematic singularity. Unlike some other approaches to quantum gravity, such as string theory, loop quantum gravity does not require extra spatial dimensions beyond the three we observe, nor does it propose new fundamental particles. Its focus is on quantizing gravity itself, rather than quantizing matter fields on a smooth spacetime background. It treats spacetime as a dynamic quantum entity from the outset. The theory is built upon a reformulation of general relativity that expresses gravity in terms of variables related to connections and loops, which are then quantized using techniques from quantum mechanics. This leads to a picture where gravity is not a force acting in space, but rather a manifestation of the quantum geometry of space itself. Despite its conceptual elegance and potential to address fundamental problems, loop quantum gravity is still a theoretical framework under active development. It faces significant mathematical and conceptual challenges. One major challenge is to fully recover classical general relativity at large scales from its quantum description. Another is to make testable predictions that can be verified through experiments or astronomical observations. Currently, the effects predicted by loop quantum gravity are so tiny, occurring at the Planck scale, that they are far beyond the reach of present-day experimental technology. However, researchers are exploring possible observable signatures, such as subtle deviations from general relativity at very high energies or specific imprints in the cosmic microwave background radiation from the early universe. The development of loop quantum gravity represents a significant effort to unify our understanding of the universe at its largest and smallest scales. By proposing that space and time are fundamentally granular, it offers a radical new perspective on the fabric of reality, suggesting that the smooth continuum we perceive is merely an approximation that holds true at scales much larger than the Planck length. This quantum nature of spacetime could hold the key to unlocking the deepest mysteries of gravity, black holes, and the very beginning of the universe. Time is a fundamental aspect of our existence, yet its true nature remains one of the most profound and elusive questions in physics and philosophy. We experience time as a continuous flow, moving irrevocably from the past, through the present, and into the future. We measure it with clocks, organize our lives around it, and perceive it as an ever-advancing sequence of events. However, modern physics suggests that time might be far more complex and less intuitive than our everyday experience suggests. In classical physics, as described by Isaac Newton, time was considered an absolute and universal quantity. It was thought to flow uniformly and independently of anything else, like an invisible river that courses through the universe, affecting everything but being affected by nothing. In this Newtonian view, clocks everywhere would tick at the exact same rate, and the concept of now would be universally agreed upon. Space was also absolute, a fixed, unchanging stage upon which events unfolded. This simple, intuitive picture of time held sway for centuries. However, the early 20th century brought a revolutionary change with Albert Einstein's theories of relativity. His special theory of relativity, published in 1905, showed that time is not absolute, but is relative to the observer's motion. This means that time can pass at different rates for different observers, a phenomenon known as time dilation. If you're moving very fast relative to someone else, your clock will tick slightly slower than theirs. This effect is minuscule at everyday speeds, but becomes significant at speeds approaching the speed of light. The special theory of relativity also introduced the concept of spacetime, a four-dimensional fabric where space and time are interwoven. Events are not just located in space or in time, but in spacetime. Einstein's general theory of relativity, published in 1915, further complicated our understanding of time by showing that gravity also affects time. This is known as gravitational time dilation. Clocks tick slower in stronger gravitational fields. For example, a clock at the top of a tall building ticks slightly faster than a clock at the bottom, because the gravitational pull is slightly weaker at higher altitudes. This effect is crucial for technologies like the Global Positioning System, or GPS, which must account for both special and general relativistic time dilation to maintain accuracy. These relativistic effects demonstrate that time is not an independent entity, but is intimately linked to space, motion, and gravity. The concept of a universal now ceases to exist. What is simultaneous for one observer may not be simultaneous for another. When we delve into the realm of quantum mechanics, the picture of time becomes even more perplexing. At the quantum level, where particles behave in probabilistic and often counterintuitive ways, time does not seem to play the same role as it does in classical or relativistic physics. There is no clear time operator in standard quantum mechanics, which makes it difficult to define the progression of events in the same way we do in the macroscopic world. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that time itself might branch, with different realities unfolding in parallel. The phenomenon of quantum entanglement, where two particles remain connected regardless of distance, also challenges our classical notions of time and locality. One of the most radical ideas about the nature of time comes from attempts to unify general relativity and quantum mechanics into a theory of quantum gravity. Some of these theories suggest that time might not be a fundamental aspect of reality at all, but rather an emergent property. This means that time, as we perceive it, might arise from more fundamental, timeless interactions at the Planck scale. For example, in some formulations of loop quantum gravity, the equations describing the universe do not explicitly contain a time variable. This leads to the problem of time, where the universe appears timeless at its most fundamental level. In this view, our experience of time's flow could be an illusion or a macroscopic phenomenon that emerges from the underlying quantum structure of spacetime, similar to how temperature emerges from the collective motion of countless atoms. The concept of time also changes dramatically when we consider the extreme conditions of the early universe. According to the Big Bang theory, time itself began with the Big Bang, approximately 13.8 billion years ago. Before this event, the very notion of before loses its meaning, as time and space as we understand them did not exist. This implies that time is not an eternal backdrop, but rather a property that came into existence with the universe itself. This idea is incredibly challenging to grasp, as our minds are accustomed to thinking of time as always having been there. The possibility of extra spatial dimensions, as proposed by theories like string theory and M theory, also introduces new considerations for time. If our universe is a three-dimensional brain embedded in a higher dimensional bulk, then the flow of time might be different or more complex in the bulk. It's possible that what we perceive as time in our dimension is just a slice or projection of a higher dimensional reality. However, These ideas are highly speculative and currently lack experimental verification. One of the most intuitive yet puzzling aspects of our experience is that time always moves forward. We remember the past, we live in the present, and we anticipate the future. We never observe events unfolding in reverse, nor do we spontaneously remember future events. This unidirectional flow of time is known as the arrow of time. While the fundamental laws of physics, which describe how particles interact and forces behave, are almost entirely symmetric with respect to time, meaning they would work just as well if time ran backward, our macroscopic world clearly exhibits a preferred direction for time. The key to understanding this arrow lies in the concept of entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that in any closed system, the total entropy can only increase or stay the same. It can never decrease. This law is not a fundamental force like gravity or electromagnetism, but rather a statistical law. It means that systems naturally tend to move from states of order to states of disorder, because there are simply many more ways for things to be disordered than ordered. For example, if you drop a glass, it shatters into many pieces, increasing its disorder. You never observe shattered pieces spontaneously reassembling themselves into a whole glass. An ice cube melts in a warm room, increasing the disorder of water molecules. It never spontaneously refreezes by drawing heat from the room. These are irreversible processes, and their irreversibility is tied directly to the increase of entropy. The arrow of time in this context is the direction in which entropy increases. The universe itself can be considered a vast evolving system, and its overall progression is governed by the second law of thermodynamics. Cosmologists refer to this as the cosmological arrow of time. The Big Bang theory suggests that the universe began in an incredibly low entropy state, meaning it was highly ordered and uniform. From that initial hot, dense, and remarkably smooth state, the universe has been expanding and evolving, leading to the formation of stars, galaxies, and complex structures. This process of structure formation, while appearing to create order locally, like a galaxy forming, actually contributes to the overall increase in the universe's entropy. For instance, stars convert nuclear fuel into energy, increasing the disorder of their atomic nuclei, and eventually die, spreading their matter and energy into space. The expansion of the universe itself contributes to increasing entropy by spreading matter and energy over larger volumes, leading to a more disordered distribution. The universe is moving from a state of low entropy to a state of higher entropy, and this progression defines the direction of cosmic time. Beyond the thermodynamic arrow, there are other arrows of time that generally point in the same direction. The psychological arrow of time refers to our subjective experience. We remember the past but not the future. Our brains are structured to record and process events as they happen, creating memories that are stored and retrieved. We build our understanding of the world based on these past experiences, allowing us to predict future events, but we do not have direct access to future information. This psychological arrow is deeply intertwined with the thermodynamic arrow, as the formation of memories and the functioning of our brains are complex processes that also involve an increase in entropy. The radiative arrow of time refers to the fact that waves, such as light waves or sound waves, always spread outwards from their source rather than converging inwards. When you drop a pebble in a pond, ripples expand outwards. You never see ripples spontaneously converging to form a splash. Similarly, light from a star travels outwards into space. It does not spontaneously converge from all directions to illuminate a star. This outward propagation of radiation is also linked to the second law of thermodynamics, as it represents a dispersal of energy and an increase in disorder. The causal arrow of time states that cause always precedes effect. A cause must occur before its effect. For example, striking a match causes a flame. The flame does not appear before the match is struck. This fundamental principle of causality is essential for our understanding of how events unfold and how the universe operates. If effects could precede causes, the universe would be chaotic and unpredictable, and our ability to understand and interact with it would be impossible. This arrow is also deeply connected to the thermodynamic arrow, as the processes that lead to cause and effect relationships generally involve an increase in entropy. The remarkable consistency among these various arrows of time all pointing from past to future, suggest a deep connection to the universe's overall evolution from a low-entropy state. If the universe were to eventually reverse its expansion and begin to contract in a hypothetical Big Crunch, some speculative theories suggest that the arrow of time might also reverse, leading to a decrease in entropy. However, current observations, particularly the discovery of accelerating expansion, driven by dark energy, suggest that a Big Crunch is unlikely. Instead, the universe appears destined for a big freeze or heat death, where it expands indefinitely, becoming increasingly cold, dilute, and disordered, eventually reaching a state of maximum entropy, where no further work can be done and all processes cease. In essence, while the microscopic laws of physics do not distinguish between past and future, the macroscopic behavior of the universe, driven by the relentless increase of entropy, defines the unmistakable direction of time. This fundamental asymmetry is what gives time its flow, shaping our experience of reality and dictating the irreversible progression of all events in the cosmos. For a long time, we have believed that humans are the first and only intelligent beings to live on Earth, building cities, inventing technology, and sending machines into space. But what if that idea isn't the full story? What if, long before us, another advanced civilization lived on this planet, smart, powerful, and now completely gone? Is it possible that something rose and fell millions of years ago, leaving behind strange objects, tools, carvings, or buildings we don't understand? Could the Earth have quietly hidden their story under layers of time, just waiting for someone to ask the right question? The Silurian hypothesis is a bold and fascinating idea that challenges everything we think we know about human history. It asks a deep and surprising question. What if human beings are not the first intelligent civilization to rise on Earth? What if, millions of years before us, there was another advanced society, one that built technology, explored science, and maybe even reached for the stars, only to vanish completely, leaving behind little or no trace? This hypothesis was introduced by two scientists, astrophysicist Adam Frank and planetary scientist Gavin Schmidt. They wondered whether Earth might have once been home to intelligent life forms long before humans ever appeared. If such a civilization existed, could all signs of their presence have been wiped away by nature itself? By volcanic eruptions, earthquakes, erosion, rising seas, or changes in climate over tens of millions of years? Unlike traditional archaeology, which focuses on the rise of human civilizations over the past few thousand years, this idea stretches far beyond our known history. It dares us to consider that civilization itself might not be unique to humanity. Perhaps it is something that has happened more than once during Earth's 4.5 billion year history. At the heart of this hypothesis is a simple but powerful idea. Maybe humans are not the first, and maybe we are not the only intelligent life to walk this planet. If another civilization once existed millions of years ago, most of their buildings, cities, and machines would likely have crumbled away. Natural processes, like shifting tectonic plates, rising mountains, eroding coastlines, and even asteroid impacts, could have erased nearly all signs of them. That's why scientists looking into this possibility aren't just searching for statues or ruins. Instead, they're hunting for more subtle, indirect clues. These might include unusual chemical traces buried in rocks, strange layers in ancient sediments, or odd patterns in the Earth's isotopes, tiny atomic fingerprints that might suggest past industrial activity. Finding such hints is difficult, but not impossible. The big problem is that Earth's geological record, the layers of rock and sediment that tell the story of our planet, is incomplete. Over millions of years, much of it gets crushed, melted, or recycled by nature. Regular archaeology depends on objects like tools, pottery, and bones, things that rarely survive beyond a few 100,000 years. So, if a civilization lived on Earth, say 50 million years ago, almost everything they built would be gone. That's why the Silurian hypothesis encourages a different approach, one that brings together many branches of science. It's not just about digging up old objects, it's about combining geology, chemistry, climate science, and even computer simulations to search for deeper clues buried in Earth's history. This theory doesn't just challenge how we search for the past, it also asks us to rethink what we mean by civilization. It opens up big questions. How long can a technological society survive? Do civilizations rise and fall like waves over time? Could our own be one in a long series of many? And what happens when a civilization collapses? Does it leave any mark that survives? Exploring these questions forces us to rethink not just the past, but also the future. If other intelligent species once lived on Earth, and if they vanished without a trace, what might that say about us? Thinking about civilizations that might have existed before humans isn't just science fiction. It has real value for scientists and archaeologists. It helps us question long-held assumptions and expand our understanding of how life and intelligence evolve over time. For a long time, historians and scientists believed that civilization followed a straight path. Early humans formed tribes, then cities, then built machines, and finally reached the modern world. This story made it seem like humans were the only ones ever capable of creating complex societies and advanced technology. But the Silurian hypothesis flips that idea on its head. If a civilization rose and fell millions of years ago, we might not find stone buildings or metal tools. Instead, we would need to look for subtle signs, like strange chemical residues, odd rock patterns, or even unexpected minerals that might suggest industrial processes. These traces might be buried deep underground or hidden in the ocean floor. Finding such signs would be one of the biggest discoveries in human history. It would force us to rewrite everything we know about life on Earth. It would also raise new questions. How long did that civilization last? What caused it to collapse? Could the same thing happen to us? And there's another layer to this story, one that goes beyond science. The idea that humans might not be the only intelligent beings ever to live on Earth shakes up our sense of importance. For centuries, people have believed that we are the center of everything. From ancient religious teachings to Enlightenment science, humanity has often been seen as unique, special, even destined to rule the world. This belief was reinforced by the complexity of human language, culture, and technology. It made it seem unlikely that any other species, on Earth or elsewhere, could match our intelligence. And because we've never found strong evidence of alien civilizations or pre-human ones, many assumed they didn't exist. But as our tools grow more advanced, and as we learn more about the history of our planet, that confidence is beginning to fade. New discoveries in fields like astrobiology, planetary science, and deep-time geology suggest that we may have been too quick to dismiss other possibilities. The Silurian hypothesis encourages us to be open-minded. It reminds us that intelligence might not look like we expect. It could arise in forms and places we've never imagined. And if civilizations can come and go, here on Earth or out in the stars, it's worth asking, what will future beings think of us? Will we leave behind anything they can find? The belief that humans are special has been with us for a very long time. During the Renaissance and the Enlightenment, roughly between the 15th and 18th centuries, science began to flourish. People started using careful observation and logical thinking to understand the world. But even as knowledge grew, many still saw humans as the center of everything. Back then, people believed Earth was the center of the universe, a view known as the geocentric model. Even when that idea was proven wrong, another belief took its place, that humans were the most intelligent and important species in the universe. Our ability to build cities, speak languages, and develop advanced technologies seemed to prove it. Some of these beliefs also came from religious or philosophical ideas. Many thought humans were specially created, set apart from all other creatures. Others believed that if intelligent life existed elsewhere, it would either be very different or far less advanced than us. Another reason people believed in human uniqueness was the lack of evidence for anything else. We hadn't found any signs of alien civilizations, nor had we found clear proof of intelligent life on Earth before us. From a scientific point of view, this possibility pushes researchers to look more carefully at the clues left behind in rocks, fossils, and ancient layers of the Earth. Our current tools, like radiometric dating and stratigraphy, which studies the layers of the Earth, are designed to detect natural changes over time. But what if there were traces of advanced technology buried deep underground? signals so faint or so unusual that we simply overlook them or mistook them for something natural. Scientists may need to go back and examine the fossil record, layers of sediment and chemical compositions in a new way, looking for things that might have been built or shaped by intelligent hands. These signs could be tiny, hidden, or damaged by time. Over millions of years, metal might rust away, buildings might be crushed or buried, and only strange patterns or chemical leftovers would remain. The big question is, could the remains of a long-lost civilization be hidden so deeply or eroded so badly that we can no longer recognize them? From a philosophical standpoint, the idea is just as powerful. If intelligent life once rose and fell on Earth before us, it would mean we're not necessarily the first or the only beings to reach a high level of knowledge and technology. That thought humbles us. It suggests that perhaps the rise of intelligence is not a rare miracle, but something that could happen again and again when the right conditions come together. It also makes us think more deeply about the nature of progress. Are civilizations like ours a natural outcome of evolution on Earth-like planets? Or are they rare and fragile, doomed to collapse after reaching a certain point? Could it be that other civilizations once existed here, achieved great things, and then vanished, leaving behind only hints that we're just now beginning to consider? This idea also raises important questions about how long technology can last. Would the machines, tools, or buildings of an ancient civilization survive for tens of millions of years? Or would nature destroy them so completely that we would never even know they were there? If an ancient civilization changed the Earth's climate or left behind chemicals in the soil, could we detect those changes today? All of this ties into bigger ongoing conversations about life beyond Earth. The Silurian hypothesis, a name given to this idea by scientists Adam Frank and Gavin Schmidt, connects the possibility of ancient Earth civilizations with the search for intelligent life elsewhere in the universe. It opens up exciting questions. If ancient intelligent life once existed on our planet, could other planets also have gone through similar cycles? Could life appear, rise to greatness, and disappear again and again throughout the galaxy? The hypothesis makes us look differently at both archaeological mysteries and stories from ancient cultures. For example, what if the strange leaps in ancient technology or the sudden appearance of complex knowledge in early societies were echoes of something older? Could myths of lost worlds like Atlantis or Lemuria be distant memories of real places that once existed, civilizations so old that they were forgotten by history? The Silurian hypothesis also encourages scientists to study ancient ruins and puzzling artifacts more carefully. Are some of these things really just the work of early humans? Or could they be misunderstood remains of something much older, perhaps even non-human? This idea challenges the traditional belief that all stories of gods, sky people, or vanished cities are just myths. What if some of them are based on real events from a time long before our own? Ancient cultures such as the Sumerians and Egyptians offer stories that hint at this possibility. The Sumerians, one of the oldest known civilizations, believed that their knowledge came from gods who descended from the sky. The Egyptians spoke of a time of chaos that was brought into order by divine beings, ideas that suggest something existed before humans, or at least before known history. On the other hand, many traditional stories describe history as starting with human beings, and moving in a straight line of progress from simple to advanced. Religious texts often describe a moment of divine creation, after which human history begins, leaving no room for earlier intelligent life. These stories seem to reject the idea of civilizations before our own. Still, there are legends and mysterious archaeological discoveries that keep the debate alive. Plato's famous story of Atlantis describes an advanced society that vanished beneath the sea. While many scholars see it as symbolic, others wonder if it could be based on a real place lost in time. Monumental structures like the Great Pyramids of Egypt or Stonehenge in England raise similar questions. Did ancient people really build them with the tools we think they had? Or did they inherit knowledge from a much older, forgotten source? Mainstream scientists are often cautious and prefer to see these ancient stories as myths or metaphors, not literal history. But the Silurian hypothesis invites us to stay open-minded. Instead of ignoring ancient tales or unexplained findings, perhaps we should take another look, with better tools and fresh thinking. To carefully test the idea behind the Silurian hypothesis, the suggestion that an advanced civilization may have existed on Earth long before humans, scientists turned to three major fields: geology, paleontology, and archaeology. Each of these scientific disciplines brings a different set of tools and knowledge to help us explore the incredibly long and complex history of our planet. Geology is the first and most fundamental field. Geologists study the layers of rocks, the minerals they contain, and how these layers are arranged over time. This gives us a timeline of Earth's past that stretches back for billions of years, far beyond anything written in human records. One of the most powerful tools geologists use is radiometric dating, which helps them figure out how old rocks are. For example, they can examine volcanic ash trapped between rock layers and use isotopes, tiny versions of elements that change over time, to tell exactly when that ash fell. This lets scientists build a reliable timeline of Earth's events. Now, imagine they discover something strange buried deep in the Earth: unusual mineral layers, massive disruptions in ancient rocks, or signs that something extremely hot once passed through. These oddities, if they don't match known natural processes, could be clues, hints that perhaps, long ago, some intelligent beings might have done something on this planet that left a trace. Paleontology, the study of ancient life through fossils, adds another piece to the puzzle. Paleontologists usually look at how life has changed and evolved by studying bones, shells, and imprints left in stone, but they also keep an eye out for anything odd, like a sudden change in fossil types, or something buried in a sediment layer that doesn't seem to belong, such as tiny manufactured-looking objects or materials with strange patterns. If these are not natural, they could suggest that intelligent life may have existed long before us, and left behind clues of their technology or impact. Archaeology, often thought of as the study of ancient human civilizations, can also look much deeper into the past when it turns its focus to very old, unexplained objects or materials. Modern tools like spectroscopy, electron microscopes, and chemical analysis help archaeologists figure out if a material was made naturally or created by intelligent beings. If scientists ever discover strange metals, unique alloys, or synthetic compounds in ancient rocks, especially in layers dating back millions of years, it might suggest the work of a long-lost civilization. These three fields, geology, paleontology, and archaeology, come together to form a powerful, multidisciplinary way of looking for signs of ancient civilizations. By combining rock timelines, fossil records, and possible artifacts, scientists look for patterns that don't make sense under current theories. And because this method uses multiple types of evidence, it helps make sure that any claims of a past advanced civilization are supported by strong scientific proof, not just wild guesses. If such proof ever did appear, it would mean we'd have to seriously rethink everything we thought we knew about life on Earth. The scientific process is designed to be very careful and skeptical, making sure any unusual discovery is not just the result of natural processes. But if something truly unexpected were found, something that points to a real, intelligent civilization from long before humans, it would be one of the most important discoveries in all of science. If the Silurian hypothesis turned out to be true, and we learned that a civilization as advanced as ours, or even more advanced, existed on Earth millions or even hundreds of millions of years ago, it would completely change how we see ourselves. Right now, most people believe that humans are the first and only species on Earth to build cities, create technology, and explore space. But if another intelligent species had already done something similar long ago, it would show that advanced life might not be as rare as we think. It could mean that the forces of evolution may have produced smart, tool-using beings more than once on this planet. This would also make us question just how stable and safe our planet really is. If an earlier civilization once existed and then disappeared, perhaps because of war, climate change, or a natural disaster, what does that say about our future? Could the same thing happen to us? If they changed the planet's surface by mining, building huge structures, or causing environmental damage, and that damage can still be seen today, it would suggest Earth remembers what we do for a very long time. It would raise serious questions about how long civilizations like ours can survive, and how carefully we need to treat the world we live in. In addition, proving this hypothesis could change our ideas about how long Earth has been a suitable home for life. It might suggest that Earth has gone through cycles, times when it supports complex life, and times when it resets due to catastrophe. That means civilizations could rise, fall, and disappear entirely, only to be replaced by others much later. These ups and downs would force scientists to look again at how Earth's climate, ecosystems, and life forms respond to major changes, and how often. What if an advanced civilization once lived on Earth long before humans, and all that's left of it are faint clues buried deep in the ground? Unlike modern humans, who leave behind buildings, roads, and machines, such a long-lost civilization might have vanished so completely that we would only find the faintest traces, clues hidden in the rocks, sediments, and minerals beneath our feet. To uncover these traces, scientists must look very closely at the Earth's geological layers, like detectives searching for a mystery buried in time. Geology, the study of Earth's layers, and related sciences like archaeology and chemistry can help us find possible evidence. But instead of clear signs like ancient tools or monuments, we might only find strange patterns in the way soil and minerals were deposited. These patterns are small and subtle, but they could tell us if something unusual once happened, something caused not by nature, but by intelligent beings. One of the biggest clues is found in sediment layers. Normally, over thousands or millions of years, dirt, sand, and other particles settle into layers. But sometimes, these layers don't look normal. They're too thick, mixed up, or made of strange materials. That can be a sign of something unnatural. Maybe large machines moved the Earth, or a civilization mined and reshaped the land. For example, if we find layers full of processed materials, like metal particles, building waste, or synthetic substances that don't belong in nature, it could mean someone was once living and building there. These materials might include special metal mixtures, alloys, or waste from factories, things that nature doesn't make on its own. Another important clue comes from chemistry, especially when scientists look at isotopes. Isotopes are versions of chemical elements with different weights, and they usually appear in natural ratios. But if these ratios are suddenly off, say, there's too much of one kind of lead or copper, it might mean that something or someone was messing with them. That someone could be a civilization using technology, like metalworking or chemical processing. These shifts in isotopic ratios act like chemical fingerprints, showing that something unusual happened in that location. If found in the same place as strange sediments or odd minerals, they build a stronger case that something artificial might have occurred long ago. Minerals can also carry important secrets. Natural processes usually create minerals in predictable ways, but sometimes scientists find minerals that look like they were formed under extreme heat or pressure, not from volcanoes, but possibly from furnaces, kilns, or factories. Imagine finding early ceramics or melted rocks stuck inside ancient sediments. Those could be leftovers from old technologies, like pottery or smelting. Some minerals might even look like industrial waste, such as slag or fused glass, which wouldn't naturally form in that environment, unless someone had created them. When we put all these clues together, strange sediment layers, unusual isotopes, and weird mineral formations, they begin to tell a story. It's like reading a hidden chapter of Earth's history, one that may point to a forgotten civilization. But this kind of research is tricky. Earth has changed a lot over the last several billion years. Volcanoes have erupted, continents have shifted, oceans have risen and fallen, and meteorites have smashed into the ground. All these events can bury or erase evidence, or even make natural things look like they were created by intelligent life. One of the biggest problems is that nature can sometimes make things that look like human artifacts. For example, certain minerals might form patterns that resemble tools or structures. Without context, it's easy to make a mistake and think something natural is man-made, or miss a real artifact because it's too damaged or hidden. Real evidence of ancient civilizations might be so worn down or buried so deep that it's hard to recognize. Some artifacts may have chemically changed over millions of years. That's why scientists have to be very careful. They use advanced techniques like high-resolution imaging, chemical testing, and stratigraphic analysis, studying rock layers, to figure out whether something is natural or artificial. This work often brings together many fields: geology, archaeology, chemistry, and even physics to piece together the puzzle. Earth has also gone through major disasters. Massive volcanic eruptions, asteroid impacts, and sudden climate changes can destroy entire regions. These events could have wiped out any early civilization and buried whatever evidence they left behind under thick layers of ash or rock. Sometimes, these disasters even create confusing signals. For instance, a layer of volcanic ash might look like a man-made concrete floor, or melted rocks from an asteroid impact might resemble industrial waste. Scientists must untangle these clues to find out what really happened. Fortunately, today's scientists have powerful tools to help them. They can use satellite images, 3D scans of rock layers, and isotopic dating to look deep into Earth's past. Radiometric dating, for example, helps tell how old a layer of rock or sediment is, sometimes down to the exact year, even if it's hundreds of millions of years old. These tools help experts figure out if something unusual in the geological record is due to nature, or possibly the work of intelligent beings. One especially interesting place to search is in and around old impact craters. When a giant asteroid or comet hits the Earth, it makes a huge crater and sends debris flying everywhere. These craters can preserve unusual materials, like melted rock, glassy minerals, or rare metals, for hundreds of millions of years. If a civilization had existed during the time of an impact, the debris from that civilization might be buried along with the asteroid fragments. For example, if scientists found processed metals or synthetic materials in the same layer as an ancient impact, it could hint that intelligent life was around when the event happened. Sometimes, nature itself can help preserve the secrets of the past, especially when something dramatic happens to the planet. Huge volcanic eruptions or powerful earthquakes can completely change landscapes and bury everything in their path. These kinds of events don't just destroy, they also help preserve. When a supervolcano explodes, for example, it can spread ash across entire continents. This thick layer of ash settles and becomes part of the rock layers deep underground. Scientists can trace these ash layers across different parts of the world, almost like reading pages in a giant book of Earth's history. Now, imagine if an ancient civilization had existed before or during one of these massive eruptions. Their tools, buildings, or even traces of their presence, like changes in soil or strange chemical patterns, might have been buried under all that ash. Over tens of thousands or even millions of years, those layers could harden and protect whatever is trapped beneath them, keeping evidence of forgotten technologies safely hidden inside the Earth's crust. Planet-wide disasters like asteroid impacts or violent geological shifts can also affect the climate. These changes might speed up the decay of certain materials, but they might also create perfect conditions for preserving them. For example, the extreme heat and pressure caused by a giant impact could form very unusual minerals. If scientists ever find those minerals in strange places, especially alongside other odd discoveries, it might be a sign of something more than just natural activity. It might point to the presence of a civilization that came and went long before humans. As we dig deeper into Earth's past, these natural disasters start to look like both destroyers and time capsules. They can wipe out civilizations, but also freeze pieces of their world in time. That's why many researchers are asking new questions. Could the sediments at the bottom of the oceans or the layers of ancient ice near the poles hold hidden clues? Could these natural archives contain traces of a high-tech civilization that vanished long before recorded history began? Deep-sea sediments and thick ice cores are like Earth's memory banks. They hold information about our planet's environment going back hundreds of thousands to millions of years. These natural records offer scientists a unique way to look far beyond the reach of archaeology or written history. If any advanced society once walked the Earth long before humans, these hidden archives might be the best places to find proof. At the bottom of the oceans, sediments build up slowly over time. These layers contain a mix of mineral dust, bits of dead organisms, and microscopic fossils. Buried in this mix, researchers might find strange chemicals, rare minerals, or unexpected metals. For example, very high levels of gold, platinum, or rare earth elements, much more than what would occur naturally, could suggest activities like mining or metalworking carried out by some long-lost civilization. In much the same way, cores of ancient ice taken from Antarctica or Greenland are also incredibly valuable. These ice cores trap layers of ash from old volcanoes, tiny particles from the air, and even pollution. Scientists can study these layers and look for artificial chemicals, like man-made industrial gases or synthetic pollutants. If any of these are found in ice layers that are far older than modern civilization, it could suggest that someone long ago had the technology to create such substances. To find such tiny clues, scientists use extremely precise tools. Techniques like mass spectrometry, isotope analysis, and synchrotron radiation allow them to detect the smallest traces of unusual materials. These techniques can even tell the difference between minerals that form naturally and those that might have been shaped or changed by technology. For instance, strange isotopes found in an ice core or sediment layer might reveal that someone, millions of years ago, was building things or processing materials in a way that nature alone would not produce. Because of this, deep-sea sediments and polar ice cores are now seen as some of the most powerful tools for uncovering the mysteries of ancient technology. They help us build a detailed timeline and allow us to match strange findings with specific moments in Earth's past. When combined with modern scientific techniques, these layers might reveal evidence of civilizations that vanished long before humans ever walked the Earth. But to truly understand what we're seeing in these ancient records, we also need to know when things happened. That's where the science of geochronology, dating the age of rocks and minerals, becomes incredibly important. Without accurate dating methods, strange discoveries could be misunderstood or wrongly placed in the timeline of Earth's history. Geochronology is the science that helps us put dates on ancient rocks, ash layers, and mineral changes. One of the most trusted methods is radiometric dating, which looks at how radioactive elements inside rocks slowly break down over time. For example, uranium-lead dating is often used to determine the age of zircon crystals in volcanic ash. These crystals can be over 1 billion years old. When scientists find unusual materials or patterns in the same layers as these crystals, dating can help figure out if those things might be signs of technology from an earlier time. Another technique, known as argon-argon dating, is especially useful for studying volcanic eruptions. It helps place a precise date on the ash layers that might contain buried artifacts or unusual materials. Thermochronology, which measures how long it has been since a rock cooled down, can show when rocks were uplifted or buried, events that might explain how ancient structures came to be hidden or destroyed. Newer methods like isotope geochemistry also let scientists study changes in the environment. By looking at shifts in the ratios of certain isotopes, like those of carbon or oxygen, scientists can detect major changes in climate or atmosphere. If those changes seem to match patterns we see today from industrial activity, they might be a clue that something similar happened long ago. However, using these dating tools correctly takes great care. Not every unusual pattern means a lost civilization existed. Nature can create strange things too. That's why scientists must always check the context in which materials are found, what's around them, what layer they came from, and what other clues are nearby. Even though modern geology has greatly improved our understanding of Earth's incredibly long and complex history, it still has some big challenges, especially when it comes to finding signs of civilizations that might have lived on Earth before humans. These challenges mainly come from how slow and powerful geological processes are, and how they constantly change the surface of our planet. Because of this, discovering any traces of ancient non-human civilizations becomes a very difficult task. One of the biggest problems is time itself. If such ancient civilizations did exist, they might have lived millions or even hundreds of millions of years ago. Over such huge stretches of time, many clues they may have left behind, such as tools, buildings, or even changes in the environment, could have been erased, buried, or hidden by natural forces. The Earth is always changing due to erosion, shifting tectonic plates, volcanic eruptions, and layers of sediment building up. These powerful forces can completely wipe out weak or temporary signs of ancient life. For example, if a civilization used mostly wood, plant fibers, or other materials that break down easily, it's unlikely that much would survive after so many millions of years. In addition to that, the scientific tools we use to study the Earth's past have their limits. Methods like radiometric dating, isotope analysis, and studying layers of rock, known as stratigraphy, are great at helping scientists figure out the age of fossils, rocks, and other materials, but only up to a certain point. These methods become less reliable the farther back in time we go, especially when we're talking about hundreds of thousands or even millions of years. So if there was an early intelligent civilization during one of these distant time periods, we might not be able to detect it very clearly, if at all. Another challenge is that not all evidence is straightforward. Sometimes clues from ancient civilizations could be indirect, like unusual chemical patterns in minerals, strange types of sediment, or odd mixes of isotopes. These might look like natural changes at first glance. It takes a very trained and careful scientist to notice when something might actually be the result of intelligent activity. But often, these subtle clues are overlooked or dismissed because they don't stand out enough. There's also something called preservation bias. This means that certain places on Earth are much better at preserving ancient things than others. Dry caves, deserts, and areas with very stable conditions are good at keeping evidence safe for a long time. But places with water, heavy rain, or lots of volcanic activity tend to destroy or wash away artifacts quickly. So if an ancient civilization lived in one of these harsh environments, there's a good chance we'd never find their remains. Because of all these difficulties, even though our scientific tools are powerful, they still give us only a partial view of Earth's deep past. This opens up a fascinating idea. Could it be possible that traces of an ancient civilization were erased by nature or hidden beneath the surface of the Earth? Or even more dramatically, could the traces have been wiped out by giant cosmic events? This is where things get even more interesting. Scientists and thinkers have long been fascinated by the idea that events from outer space, like massive asteroid strikes, exploding stars, called supernovae, or intense radiation bursts, might have changed the course of life on Earth. These huge events have the power to destroy entire ecosystems, reshape the surface of the planet, and possibly even erase all signs of civilizations that once existed. One of the most famous examples is the asteroid that hit Earth around 66 million years ago. This giant impact caused what scientists call the Cretaceous-Paleogene extinction event, which led to the extinction of the dinosaurs. But it didn't just affect animals. That impact changed the Earth's environment, climate and surface in enormous ways. It left behind a special layer of material filled with the rare metal iridium, as well as shocked quartz and a huge crater. These are things that scientists can still find in rocks today. But if an intelligent civilization had existed before that asteroid hit, the impact might have completely buried their cities and artifacts under thick layers of debris or turned them into different kinds of rock through heat and pressure, making them almost impossible to recognize. Other powerful space events could have had similar effects. For example, a nearby supernova or a gamma-ray burst, huge explosions of energy in the universe, could have blasted Earth with radiation. That radiation might have destroyed the ozone layer, changed the climate for thousands of years, and made it much harder for life to survive. Any technology or structures from a civilization existing at the time might have been broken down by harsh weather, rising oceans, or fast erosion. And these space disasters don't just happen on their own, they can cause other events too. An asteroid strike, for instance, could set off volcanic eruptions, giant earthquakes, or long-term climate changes. These follow-up effects could further destroy or bury signs of civilization. This makes things even harder for scientists and archaeologists who are trying to figure out what Earth was like in its distant past. All of this shows us that cosmic events could play a major role in hiding or erasing the evidence of ancient civilizations. But here's the twist. They also leave their own clues behind. So while these disasters might cover up ancient footprints, they also leave marks in the rocks that scientists can study, like craters, special chemical layers, and changes in the Earth's surface. By learning how to read these marks more carefully, we might one day uncover signs of intelligent life that lived long before us. And that leads us to a new and even more intriguing question. What do fossils tell us about the possible existence of ancient civilizations that were not human at all? Fossils are like time capsules buried in stone, precious records that give us a window into Earth's incredibly ancient past. They help scientists piece together the story of life on our planet, showing how living things have changed and evolved over millions and even billions of years. Normally, fossils are thought to be the remains of once living creatures, plants, animals, or tiny microbes. But sometimes, strange and puzzling fossils are found that don't quite fit this idea. These rare finds raise fascinating questions. Could some of these unusual fossils point to something other than biology, perhaps the remains of ancient technology, or even long-lost civilizations that existed before humans? One especially curious group of fossil discoveries includes unusual mineral patterns and microscopic structures that are very hard to explain through normal biological processes. In some cases, researchers have found fossilized shapes that look incredibly precise and geometric, symmetrical patterns and complex structures that are rarely seen in nature. For example, some microstructures buried in rock look almost like they were carefully built, with patterns that repeat and shapes that resemble parts of machines more than tissues of living organisms. Some of these even have intricate, repeating tree-like or fractal designs, which are not common in known biological fossils. Even more surprising are the tiny bits of metal or carbon found within layers of ancient sediment that resemble man-made objects. Some of these inclusions have surfaces that are smooth and regular, layered like composites, or even look like miniature assemblies of parts. These features are hard to explain with what we know about how fossils form. In fact, if we find fossil-like objects that have very fine grooves, perfect circles, sharp edges, or tiny holes that look like they were made with tools, especially if they're found right next to regular biological fossils, it naturally leads us to wonder, were these things made by someone or something intelligent? Another interesting direction scientists are exploring involves strange chemical and elemental clues locked inside rocks. For example, some fossils contain elements or metal alloys that don't usually form through normal geological processes. Some materials look like they've been heated or altered in ways that suggest they went through some kind of industrial process. These chemical fingerprints might point to artificial origins, especially if they're found together with the geometric or structural anomalies mentioned earlier. Sometimes, researchers even find markings carved or scratched onto fossilized shells or bones, markings that seem too precise and too regular to be caused by nature alone. When these engravings look like symbols, patterns, or artificial designs, they could hint at craftsmanship, tools, or perhaps machines. This possibility opens up an entirely new way of thinking about Earth's history. What if, long before humans ever appeared, some other intelligent beings walked this planet? Of course, most fossils show clear signs of biological life, such as shells, bones, or the shapes of leaves and roots. But every now and then, scientists come across something that stands out, something that seems different, as if it doesn't belong. These unusual fossils may contain hints that intelligent design or technology once existed on Earth in the deep past. One possible clue is the presence of mineral structures that look like manufactured parts. These might include repeating patterns that mimic circuits, layered designs that resemble artificial materials, or even tiny lines and shapes that suggest machines. Some researchers have discovered microfractures that seem to follow exact shapes or directions, as well as metals that look like they were mixed or engineered, rather than naturally formed. In some rare cases, fossils seem to include structures that resemble microelectronic circuits, which is hard to explain using just biology or geology. Another promising area of study focuses on fossils that come from microbial mats, or ancient slime-like layers left behind by colonies of tiny organisms. If these structures are arranged in neat layers, with clear symmetry or other signs of organization, they might point to something more than just natural microbial growth. Some of these fossilized mats even contain strange chemical signals, such as unusual combinations of elements or unnatural isotopic ratios, which might suggest the presence of non-biological materials. This could support the idea that something artificial was at play. But there's a big challenge. How do we tell the difference between a real anomaly and a natural oddity? Sometimes the process of fossilization itself can change the shape or chemistry of a fossil, making it look stranger than it really is. That's why scientists now use powerful tools to study these mysteries. Advanced microscopes, special radiation scanners, and chemical analysis methods allow researchers to zoom in on fossils at the microscopic or even nanoscopic level, revealing details so tiny that they can't be seen with the naked eye. If any features discovered through these methods clearly don't match what nature would normally produce, it could be a strong sign of ancient technology or intelligent activity. All of this leads us to a bigger question. Could these tiny fossil clues, especially the ones too small to see without powerful equipment, actually reveal signs of advanced biological or even technological processes. The study of microfossils, fossils that are smaller than a millionth of a meter, is a fascinating field. These tiny remains can be found in rocks that are thousands, millions, or even billions of years old. Microfossils have helped scientists learn about the earliest forms of life, long before plants and animals appeared. Traditionally, these fossils were thought to represent very simple life forms like bacteria or algae. But recent discoveries suggest that even these early organisms might have had more complex behaviours than we thought. For example, some microfossils appear to have organised shapes, with cells that seem to work together or form networks, like early versions of biofilms or microbial communities. This could mean that even the simplest forms of life were already developing ways to cooperate, share resources, or communicate, traits we usually associate with more advanced life. Chemical studies of these microfossils have also turned up surprising results. By measuring the types of carbon or sulfur isotopes trapped inside them, scientists can sometimes tell what kind of metabolism the ancient microbes used. Some of these isotopic ratios match what we see in modern microbes that live in extreme environments, such as those that perform photosynthesis, or survive in high heat or acidity. This suggests that early life may not have been so basic after all. It might have included a range of sophisticated behaviours and adaptations that we're only just beginning to understand. Some researchers even propose that certain microfossils might show signs of ancient technology or artificial influence. For instance, if a fossil contains metal, layered materials, or tiny structures that look like tools or circuits, it could mean that these early microbes were interacting with their environment in ways that resemble engineering or design. While these ideas are still debated, they encourage scientists to look more closely at the tiniest traces of the past. The discovery of ancient life, whether simple microbes or more complex organisms, opens an exciting window into Earth's distant past. It helps scientists understand how life may have begun and how it slowly changed and evolved over billions of years. But these discoveries also bring along many puzzles. Figuring out what these fossils really are and where they came from is not always easy. In fact, sometimes it's like trying to solve a mystery with only half the clues. Some of the oldest traces of life on Earth come from fossils of microscopic organisms, often preserved in rocks as tiny mineral threads or in layered structures called stromatolites. These ancient formations are among the earliest signs of life, and some may be more than 3 billion and 500 million years old. That means life may have appeared on our planet not long after Earth itself formed. But because these fossils are so small and simple in shape, scientists often struggle to tell whether they are truly biological remains or just patterns created by natural non-living processes. For example, certain minerals can form shapes that look very much like tiny colonies of microbes, making it difficult to say for sure whether they were once alive. The challenge becomes even more complicated when we look at fossils of more advanced creatures, such as soft-bodied animals or the earliest examples of multicelled life. These fossils may have complex shapes and fine details that suggest life was already quite advanced at an early stage in Earth's history. But interpreting these fossils is tricky. Over time, the way organisms decay and how their remains get preserved in rock can change their appearance. This process, known as taphonomy, can make it hard to tell what the original creature looked like, or even whether it was ever alive in the first place. Sometimes, what looks like a fossil may turn out to be a mineral formation that just happened to take on a lifelike shape. Another important part of this puzzle is the rock layer or stratum in which a fossil is found. Scientists study the layering of sediments to understand the age and origin of fossils, but even this can be misleading. Mineral-rich water can move through rock and leave behind deposits that form patterns similar to those made by living things. These purely geological formations, though formed by natural forces like pressure and chemical reactions, can closely mimic biological shapes. As a result, researchers must be extremely cautious when they come across fossil-like features. They may not always be what they seem. To solve these mysteries, scientists rely on very precise and careful methods. They use tools like high-powered microscopes, chemical tests, and isotopic analysis, which looks at the types of atoms in a sample, to search for biosignatures, clues that a sample came from a living organism. These clues might include certain types of molecules or unusual ratios of atoms that are hard to produce without biological processes. Still, even with all this technology, it's possible to get false positives, samples that look biological but actually aren't. That's why experts from many different scientific fields must work together to investigate these ancient traces of life. Their job is not just to examine the fossils, but also to understand the bigger picture, where they were found, how they were formed, and what they might mean. But what if some of these fossils aren't just signs of life? What if they're signs of something much more advanced? What if, hidden deep within the layers of rock, there are clues pointing to the existence of civilizations that lived long before humans ever walked the Earth? This fascinating idea brings us to an even more difficult challenge. Some scientists and thinkers have wondered whether certain unusual structures in the fossil record could actually be ancient tools, machines, or even parts of advanced technologies, but trying to tell the difference between natural mineral formations and artificial human-made objects from deep time is extremely difficult. Many naturally occurring processes, like crystal growth, pressure, or chemical changes, can create shapes that look surprisingly like artifacts. For example, some mineral concretions, rounded stone formations, or fossilized microbial films can look very much like carved surfaces, gears, or mechanical parts. One of the biggest problems is that nature itself can be very good at creating patterns and shapes that look designed. Crystals, for example, can grow in perfect geometric shapes, with straight lines and sharp angles. These shapes can easily be mistaken for tool marks or machine parts. Even microbial colonies, when fossilized, can form repeating textures that look like they were made by intelligent hands. That's why scientists must use many different types of analysis, such as ultra-detailed imaging, chemical fingerprinting, and microscopic inspection, to figure out what they are really looking at. There's another major problem too: time. If a civilization existed hundreds of millions, or even billions of years ago, then whatever it left behind would likely be deeply buried, eroded, or changed beyond recognition. Over such long periods, even strong materials like metal or stone can be broken down, crushed, or transformed by heat and pressure. Without clear signs, like tool marks, carvings, or a grouping of objects that obviously don't belong, it's almost impossible to tell whether a strange structure in the rock is natural or not. Adding to the confusion, Earth still holds many geological secrets. Some rock formations and structures that we find today don't fit into current scientific explanations. These unexplained formations could simply be rare natural events, but they might also be something more. That's why scientists are encouraged to be both cautious and open-minded, using every tool available to investigate these mysteries. They look closely at the shapes, materials, and surroundings of each discovery, asking whether it truly came from nature or from a forgotten hand. This line of thinking leads to a captivating question. Could there be fossilized remains of ancient machines, tools, or technologies buried within the Earth? Although this idea is highly controversial, it's not entirely out of the question. Some fossil-like objects found in sedimentary rocks have sparked debate because they show patterns that are symmetrical, precise, and complex, traits we normally associate with tools or machines. In some cases, scientists have even found metallic-looking inclusions, tiny pieces inside fossils, that under a microscope seem to have patterns resembling gear teeth, hinges, or other mechanical components. If any of these features were proven to be real artifacts, it would rewrite everything we know about Earth's history and humanity's place in it. But before jumping to conclusions, scientists must consider simpler explanations. Many of these shapes can still be explained by natural processes, such as the way minerals grow and settle over time. Some silicate crystals, for instance, naturally form in shapes that can look like screws, bolts, or parts of a mechanism. And over millions of years, even real metal would likely corrode or be replaced by minerals, making it even harder to identify. Equally important is context. A single strange object found in isolation doesn't prove anything. But if similar objects were found at multiple sites, with signs of advanced activity like worked surfaces, artificial alignment, or unnatural materials, the case would become much stronger. So far, however, no such discovery has been confirmed beyond doubt, and that brings us to the heart of the mystery. Could the fossil record, the grand archive of life on Earth, contain hints not just of plants and animals, but of civilizations that lived and vanished long before our own? The fossil record is one of the most important tools scientists use to study the ancient history of Earth. It gives us a way to look far back in time, millions and even billions of years, to understand how life has changed and evolved. But when scientists try to use the fossil record to search for signs of civilizations that may have existed long before humans, they run into many difficulties. While some clues might support the idea of such civilizations, many others raise doubts or are too unclear to prove anything for sure. Fossils usually form when hard parts of living things, like bones, shells, or teeth, are buried and preserved over time. But this process is very picky. It does not preserve everything. Soft materials such as wood, fabric, or even the remains of technology like wires or tools rarely survive long enough to become fossils. That means if an ancient civilization left behind things made of soft materials or delicate machinery, those items would almost never be found in fossil form today. This makes it much harder for scientists to detect signs of complex, possibly advanced societies that may have lived before humans. Even when strange findings do show up, like odd-shaped structures in rocks or layers of minerals that don't quite fit the usual patterns, they are often explained away as natural, not artificial. Many scientists are cautious and tend to dismiss these discoveries if they resemble things that nature could have created on its own. Some unusual mineral patterns or strange arrangements of sediments might actually be clues, but they are often too subtle for our current tools to recognize, and without clear, solid artifacts like tools, buildings, or inscriptions, it is very difficult to prove that these are the results of intelligent activity. On the other hand, the fossil record does offer a few curious hints that could support the idea of pre-human civilizations. For instance, the sudden appearance of certain kinds of minerals or the presence of unexpected tiny fossils, called microfossils, in certain rock layers might point to large changes in the environment. These changes could have been caused by advanced life forms doing things like mining, building cities, or using energy on a large scale. However, these signals are vague. It's hard to tell if they came from natural processes, like volcanoes or climate changes, or from intelligent beings doing something purposeful. In general, while the fossil record gives us amazing snapshots of life's long journey on Earth, it does not clearly support the idea of ancient advanced civilizations before humans. There are no unmistakable, well-preserved signs of such societies, and the lack of strong evidence shows how important it is to improve the ways we search. If we want to find subtle or hidden signs of ancient intelligence, we need better tools and new ideas. This leads us to wonder, what new methods could help us search deeper into the past and possibly uncover signs of civilizations we've never known? Thankfully, scientists are now developing exciting new technologies that may help us find what has long been hidden. Traditional fossil hunting methods often rely on what can be seen on the surface or dug up in shallow layers, but modern techniques are going far beyond that. One powerful method is called ground-penetrating radar, or GPR. When combined with special three-dimensional imaging, it lets scientists see what's underground without digging anything up. These tools can detect buried structures or shapes that might be old buildings or roads, even if they're covered by many layers of earth and rock. When artificial intelligence is added to the process, computers can quickly scan massive amounts of data and point out anything that looks unnatural or possibly man-made, saving researchers lots of time and effort. Another breakthrough is called spectral imaging. This technology looks at objects using many different kinds of light, not just what we see with our eyes, but also infrared and ultraviolet light. This helps scientists detect chemicals or materials that may have been used by intelligent beings. For example, certain paints, metals, or synthetic materials leave behind clues in the way they reflect light. Spectral imaging can be done from planes, drones, or satellites, allowing researchers to scan entire landscapes that are too remote or dangerous to visit in person. Scientists are also using advanced forms of isotope analysis. One such method, known as clumped isotope thermometry, can measure the temperature and chemical conditions that existed when certain rocks or fossils formed. If these temperatures don't match what we'd expect from natural processes, it could suggest something unusual happened, possibly related to intelligent activity, like machines, industry, or artificial heating. Another helpful tool is micro-CT scanning, which creates extremely detailed, three-dimensional pictures of very small objects trapped inside rocks. This lets scientists see fine details, like tiny tool marks or layers that look like they were carefully built, without destroying the sample. It can help identify possible signs of craftsmanship or technology that are too small or fragile to examine by hand. All these high-tech tools are opening up new possibilities for finding out what really happened on Earth in the very distant past. Sometimes, archaeologists discover strange objects or structures that don't seem to fit with what we think we know about human history. These unusual findings, often called archaeological anomalies, raise big questions. They challenge our usual understanding of the past and make us wonder, could another, possibly non-human civilization have existed on Earth long before us? These strange clues come in many forms. Some are ancient tools or artifacts that seem too advanced for their time. Others are massive stone structures that show an incredible level of skill, far beyond what early humans were believed to be capable of. When we take a closer look, some of these discoveries seem to have been made using knowledge or technology that shouldn't have existed yet, at least not according to our current timeline of history. One of the most fascinating mysteries is the existence of ancient structures that appear to be built with astonishing precision. In many places around the world, we find huge stone buildings and monuments that are perfectly aligned with the stars or the sun, something that would have required an impressive understanding of astronomy and engineering. But here's the twist. These structures were built thousands of years before modern civilizations were thought to have this kind of knowledge. Take, for example, the massive stone monuments found in places like Egypt, South America, or Southeast Asia. Some of these are not only massive in size, but also built with geometric precision that still amazes engineers today. How did ancient people, without modern machines or computers, manage to carve, move, and align such gigantic stone so perfectly? Could they have had help? Or could they have inherited this knowledge from a civilization that came long before them? The mystery deepens when we find metal objects or materials that seem completely out of place. In some ancient layers of Earth, layers that are tens of thousands or even millions of years old, archaeologists have unearthed metallic tools, advanced alloys, and even synthetic materials that, according to our textbooks, shouldn't have existed back then. In some cases, these materials have unusual isotopic signatures or contain traces of substances that we don't yet fully understand. Could these be the leftovers of lost knowledge, or even signs of technological processes that go far beyond anything early humans were capable of? If so, where did that knowledge come from? Then there are the even stranger discoveries. Carved stones marked with symbols that don't match any known language or culture, and tools or objects with no clear purpose or origin. These items often seem to come from nowhere, showing a level of craftsmanship or intent that doesn't align with any ancient culture we know. Some objects appear to have been machined with great precision, or bear markings that look more like those made by industrial tools than by hand chisels. These mysteries suggest the presence of an intelligence, maybe even a civilization, that operated with a level of knowledge far ahead of its time. Other strange findings involve structures built in places that seem almost impossible to reach or work in. For example, there are perfectly straight roads stretching over rough mountains and deep valleys, and underground chambers carved into solid rock with no clear entry point or explanation for how they were made. Some of these underground structures are so vast and complex that they baffle modern engineers. Could they have been made by an advanced species, perhaps one that wasn't human, using tools and technologies that we no longer possess or understand? All of these discoveries, when looked at together, are like pieces of a puzzle. They don't fit neatly into the story we've been told about human history, that we evolved slowly over time, building up our knowledge little by little. Instead, they hint at the possibility that our past may be far more mysterious, layered, and complex than we ever imagined. What if long before the dawn of recorded history, a technologically advanced civilization, maybe even non-human, walked this Earth? What if we are only now beginning to uncover their fingerprints, hidden deep beneath layers of time? Mainstream archaeology teaches that modern human civilization began around 10,000 years ago, slowly growing from simple farming communities into complex societies. But the strange and out-of-place artifacts mentioned above cast serious doubt on that tidy timeline. Some of these discoveries, such as tools, carvings, or metals found in ancient rock layers, seem far older than they should be. Others show a level of skill and precision that early humans supposedly didn't have. These clues suggest that something is missing from our current understanding, possibly even an entire chapter of history that has been forgotten. Many of the strangest objects can't be properly dated. Others seem to have been made using advanced machining or metallurgy techniques that shouldn't have been available at the time. Could this mean that some ancient cultures were far more advanced than we think? Or could these be remnants of a civilization that existed long before humans, perhaps even one that we have no record of at all? Some scientists have even proposed bold ideas like the Silurian hypothesis, which asks, what if a smart industrial civilization existed on Earth millions of years before humans and vanished without a trace? If this is true, some of the strange items we've found might be their leftovers, left behind like forgotten tools in an ancient workshop. These oddities don't just challenge our ideas of the past, they also expose potential weaknesses in our methods. What if the tools we use to dig up history are missing some of the most important clues? What if we've already found signs of the lost civilizations but brushed them off because they didn't fit the story we expected? If we open our minds to new possibilities, we might begin to see that the past isn't a straight line. It's more like a maze, filled with twists, turns, and secrets still waiting to be uncovered. Some of the world's most famous ancient monuments might hold hidden meanings if we look at them through the lens of this idea. Structures like the megalithic stone circles in Europe, the giant stone heads of Easter Island, and the pyramids of Egypt have long puzzled experts and inspired wild theories. Take Göbekli Tepe, for example, a site in modern-day Turkey believed to be the oldest known megalithic structure in the world, built more than 11,000 years ago. Its towering stone pillars are decorated with carved animals and strange symbols, but what's truly shocking is that it seems to have appeared suddenly in the archaeological record, with no earlier examples to explain its origin. Did this knowledge come from an older civilization that we no longer remember? Or consider the Nazca lines in Peru, giant drawings carved into the earth, only visible from the sky. How did ancient people make such massive figures without being able to see them from above? Could this hint at knowledge of aerial viewing, possibly handed down from an older and more advanced society? Even the Egyptian pyramids and the temples of Malta are full of mysteries. Their perfect alignments with stars, their strange internal acoustics, and the size of the stones used suggest a kind of engineering that may have been far ahead of its time. Some of the world's most mysterious and awe-inspiring ancient structures might offer important clues that challenge what we think we know about history. These giant buildings, often called megastructures, are not like the usual ruins we find from ancient times. They are enormous, incredibly precise, and sometimes seem to have been built with skills or knowledge that don't match the time periods we associate them with. For example, at several ancient sites around the world, massive stone blocks have been carefully fitted together without using any kind of cement or mortar. These stones are not only gigantic, but also perfectly aligned, sometimes with the stars or the sun, showing a deep understanding of mathematics and astronomy. Stone circles, huge terraces, and water-carrying systems known as aqueducts seem to show that the people who built them had an advanced grasp of engineering, possibly beyond what we thought was possible for ancient civilizations. What makes these ancient structures even more fascinating is the level of planning, skill, and possibly even machines involved in building them. In some places, enormous stones were carved with incredible precision and moved across long distances, something that would be very hard to do even today without powerful tools. Some researchers believe that the builders may have used advanced materials, like early types of concrete or artificial stone, which seem too modern for the times they came from. These ideas suggest that knowledge or technologies might have existed in the past, but were forgotten over time. In some cases, the way these buildings were made is so strange that it raises even more questions. Multiple layers of different materials, complex shapes, or buildings that don't seem to serve any clear purpose might mean they had symbolic, religious, or astronomical meanings. This suggests that the people behind these structures were not only skilled builders, but also had a rich and complicated culture. All of this leads to a bigger mystery. Could there have been earlier civilizations, possibly even global ones, that were far more advanced than we thought? And if so, what happened to them? Many of these ancient wonders are located in places that are now underground or underwater. These hidden places might hold the answers to questions about civilizations that came long before our own, and then vanished without a trace. That's where the Silurian hypothesis comes in. This is the idea that an advanced civilization might have existed on Earth millions of years ago, long before modern humans. If such a civilization did exist, its remains might now be buried beneath layers of Earth or submerged deep under the ocean. Underground and underwater archaeological sites are especially important because they can protect ancient ruins from erosion, looting, and other types of damage. These sites might contain old tools, buildings, or even remains of cities that have been sealed off for thousands or even millions of years. For instance, underground tunnels and buried cities could hold clues about lost technologies, while sunken settlements beneath the sea might show signs of intelligent life that lived during a forgotten chapter of Earth's history. Some researchers believe that entire cities may have been swallowed up by rising sea levels or major disasters, leaving behind only ruins hidden below the waves. Discoveries like these could totally change how we see human history, and possibly reveal that intelligent beings lived on Earth long before us. But finding these lost sites isn't easy. Earth is a huge place, and natural processes like earthquakes, landslides, and the slow movement of soil can cover up or destroy evidence. Traditional digging methods can't reach many of these places. That's why scientists now rely on powerful modern tools to help them explore. Two of the most important technologies being used today are ground-penetrating radar, GPR, and LiDAR, short for light detection and ranging. Ground-penetrating radar works by sending radio waves into the ground. When those waves hit something underground, like a buried wall, a hidden tunnel, or even an ancient object, they bounce back. The radar picks up the echoes and creates images of what's below the surface. This helps archaeologists know where to dig and what to look for, without having to dig up everything blindly. LiDAR is another amazing tool. It uses laser beams, usually from a drone or airplane, to scan the ground from above. These lasers can see through thick forests and other obstacles that normally hide ancient ruins. By measuring how long it takes for the laser light to bounce back, LiDAR creates detailed 3D maps that show even small changes in the landscape, like old roads, building outlines, or hidden pyramids. Some lost cities have already been found using this technology in places like Central America and Southeast Asia. These high-tech tools allow scientists to explore huge areas quickly, safely, and in great detail, something that would take years to do by hand. They also help researchers compare sites in different countries, uncovering patterns and similarities that might point to a shared global culture that existed long ago. However, even though GPR and LiDAR are incredibly powerful, they come with their own challenges. The amount of data they produce is massive, and interpreting it takes skill and experience. Sometimes it's hard to tell the difference between man-made objects and natural formations, and even when something strange is discovered, scientists still need to prove how old it is, who made it, and what it was used for. That brings us to the next big question. Once we find something unusual, how do we know it's real, and how do we figure out how old it is? These are the puzzles that researchers must solve if we are ever to uncover the true story of Earth's ancient past. Could it be that long before modern humans walked the Earth, another intelligent civilization built wonders that now lie hidden, waiting to be rediscovered, trying to prove whether strange-looking artifacts are real, and figuring out exactly how old they are is one of the hardest tasks researchers face. This is mainly because today's scientific tools, though powerful, have their limits, and the objects themselves are often mysterious and difficult to study. One major problem is telling the difference between truly ancient items made by intelligent beings and modern copies or naturally formed objects that just look like they were crafted by someone. Sometimes, even rocks shaped by wind or water over thousands or millions of years can resemble man-made tools or structures. Scientists use a variety of methods to date artifacts and determine their origins. Techniques like radiocarbon dating, thermoluminescence, and stratigraphic analysis can offer clues about how old something is or what layer of Earth it came from. But none of these methods are perfect. they rely on certain assumptions, like the idea that specific chemical elements or layers in the soil have remained unchanged over time. Unfortunately, environmental conditions, contamination, or movements in the ground can disturb these layers or chemical traces, making the results unclear or even misleading. Things get even more complicated when the artifact in question doesn't fit into what we currently understand about ancient history. Objects with strange shapes, unusual materials, or unknown construction methods are often met with deep skepticism. Some scientists might quickly dismiss them as natural rocks or modern fakes. However, unless these conclusions are supported by strong evidence, such as dating from multiple techniques, consistent placement in undisturbed soil layers, or nearby related artifacts, the verdict remains uncertain. The task becomes even more difficult when the object is broken, worn down, or has been affected by natural forces like wind, water, or volcanic activity over tens of thousands or even millions of years. Adding to the challenge is the fact that nature itself can sometimes produce shapes that closely resemble crafted tools or ornaments. Certain rock formations, mineral crystals, or even hardened lava flows can, at a glance, look like carved stones or pieces of machinery. These misleading shapes can easily be mistaken for human-made artifacts. To tell the difference, scientists have to study the object carefully, using knowledge from geology, the study of Earth's layers and rocks, mineralogy, the study of minerals, and how natural formations develop over time. Experts often examine these questionable objects under powerful microscopes, perform chemical tests to identify what they're made of, and use 3D scanning to search for signs of carving or shaping. Real artifacts tend to show signs of deliberate work, like straight cuts, repeated patterns, smooth surfaces, or marks left by tools. In contrast, natural objects usually have uneven, jagged, or chaotic patterns caused by natural forces like erosion, crystal growth, or underground pressure. One of the most important parts of figuring out if an object is real is its context, where it was found and what was found around it. If the object was buried in the same soil layer as other ancient items like stone tools, pottery, or bones, then it's more likely to be real. But if it was found all alone or in a disturbed area, then scientists have to be much more cautious. It's also important to study the local geology. Knowing the history of nearby volcanoes, rivers, or rock formations helps researchers decide whether something was likely made by nature or by intelligent hands. High-tech tools are becoming more helpful in this detective work. Spectroscopy, for instance, can reveal what kind of materials the object is made from, and whether they match those found in known human tools. 3D scanning and even electron microscopes can uncover tiny details, like scratch marks from tools or grooves from shaping, that the human eye can't see. When scientists combine all these methods with the knowledge of archaeologists, chemists, and geologists, they can build a much clearer picture of what the object truly is. Climate change and shifts in the environment have played a powerful role in shaping the story of human history, and perhaps even the hidden stories of civilizations that came before us. These natural forces act like both protectors and destroyers. Sometimes they help preserve traces of the past. Other times they wipe the evidence away completely, leaving behind only whispers buried deep in the earth. On the one hand, nature can be an incredible guardian of history. Certain conditions, like fast burial under mud or sand during floods, the cold and airless environment of peat bogs or deep caves, or being sealed in ice or covered by volcanic ash, can protect ancient objects and even human remains for thousands of years. A famous example of this is Ötzi the Iceman, who lived over 5,000 years ago. His body was found frozen in the Alps, perfectly preserved by the cold. In other places, entire towns have been covered by ash from volcanic eruptions, freezing them in time and giving us rare, detailed snapshots of life in the distant past. But nature can also act as a great eraser. Enormous changes like ice ages have dramatically reshaped the Earth. Thick ice sheets can grind down landscapes, crush artifacts, and erase whole coastal settlements as sea levels rise and fall. Glaciers can scoop up or bury ancient remains and move them far from where they were originally left. Volcanic eruptions, while sometimes preserving things, can also destroy everything in their path, burning, burying, or scattering what remains of past civilizations. The oceans have their role too. When sea levels rise, Entire coastal cities can be swallowed, hiding all evidence underwater. When the sea retreats, it can reveal sunken lands that were once thriving settlements. These powerful natural events are like a double-edged sword. They can either protect ancient secrets for thousands, or even millions of years, or they can erase them completely. That's why understanding how the Earth's environment changes is so important to archaeologists and geologists. These forces shape what we can find, what survives, and how we interpret the story of civilizations long gone. This constant push and pull between preservation and destruction sets the stage for deeper questions. How have past ice ages, volcanic eruptions, and oceanic shifts shaped our ability to discover forgotten civilizations? Could there be entire chapters of Earth's history missing simply because nature swept them away? Let's look more closely at how some of these forces work. During ice ages, which have happened many times over millions of years, massive sheets of ice stretch across continents. These glaciers can act like natural freezers, preserving objects and remains in the frozen ground. But as they move, these glaciers also act like bulldozers, flattening the land, crushing artifacts, and dragging debris over great distances. When the ice finally melts, it can wash away what little is left, or leave evidence jumbled and scattered. In some areas, the weight of the ice pushes the ground down and distorts the natural layering of soil and rock, making it much harder for scientists to figure out the age and origin of what they find. In places that were not covered by ice, sea levels during ice ages dropped dramatically. This revealed land bridges, like the one that once connected Asia to North America across what is now the Bering Strait. These exposed lands made it possible for people, and possibly earlier civilizations, to migrate across continents. But when the Ice Age ended and sea levels rose again, many of those areas were drowned, possibly taking entire settlements with them. Volcanoes add another layer of mystery. When they erupt, they can quickly bury entire towns and forests in volcanic ash or lava. The ash, called tephra, can cover everything in a thick blanket, freezing a moment in time. This can sometimes preserve things with incredible detail, almost like a natural time capsule. But future eruptions, earthquakes, or erosion can later disturb or even destroy these delicate layers, scattering the evidence. Volcanic landscapes themselves constantly shift, which complicates scientists' efforts to analyze what lies beneath. The oceans also play a massive role in what we find and what we lose. Over time, sea levels have risen and fallen by hundreds of feet. When the sea rises, it swallows up coastlines and floods cities, hiding them under layers of silt and coral. When the sea recedes, it can reveal lost lands, like ancient river valleys or shorelines that once hosted thriving communities. The movement of Earth's crust, through a process called tectonic activity, can lift entire regions out of the sea or cause them to sink, messing with the layers of sediment that archaeologists depend on to date what they find. Altogether, these forces create a constantly changing picture of Earth's surface. Some areas may protect ancient clues for tens of thousands of years, while others may bury or destroy them without a trace. This makes the job of finding civilizations that existed before humans, or alongside early humans, a huge challenge. To solve these ancient mysteries, scientists must read Earth's layered history like a detective, sifting through a book with missing pages. Some scientists and thinkers have asked, what if natural disasters didn't just shape history, but completely erased parts of it? Could civilizations that existed long before us have been destroyed so suddenly and completely that hardly any trace remains? We know that environmental disasters have caused major collapses in human societies, but for civilizations that may have existed before us, or early in human history, these events could have had even more dramatic effects. Take, for example, the Younger Dryas, a sudden period of intense global cooling that started around 12,900 years ago. This dramatic shift in climate may have devastated early farming communities and forced entire groups to abandon their homes. Even earlier, about 74,000 years ago, the Toba supervolcano erupted in what is now Indonesia. That eruption was one of the largest in Earth's history and may have triggered a global volcanic winter. Some scientists believe it caused a massive drop in human population, a bottleneck that could have affected both human evolution and the survival of other possible civilizations. Asteroid impacts are another terrifying force. The most famous one happened around 66 million years ago, when a huge asteroid hit Earth near the Yucatan Peninsula. This event, known as the Chicxulub impact, is believed to have wiped out the dinosaurs. If an impact like that happened during the time of a pre-human civilization, it could have ended it almost instantly, crushing cities, destroying food sources, and plunging the world into chaos. But not all disasters wipe everything out at once. Some might weaken a civilization gradually, setting off a chain reaction of problems. A drought could lead to failed crops, which might cause conflict, war, or migration. Over time, the society might fall apart, not with a bang, but with a slow unravelling. Two very basic natural processes, sedimentation and erosion, also shape what survives from the ancient world. Sedimentation is when layers of sand, mud, and organic materials slowly build up over time. In quiet places like lake bottoms or calm river valleys, these layers can gently cover and protect artifacts like tools, bones, or even entire structures. In such calm and stable environments, things can stay preserved for tens of thousands of years. Erosion, though often seen as destructive, plays a double role in the world of archaeology. On one hand, it wears away soil and rock over time, which can damage or destroy ancient sites. But on the other hand, it can also be a powerful tool of discovery. As erosion slowly removes layers of Earth, it sometimes uncovers objects and structures that had been hidden underground for thousands of years. What was once buried and forgotten can suddenly come to light, giving us exciting glimpses into the distant past. Places like coastal cliffs, riverbanks, and steep mountain slopes are especially important in this process. These natural landscapes often act like nature's own digging tools. As rain, wind, and water do their work over centuries, they strip away the surface and reveal traces of ancient human life, tools, pottery, bones, and even forgotten dwellings. In this way, erosion doesn't just destroy history, it also helps us find it. But erosion doesn't work alone. It constantly interacts with another powerful natural force, sedimentation, the slow build-up of materials like mud, sand, and minerals that get deposited over time. These layers can cover and protect ancient remains, or sometimes change the environment around them. When minerals mix with the buried materials, they can help preserve them by turning them into stone, a process called mineralization. However, not all chemical reactions are helpful. In some cases, the wrong soil conditions can speed up decay. For example, soil that's very acidic can break down wood, bone, and other organic materials much faster. In contrast, soil that's more neutral or slightly alkaline can keep these remains in good condition for thousands of years. Understanding how erosion and sedimentation work is incredibly important for archaeologists. These processes don't just influence whether artifacts survive, they also affect where those artifacts end up and how easy they are to find. When archaeologists learn to read the signs left behind by erosion and sedimentation, such as unusual soil layers, patterns in the landscape, or exposed artifacts, they can better decide where to dig and how to interpret what they find. But there's another important factor that can hide or reveal traces of ancient civilizations: natural resource deposits. These include things like coal seams, underground water, aquifers, and mineral-rich veins of rock. These deposits can act like both guardians and gatekeepers of history. Sometimes they hide human activity deep underground, and other times they bring it to the surface. For instance, when ancient people mined for minerals or used natural resources, they often left behind clues. These clues might be disturbed rock layers, strange shapes in the ground, or even leftover materials from smelting or tool making. Today, scientists can detect these subtle signs using advanced tools like geochemical analysis, which helps them spot changes in mineral content caused by human activity. In some cases, these resource deposits have actually protected ancient items for thousands of years. Imagine an old mine or a peat bog that preserved wood, cloth, or even human remains so well that they still look nearly untouched today, like nature's time capsules. However, these same deposits can also bury or distort archaeological layers over time, making it harder to tell whether a structure or formation is natural or human-made. Interestingly, areas rich in natural resources were often magnets for early human settlements. People were drawn to these places for their useful materials, like metal ores or fresh water. But mining and other resource-gathering activities often disturbed or destroyed the very evidence archaeologists now search for. Artifacts might be pushed deeper into the ground or broken apart. Still, in some special environments like peat bogs or salty mineral-rich lakes, even fragile materials like fabric or rope can survive for ages. All of this shows why it's so important for experts in different fields, from geology to chemistry to archaeology, to work together. Only by combining their knowledge can they fully understand how natural deposits affect the discovery of ancient sites. Recognizing the role of geology helps researchers figure out where to dig and how to explain what they find. And sometimes, it even helps them uncover parts of our past that would otherwise stay hidden. To take this search even further, scientists now turn to a powerful modern tool, climate models. These models help researchers predict where evidence of lost civilizations might be hiding by showing how Earth's climate has changed over tens of thousands of years. By simulating ancient weather patterns like rainfall, temperature, and wind, these models can identify areas that once supported human life but are now covered by deserts, forests, or oceans. For example, a region that is dry and lifeless today might once have been a green and fertile valley with rivers, crops, and villages. Using paleoclimate data, which includes ancient pollen, ice cores, and sediment records, scientists can recreate what the world looked like in different periods. This helps archaeologists focus their efforts on places where ancient people most likely lived, even if those places are now hidden under sand, soil, or snow. One especially helpful way climate models are used is in combination with satellite images and ground-penetrating radar. These technologies can detect signs of human-made structures, like ancient roads, canals, or cities buried beneath the surface. When combined with climate models, they offer a clearer picture of where and when these structures were built, and why people may have left them behind. These models are not static. They improve over time, using new information from biology, geology, and climatology to paint ever more accurate pictures of the past. With these tools, researchers can even identify short-lived climate windows, periods when the environment was just right for human civilization to grow and thrive. Knowing when and where these windows opened up helps archaeologists search smarter, not harder. But the story doesn't end with the past. In fact, future climate change could open up entirely new possibilities and pose serious new risks for archaeology. As global temperatures continue to rise, ice sheets are melting, seas are rising, and weather patterns are changing across the globe. These environmental changes are already reshaping the Earth's surface, sometimes exposing long-hidden sites, and other times damaging fragile remains. For instance, when glaciers melt in places like the Arctic or the Alps, they may reveal astonishingly well-preserved ancient settlements, tools, clothing, and even mummies that were frozen in time. Yet, once these remains are exposed to air and sunlight, they can start to decay rapidly. In other areas, stronger storms and heavier rains may wash away or bury ancient layers of civilization, while new patterns of drought and heat may dry out regions that were once rich in vegetation and water. These changes could lead to better preservation in some dry places, but make exploration harder in others. In places like deserts or frozen tundra, once seen as poor candidates for archaeological study, shifting climate conditions may suddenly make these areas more promising. However, they also come with new complications like salty soil or melting permafrost, both of which can harm ancient artifacts and make excavation more difficult. That's why archaeologists today are racing against time. They know that climate change is altering the Earth in unpredictable ways, and many fragile pieces of human history might soon be lost forever. That's also why it's more important than ever to combine the power of climate science with archaeology, using every available tool to locate, study, and preserve the past before it disappears. Studying how Earth's environment has changed in the past gives us deep and powerful lessons about how human civilizations have survived, or sometimes failed, through the centuries. Many ancient societies such as the Maya in Central America and the people of ancient Mesopotamia in what is now Iraq had to deal with major challenges like changing weather patterns, running out of natural resources, and powerful natural disasters. These struggles often led to serious problems for those societies, sometimes even to their collapse or transformation. These historical stories remind us of a powerful truth. No civilization, no matter how advanced or complex, is completely safe from the forces of nature. One of the most important lessons we learn from the past is the value of being able to adapt. Civilizations that were able to survive tough environmental changes usually found smart ways to adjust. They changed how they farmed, managed their water and forests more carefully, or even reorganized their social systems to better handle the new challenges. On the other hand, societies that ignored the warning signs, like long droughts or damaged soil, often could not survive. A clear example is the fall of the classic Maya civilization, which seems to be linked to major shifts in the climate and the destruction of forests. This shows how environmental stress, when combined with poor responses, can push a society toward disaster. Another key lesson is that long-term planning and taking care of the environment are absolutely essential. Many ancient civilizations did not have the ability, or sometimes the wisdom, to plan for the future. They used up their resources too quickly, and when trouble came, they were unprepared. This led to social breakdowns and even the disappearance of entire cultures. Today, we see similar problems happening again. Climate change, the overuse of fossil fuels, deforestation and pollution are putting modern societies at serious risk. By studying how earlier civilizations collapsed, we are reminded just how important it is to build a future based on sustainability and smart preparation. Interestingly, not all environmental crises led to doom. In many cases, hard times pushed people to become more creative. When faced with droughts, floods, or food shortages, ancient people often came up with new tools, better farming methods, or even new religious beliefs to make sense of their world and survive. These moments of change show the amazing ability of humans to find hope and progress, even when things seem bleak. In the end, looking at how ancient civilizations dealt with environmental changes teaches us that the survival of any society depends on its ability to adapt, to think ahead, and to live within the limits of nature. This is more than just a lesson from history. It is a warning and a guide for our own time. If we truly want modern civilization to last, we must take care of our planet, think for the long term, and be ready to change when needed. As we think about all this, a fascinating question comes to mind. What if ancient civilizations also existed long ago and disappeared just like the Maya or Mesopotamians? And how does this connect with the ongoing search for intelligent life beyond Earth, the work of SETI, the search for extraterrestrial intelligence? Could the rise and fall of ancient human, or even non-human civilizations help us understand what might be happening on other planets? Trying to find the remains of machines or infrastructure built by an ancient civilization isn't as simple as digging in the dirt and hoping to find a gear or a metal pipe. Over thousands upon thousands of years, most surface artifacts are either buried deep underground, destroyed by erosion, or broken down by time. However, a very clever and careful scientist can look for something much harder to erase. Strange patterns hidden in the Earth's electromagnetic fields, gravity, and even in the way sound waves travel through rock. These hidden clues, though invisible to the naked eye, may serve as signs left behind by a long-lost technological world. One of the most exciting types of evidence is called an electromagnetic anomaly. This refers to strange behavior in the Earth's natural electric or magnetic fields. If an ancient civilization once built machines, power grids, or communication systems on a large scale, those activities would have left behind unnatural electromagnetic fingerprints. For example, ancient underground wires or machinery might change how electricity moves through the soil or create weird magnetic spots that don't match the natural rocks around them. Today, scientists use tools like magnetometers and electromagnetic induction equipment to scan the Earth's surface. These instruments help them spot strange electrical or magnetic patterns. If these anomalies are well organized and don't look like what we'd expect from nature, they might point to something artificial, like a buried power system or forgotten energy device. Gravity is another tool in the modern explorer's toolbox. Everything with mass pulls on everything else, even just a little. So if there's something unusually heavy hidden underground, like a giant machine, a buried chamber, or a dense material unlike anything else around it, that spot will create a tiny but detectable shift in gravity. Using sensitive gravimetric instruments, researchers can map out these shifts. If they find dense spots underground that don't match the natural geology of the area, they might be looking at the remains of an ancient energy facility or a once functioning technological complex. Sometimes, these gravitational changes can even reveal signs of recent movement, hinting that whatever is underground might not be entirely dead and buried. Sound waves moving through the Earth can also reveal hidden secrets. When researchers send seismic waves into the ground, usually by creating small vibrations and recording how the waves bounce back, they can detect strange shapes and materials hidden deep below. If the waves bounce off of tunnels, chambers, or man-made structures, the patterns they create will look different from waves that hit only natural rock. For example, stone buildings or metal machines buried underground can reflect seismic waves in unique ways. This allows scientists to create pictures of what's down there, even if it's hundreds of feet below the surface. These hidden reflections may show us where ancient engineers once built foundations, walls, or complex energy systems. The real magic happens when electromagnetic, gravitational, and seismic clues all line up. When strange magnetic fields appear near gravity anomalies and odd seismic reflections in the same area, it strongly suggests that something unusual, possibly even artificial, is buried there. These overlapping clues could be pointing to the remains of an ancient power system or technology we no longer understand. It raises a powerful question. What kind of energy sources might such a civilization have used? If ancient civilizations did use energy systems, they might not look like anything we know today. Instead of steel wires and power plants, they may have tapped into the natural power of the Earth, using materials and methods now lost to history. For example, if they use geothermal energy, we might find signs of heat that doesn't match the natural flow underground. These hotspots could suggest artificial heating or ancient drilling. Strange patterns in mineral layers might show that the land was once chemically altered by heat or strange reactions. Another clue could come from the rocks themselves. If a rock has odd isotope ratios or contains rare metals, it might mean it was exposed to powerful radiation or used in energy storage. Some old stone sites that are aligned perfectly with the stars or Earth's magnetic field may not be ceremonial as we once thought. They could have been part of a large energy systems collecting power from the Sun or Earth itself. Even more amazing would be the discovery of objects made of exotic materials, things we can't explain using known ancient methods. If we ever find tools or containers made from advanced alloys, synthetic materials, or other strange substances, it could mean these objects were part of ancient batteries, power regulators, or energy converters. It's even possible that ancient electromagnetic or sound-based energy systems left a lasting mark on the Earth's crust. Over tens of thousands of years, those signals might have faded or been buried under newer activity, but some parts might still be detectable using modern instruments. For example, a strange repeating magnetic signal or a faint rhythmic vibration coming from deep underground could hint at a power system that once hummed with energy. If a highly advanced civilization had existed on Earth long ago and had created some form of communication network or data storage system, there is a chance that tiny remnants of that technology might still be hiding in the Earth today. These traces wouldn't be the usual things archaeologists look for, like broken pots, carved stones, or rusted tools, but rather subtle clues buried deep in the soil, rocks, or even ice. These clues could be in the form of strange chemical elements, unusual patterns in minerals, or mysterious materials that don't quite fit with what nature usually creates. Let's imagine, for example, that this ancient civilization had figured out how to use nanotechnology, tiny machines or particles far smaller than a grain of sand. If they used these microscopic tools to store information or send messages, they might have left behind materials unlike anything found naturally on Earth. These could include engineered particles, synthetic plastics, or even super-thin carbon sheets similar to modern-day graphene. Over time, such materials could become trapped inside layers of rock or mud, where they might remain for thousands or even millions of years. To find these ghostly footprints of lost technology, scientists are now using incredibly precise tools. One method involves looking for rare combinations of atoms, called isotopes, that wouldn't normally be found together unless someone had made them on purpose. For example, Certain nanomaterials might contain strange mixes of metals or chemicals that stick out like a sore thumb compared to the usual makeup of Earth's crust. These chemical clues could be picked up using advanced machines like mass spectrometers or high-powered microscopes that zoom in on the atomic level. Some synthetic materials might even leave behind their own special fingerprints. For instance, a synthetic polymer or nanostructure might change the rocks around it by triggering new minerals to grow or causing chemical reactions that wouldn't normally happen. These changes can show up as weird shapes, unusual textures, or rare crystal forms that scientists can spot under electron microscopes. Even after many thousands of years, these odd formations could remain as silent witnesses to ancient technological activity. It's also possible that if the ancient civilization had used advanced ways to send messages, like electromagnetic waves or sound signals, some tiny physical traces of that technology could still be buried underground. For example, certain materials might hold on to faint magnetic or vibrational echoes, especially if they were designed to do so. These hidden messages might not be easy to spot, but with the right tools we might just pick them up. Of course, there are many obstacles in the way. Over long periods of time, natural forces like erosion, earthquakes, and chemical weathering can damage or erase evidence. There's also the risk of confusing recent pollution or industrial waste for ancient technology. However, scientists are getting better at sorting out what's natural and what isn't. With new and powerful tools, such as synchrotron radiation, nanoscale imaging, and isotope fingerprinting, researchers now have a better chance than ever of uncovering these ancient secrets. What makes nanotechnology and other advanced materials so special is that they often include very rare elements or complex molecular patterns. These don't just appear by accident in nature. If used on a large scale, whether through factories, dumping sites, or accidental spills, they could leave behind faint but telltale signs in the Earth. These traces might show up in sediment layers, ancient mineral deposits, or even in ice cores drilled from polar regions. For example, an ancient society might have made nanoparticles with very specific atomic arrangements, or covered them in protective coatings. These features could help them survive the passage of time, remaining locked within ancient rock layers for tens of thousands of years. In some cases, the materials might have turned into minerals themselves, forming completely new crystal types that don't naturally occur, but can be detected by scientists through detailed chemical tests. The real challenge is figuring out which of these odd findings are the result of intelligent design, and not just nature playing tricks. To do this, researchers look for things that don't quite belong, like strange ratios of elements, unusual crystal shapes, or unexpected concentrations of rare metals. These might be hidden, faint, or buried deep, which means scientists need ultra-sensitive equipment to even notice them, and it gets more complicated. We also have to figure out if these clues are from ancient times or just leftovers from modern human activity. That's where a deep understanding of Earth's natural chemistry, geology, and environmental changes comes into play. Without that knowledge, we could easily mistake something natural for something artificial, or the other way around. But there's hope. As research advances, scientists are now turning their eyes to some of the most untouched and stable parts of Earth's geological archives. By studying the oldest and most well-preserved layers of Earth's crust, we may be able to pick out strange markers that hint at a forgotten technological past. This opens up exciting new possibilities, especially when we combine high-tech tools with remote sensing from space. Satellite imaging and remote sensing have changed the game. These tools allow scientists to scan massive areas of the planet, deserts, jungles, oceans, and mountain ranges, without having to set foot on the ground. From space, satellites can pick up subtle changes in soil color, mineral content, and surface heat. These changes might point to the presence of something artificial, like buried structures or leftover technology. Special cameras on satellites use multispectral and hyperspectral imaging, which can detect differences in light that the human eye can't see. These differences can reveal unusual materials or geometric patterns, like straight lines, right angles, or perfect circles, that are rare in nature but common in man-made structures. If scientists spot something odd, they can then send teams to explore those locations in more detail. Thermal imaging also plays a role. It can detect leftover heat or cold spots that may hint at energy use from long ago. In some cases, A patch of ground might still carry a thermal signature even after thousands of years, especially if strange materials were involved. But satellite data alone isn't enough. Earth is full of natural features that look artificial, like straight cliffs, polygonal rock formations, or oddly shaped lakes. This is why experts need to carefully analyze the data using advanced algorithms and machine learning. These programs help sort out real anomalies from natural lookalikes. One of the biggest challenges in the search for signs of ancient technology, possibly left behind by forgotten or even pre-human civilizations, is telling the difference between what is natural and what might be artificial. In other words, how can scientists tell if a strange-looking rock is just a natural mineral formation shaped over millions of years, or if it's actually a piece of something man-made like an old machine or tool? Nature has a way of creating complex and beautiful shapes all on its own. Over millions of years, things like heat, pressure, water, and even tiny life forms have helped shape rocks and minerals into patterns that sometimes look very much like they were crafted by intelligent hands. For example, layered rocks known as banded iron formations, or the fossilized remains of microbial mats called stromatolites, can appear as if they were designed or assembled. Some mineral veins form repeating patterns, straight lines, or symmetrical shapes that might trick the eye into thinking they're the remains of machines or tools. These formations usually come into existence through natural processes like the slow buildup of minerals from water, the movement of sediments over time, or even biological activity. But just because something looks artificial doesn't mean it is. Nature, it turns out, is a master sculptor. What makes this even more difficult is that mineral formations in nature can be incredibly diverse. Their shapes and patterns can vary a lot depending on the environment they formed in, such as how much heat or pressure was present, or what chemicals were around at the time. Because of this wide range of possibilities, it's very hard for scientists to create a fixed set of rules to clearly separate natural formations from possible artificial ones. On top of that, when looking at things like the makeup of minerals or the ratios of certain isotopes, which are versions of elements with different atomic weights, natural and artificial materials can sometimes look very similar. If a long-lost civilization had once used special minerals or processing techniques, those materials might now resemble something completely natural. Even more confusing, nature can occasionally produce strange and rare features, like crystal formations or tightly packed mineral balls known as concretions that might seem like they were designed. There's another big hurdle. The tools scientists use today to find possible signs of past technology may not be powerful or precise enough. Technologies like satellite imaging, ground-penetrating radar, or spectroscopy, which looks at how materials reflect or absorb light, help researchers study what's beneath the Earth's surface or hidden within rocks. But many of these methods don't yet have the detail needed to spot tiny or subtle signs of artificial work, especially when they're buried in complex layers of natural geology. Telling apart a small artificial signal from a natural background pattern takes not just high-tech tools, but also a deep understanding of how the surrounding area formed. And often, this background knowledge is missing or unclear, especially in remote or ancient regions where layers of Earth have been building up for hundreds of thousands or even millions of years. All in all, the difficulty lies in three main things. First, nature's ability to mimic artificial designs. Second, the fact that natural and artificial materials can share similar features. And third, the current limits of technology. Solving this mystery will require not just better machines, but also a stronger understanding of how minerals and rocks form naturally. Only with that knowledge can we build reliable ways to identify true signs of ancient technology hiding in plain sight. But there is hope on the horizon. As our technology continues to grow more advanced, our chances of detecting long-lost signs of intelligent activity become much better. One of the most promising areas is in improving remote sensing, the science of studying Earth from a distance, usually using satellites or airborne tools. Newer, sharper satellite imaging systems can now detect tiny oddities on the Earth's surface, changes in shape, heat, or composition that might hint at artificial structures hidden under dirt, sand, or vegetation. These could include things like buried walls, strange shapes in the soil, or patterns that don't fit with natural geology. High-resolution spectroscopic tools, especially when combined with artificial intelligence and machine learning, can now process massive amounts of data and pick out unusual mineral mixtures or energy readings that probably didn't occur naturally. These smart systems can learn to recognize the difference between what nature typically does and what an intelligent hand might have done. Other important advancements are happening in geophysical surveys. Ground-penetrating radar, seismic tomography, which uses sound waves to see underground, and even magnetic resonance imaging are becoming more accurate and more affordable. These tools let scientists explore what lies deep below the surface without having to dig. They might be able to reveal buried structures, tunnels, or objects that have been hidden for thousands, or even millions, of years. Dating methods are also improving. New versions of mass spectrometry and radiometric dating can now measure the ages of rocks, bones, and other materials more accurately than ever before. This helps researchers build a timeline of events, when something was made, when it was buried, and whether it fits with known historical periods. If certain areas show signs of advanced material use or unusual energy consumption during a time when no known civilization existed, that could be a huge clue. Artificial intelligence and big data analysis are transforming how we search for these clues. By feeding computers large amounts of information about what natural formations usually look like and what artificial ones might look like, scientists can create smart systems that highlight possible artifacts or technological traces hidden in geological data. These systems can scan information from geology, chemistry, physics, and more, bringing together many different signs into a single, clearer picture. As all these technologies keep evolving, so too does our ability to explore Earth's deep past. It's possible that buried somewhere beneath the soil or locked inside ancient rocks are the secrets of civilizations that came before us. Perhaps thousands, tens of thousands, or even millions of years ago. These advancements won't just help us spot faint signs of ancient technology, they'll also help redefine how we understand intelligence and civilization itself. Over the years, many fascinating and thought-provoking theories have been suggested to explore a bold idea that intelligent civilizations might have existed long before humans ever appeared. These theories challenge the traditional belief that human civilization is the only one to have ever existed on Earth, and that we are relatively new in the planet's long and ancient history. Instead, these models invite us to imagine a much deeper past, possibly filled with lost civilizations, some even more advanced than our own. These ideas come from a wide mix of scientific fields, including geology, archaeology, evolutionary biology, and astrophysics. By combining knowledge from these different areas, researchers create detailed and believable scenarios of how intelligent life, either on Earth or on other worlds, might have risen, flourished, and then vanished without a trace. One of the most well-known theories is called the Silurian hypothesis. This theory suggests that a technological civilization could have developed on Earth millions of years ago, long before the first humans walked the planet. However, because of how Earth's geology works over long periods of time, with shifting continents, erosion, and sediment buildup, nearly all traces of such a civilization could have been erased or buried deep underground. If anything is left, it might be very hard to tell apart from natural features. For example, strange chemical signatures, odd patterns in isotopes, unusual mineral layers, or even fossilized machine parts might be hidden in the rocks, but we may overlook them or mistake them for natural processes. Another popular idea is that there may have been many different civilizations over the ages, each one rising to greatness and then collapsing, only to be forgotten by the next. This view suggests that civilizations might not be rare or unique at all. Instead, they could have come and gone across different geological periods, wiped out by disasters like volcanic eruptions, asteroid impacts, or massive climate shifts. These repeated cycles, combined with the slow but powerful forces of Earth like plate tectonics, may have completely erased the evidence of earlier technological societies. Some of these theories go even further by imagining civilizations beyond Earth, intelligent beings that may have lived on other planets or moons billions of years ago, long before humans existed. Thanks to studies in astronomy, scientists know that there are many other places in our galaxy where life could have existed. In fact, some planets might have had oceans, warm climates, and protective atmospheres billions of years before Earth was even formed. If life had time to evolve on those worlds, it's possible that intelligent civilizations could have developed and maybe even vanished long ago. When you look at all these ideas together, they stretch our understanding of civilization, time, and life itself. They show us that we need to think on much larger scales, not just thousands or millions of years, but billions of years, and not just Earth, but the entire universe. They also challenge scientists to improve their tools and techniques, to search for subtle signs of intelligence, no matter how ancient or hidden. But how do these models actually work? How do they connect all the complicated parts, like planets, living things, and technology? To build these models, scientists use multidisciplinary approaches, meaning they pull together ideas from different scientific fields to understand how civilizations might come into being, evolve, and disappear. First, they look at the planetary conditions that make life possible. This includes things like a stable climate, active geology, and the presence of an atmosphere. They also study how a planet's size, orbit, and magnetic field can protect it and support life over long stretches of time. Then they look at the biology. This part examines how life begins, grows, and survives challenges. They think about whether certain signs of life, called biosignatures, could still be found today, even after extreme changes like mass extinctions or climate disasters. Life doesn't just respond to a planet's environment, it also changes it. For example, plants and microbes can affect the atmosphere and climate, which in turn shapes the future of life on that world. These feedback loops can either help civilizations flourish or push them toward extinction. Finally, they study the technological side. This includes how long civilizations might survive, what kind of damage they might do to their environment, and whether anything they leave behind could be detected. For example, scientists wonder if we could ever detect ancient pollution in the atmosphere, unusual energy patterns, or structures buried underground. They also consider the chances that a civilization might collapse due to war, environmental destruction, or running out of resources. Some may vanish quickly, leaving very little behind. By bringing all these pieces together, the planetary setting, the biology of life, and the rise and fall of technology, these models create a richer and more complete picture of how civilizations could live and die across the cosmos. They remind us that life and intelligence don't just depend on one thing, but on many different forces working together, and sometimes against each other, over cosmic timescales. These ideas change the way we think about habitability, the ability of a planet to support life. They show us that habitability isn't something simple or permanent. A planet could be perfect for life at one time and completely dead at another. Instead of thinking of habitability as a yes or no question, these models present it as a tapestry woven across time, where the right conditions might appear, disappear, and return again. One major takeaway is that many planets might be more suitable for life than we once thought, especially if life is good at bouncing back after disasters. If civilizations really did exist long ago, their ruins might still be hidden in ancient rock layers or scattered across the galaxy. This encourages scientists to look more carefully at the oldest parts of planets and moons, searching for faint signs of forgotten life. These models also challenge the idea that planets follow a simple, straight path in their development. Instead, they suggest that random and chaotic events, like asteroid strikes, supervolcanoes, or massive ice ages, might play a huge role in shaping whether life survives or disappears. Civilizations might rise quickly during peaceful times, only to fall just as fast when disaster strikes. This explains why we may not see any signs of them. They may have come and gone long before we knew how to look. In the end, these models help us understand how deeply connected everything is: the planet itself, the life it supports, and the technology that life might create. They suggest that the universe could be filled with life in many different forms and stages, some already gone, some just beginning, and others possibly far ahead of us. They make us question whether Earth's story is really so special, or just one chapter in a much larger book. These theories also offer new ways to think about the Fermi paradox, the famous question: if the universe is so big and life is probably common, then where is everybody? The model suggests that maybe advanced civilizations are rare, short-lived, or extremely hard to detect. Some might have destroyed themselves, others might have moved far beyond the kind of technology we recognize, and some might still be waiting to be found, hidden beneath rock, time, or space. One of the most fascinating ideas explored in these theories is how long a civilization can last, what scientists call technological longevity. According to these models, civilizations, whether they exist on Earth or far away in space, might not survive long enough to be noticed by others. They may collapse or slowly decline, not because of wars or invasions, but due to problems they create for themselves. These could include destroying their own environment, falling into social chaos, or simply reaching a point where technological progress slows down or even stops. If most civilizations tend to fall apart or fade away before they manage to send out strong, long-lasting signals into space that could explain why we don't hear anything from alien worlds. In other words, the famous Fermi paradox, which asks why, in a universe so vast we haven't found signs of intelligent life, might not mean the universe is empty. Instead, it might mean civilizations come and go too quickly to be noticed. They might burn brightly for a while, then vanish before anyone can hear them. These ideas also often mention something called the Great Filter. This is a name for the big obstacles that stop civilizations from reaching a point where they can travel between the stars or send signals across the galaxy. These filters could be enormous disasters, either caused by nature or by the civilizations themselves. Imagine supervolcanoes erupting, huge asteroids smashing into planets, or global pandemics changing the climate and wiping out entire populations. Events like these could destroy even the most advanced societies, setting them back or erasing them entirely. What makes it even more complicated is that such disasters might not happen just once. They could occur in cycles. Civilizations might rise, reach incredible heights, and then fall, only for new ones to appear later. But each one might last only a short time in cosmic terms. That would mean the chances of two civilizations existing at the same time and being able to talk to each other are incredibly slim. Some theories go even further, suggesting that certain civilizations might decide, either on purpose or by accident, to stay silent. They might avoid sending signals out into space to keep from attracting danger, or they might follow a belief system that tells them not to interfere with other life. This idea adds another layer to the mystery. If many civilizations are choosing to be quiet, and others are being destroyed by disasters, then it's no wonder the universe seems so silent. All these ideas come together to paint a picture of civilizations that are fragile and short-lived. The silence we hear in space might not mean no one is out there. It might mean that civilizations keep rising and falling before they ever get the chance to reach out. This perspective leads to deeper questions. What causes societies to rise or collapse? Could the same kinds of disasters that affect Earth also have destroyed other civilizations long ago? Many of these models focus on natural catastrophes as the turning points in the lives of civilizations. Throughout Earth's history, huge volcanic eruptions, asteroid strikes, or sudden changes in climate have reshaped the world. In these theories, such disasters are not just deadly, they are moments of transformation. When a disaster strikes, it can destroy entire cities, kill millions of people, and cause social systems to fall apart. Roads crumble, knowledge is lost, and the survivors are left to rebuild from scratch. But strangely enough, these disasters don't only destroy. Sometimes they clear the way for something new. A volcanic eruption, for example, might wipe out a civilization but leave behind rich volcanic soil that helps new farming communities grow. Climate changes can force people to move to new areas where they adapt and invent new tools or ways of life. So these disasters can act as both destroyers and creators, shaping the long-term path of human or even alien civilizations. How often these disasters happen and how severe they are matters a lot. If big catastrophes strike too often, then civilizations may never get the chance to build something that lasts. On the other hand, if they happen rarely but with great force, they could explain why some societies vanish suddenly from history. And when these disasters combine with other problems like running out of resources or civil wars, it becomes very hard for civilizations to survive for long. Another important point raised by these models is that the remains of ancient civilizations may not last forever. In fact, most traces of past societies are eventually erased by nature itself. Over tens of thousands, or even millions of years, Wind and water wear down buildings, earthquakes and tectonic movements bury cities deep underground, and oceans rise to swallow entire coastlines. This makes it incredibly hard for archaeologists to find solid proof of ancient civilizations, especially those that may have existed long before humans. This leads to a very intriguing question. Could it be that the reason we've never found clear evidence of a pre-human civilization is because nature wiped away all the clues? If civilizations existed before humans, might their ruins now lie buried deep under the earth or lost beneath the sea? Some scientists and thinkers believe this is a real possibility. They suggest that these ancient civilizations might have used long-lasting building materials, or even built huge structures underground or underwater. These would be hard to find with today's technology. Others think that maybe they used special kinds of materials or lived in ways that didn't leave obvious marks, so their entire presence could be hidden within the rocks, chemical layers, or ocean floors. It's also possible that these civilizations were wiped out by disasters, giant volcanic eruptions, asteroid strikes, or sudden climate shifts that erased nearly all traces of their existence. These kinds of events might act like a global reset button, scrubbing the Earth clean and making it very unlikely that any solid evidence would survive to our time. Some theories go even further and suggest that ancient civilizations might have changed the environment in subtle ways, using advanced science, like bioengineering or climate control. These changes might leave strange patterns in soil or rock layers, things that scientists today might not recognize as artificial. They could look completely natural, even if they were actually made by intelligent beings long ago. Still, proving any of this is extremely difficult. One of the biggest problems is that we just don't have the right tools or methods to spot such faint ancient signs. The geological record, the layers of rock and sediment that hold Earth's history, is incomplete. Earthquakes, erosion, and other natural forces constantly shift, break, or erase these layers. Trying to find clues of a civilization from millions of years ago is like trying to find a single grain of sand in a desert. There's also the risk of making mistakes. If we find a strange rock formation, how do we know it's not just a natural creation? Could what looks like an ancient artifact be just a coincidence of nature? From a scientific point of view, trying to investigate the possibility of ancient civilizations that existed long before humans is extremely complicated. These investigations involve many different fields of study: geology, climate science, archaeology, and astrophysics, all working together. Each expert brings a different piece of the puzzle, but putting those pieces together can be very challenging. To figure out whether something strange in the geological record is natural or a sign of intelligent activity, scientists often have to look for indirect clues. These include odd chemical traces like unusual isotopes, mysterious patterns in microscopic structures, or strange layers of sediment in the ground. But interpreting these clues is still a work in progress. The tools and methods for understanding such signs are still being developed, and scientists have to be very careful not to let their personal beliefs or expectations influence how they interpret the evidence. This is known as confirmation bias, and it's a real danger in this kind of research. Another huge challenge is time itself. Some of these potential signs of ancient civilizations could be hundreds of thousands, or even millions, of years old. Trying to date materials that old accurately is very difficult, and understanding what was happening on Earth at that time makes things even more complex. Many dating methods lose accuracy as time stretches back so far, and events like erosion, earthquakes, or volcanic eruptions could have buried or destroyed valuable clues. From a philosophical angle, these ideas are even more mind-bending. They go against our deeply held beliefs that humans are the first and only truly advanced civilization on Earth, and that history moves forward in a straight line from primitive to modern. These theories make us ask deep questions. What counts as real evidence? Can we trust the tools we use to study the past? Is it possible that history is far more complicated than we ever imagined? They also force us to examine our own biases. One big example is anthropocentrism. This is the idea that humans are the most important and most advanced creatures ever to exist. This belief can make it hard for people to even consider the possibility that intelligent life might have existed long before us, or in ways very different from our own. Such biases can close our minds to possibilities that deserve real investigation. Because these theories are still very speculative, They often spark debates about what makes something scientific. One of the rules in science is that a good hypothesis must be testable. It should be possible to prove it wrong if the evidence doesn't support it. But when the evidence is extremely rare, very old, or hard to understand, this becomes a big problem. Still, the fact that it's difficult doesn't mean we should give up. Instead, it shows the importance of using careful, honest, and open scientific methods when studying such extraordinary ideas. Looking ahead, future discoveries could completely change the way we see these theories. New technologies are opening up exciting possibilities. Underwater exploration with powerful sonar, satellite images of hidden structures, and better methods for dating ancient materials might all reveal things we couldn't detect before. For instance, if sonar mapping of the ocean floor finds ruins that are clearly not natural and are older than any known human civilization, that would be groundbreaking. Or if scientists discover a layer of material filled with tools, carvings, or strange chemical traces and can show it's over 1 million years old, it might strongly suggest that another intelligent species once walked the Earth. On the other hand, these same technologies could also prove that no such civilization ever existed. If scientists search the ocean floor, deserts, and deep underground areas but find no clear evidence, no ancient cities, no advanced tools, no biological markers of a previous species, then it would support the current view that humans are indeed the first civilization to reach this level of complexity. Even if evidence remains missing, it might not mean those civilizations never existed. Earth is always changing. Wind, water, earthquakes, and other forces constantly reshape the surface. Over millions of years, whole continents have shifted, oceans have risen and fallen, and mountains have formed and eroded. These forces could have wiped out nearly all traces of ancient activity. But at the same time, some rare conditions, like volcanic ash covering a site, or deep-sea cold preserving an object, could have helped preserve clues, waiting for the right moment to be found. Environmental factors also add another layer of difficulty. Suppose scientists find a sudden spike in carbon dioxide, or strange particles in ancient air bubbles trapped in ice. That could point to a global event like a massive fire or industrial activity. But it could also mean a natural disaster, like a huge volcano eruption. Understanding the context is everything. The search for intelligent life beyond Earth, what scientists call SETI, short for the search for extraterrestrial intelligence, is not just about trying to talk to aliens living far away in space. It's also about the exciting possibility that alien civilizations may have already been here long ago and left behind clues we've yet to recognize. This idea fits with a fascinating theory known as the Silurian hypothesis, which suggests that highly advanced civilizations might have existed on Earth or elsewhere in the solar system long before humans came along, and they may have left behind traces of their existence that we just haven't noticed yet. So, the mission of SETI isn't only about listening for radio signals or laser flashes coming from distant stars. It's growing into something much bigger, like a cosmic treasure hunt. Scientists are now also looking for physical evidence, such as strange artifacts, mysterious structures, or unusual patterns in space that might hint at intelligent life from millions or even billions of years ago. For many years, traditional SETI work focused mainly on catching electromagnetic signals, like radio waves or flashes of light, that could have been sent on purpose by intelligent beings. But what if those alien civilizations rose and fell long before humans built radios or telescopes? Their broadcasts would have ended ages ago, making it nearly impossible for us to pick them up now. Because of this, researchers are starting to think that the best way to find ancient aliens might not be through signals, but through astroarchaeology, a kind of archaeology that looks not on Earth, but among the stars. One exciting idea is to carefully examine the surfaces of planets and moons in our solar system. If alien civilizations ever lived or visited these worlds, they might have built things or mined materials, and maybe even left behind giant structures. If scientists spot unusual shapes, perfect geometric patterns, or strange heat signatures that don't match natural processes, those could be signs of artificial activity. For example, if a planet has odd mineral deposits or looks like it's been dug into in ways nature can't explain, it might suggest that someone, or something, was working there a very long time ago. But the search doesn't stop at planets and moons. SETI researchers are also looking into the broader space environment for technosignatures, indirect hints of technology. These could be things like strange energy patterns in space, oddly behaving stars, or large objects that might be massive alien machines. One famous idea is the Dyson sphere, a giant structure built around a star to collect its energy. If such a megastructure was ever built, even billions of years ago, it might still be affecting the light or energy coming from that star in ways we can detect. There's even the possibility that artificial satellites or space probes from long-lost civilizations could be drifting quietly through space, maybe even right here in our own solar system. If intelligent life once tried to explore the galaxy, just as we are beginning to do, then bits and pieces of their technology might still be floating around, waiting for us to find them. In short, the modern search for ancient aliens has become a wide-ranging scientific effort. It now includes the study of old signals, space dust, planetary surfaces, strange metals, and even forgotten artifacts on Earth itself. Scientists are becoming more like space archaeologists, piecing together the ancient story of the universe and hunting for the faint clues that might tell us we are not, and never have been, alone. To detect signs of these ancient civilizations, scientists need to know what to look for and how to tell the difference between something natural and something artificial. Unlike loud and clear radio signals we might expect from living alien civilizations, the traces left behind by long-gone societies would likely be faint, hidden, or even decayed. They could be signals buried in the noise of space, or objects that have been damaged or buried over millions of years. One way scientists are searching is by looking for strange radio or laser emissions coming from specific parts of the sky. These could be leftovers from technology that once broadcasted messages, or just the glow of old machines that still give off energy. These emissions wouldn't be strong or obvious. They might come in bursts or be so faint that only the most sensitive instruments could notice them. Some might even be hiding among natural space signals like those from pulsars or quasars, making them very tricky to spot. Another way is to search for unusual structures on moons, asteroids or planets, structures that look like they were built rather than formed by nature. Maybe giant towers, grid-like formations, or mining areas that seem too orderly to be random. Such discoveries could point to intelligent design, perhaps for life support, energy collection, or even scientific experiments. These kinds of clues require powerful telescopes and imaging tools to explore far-off places and see what's lying beneath the surface. Scientists also study cosmic dust, meteorites, and ancient rocks that fall to Earth. If these objects contain materials that shouldn't naturally occur, like rare isotopes, strange metals, or unusual combinations of elements, it might mean they were manufactured by intelligent beings. Some of these might have crashed to Earth long ago and could now be buried in ancient rock layers, just waiting to be dug up and examined. And here's an even more astonishing idea. What if some alien artifacts are already on Earth, buried deep within our planet's ancient history? Imagine discovering a tool or structure that looks way too advanced to have been made by any known human civilization. Maybe a metallic object with a perfect shape, or an inscription using symbols that don't match any language we've ever seen. If such objects exist, they might be misidentified as natural, or simply dismissed because they don't fit what we expect. To truly recognize these clues, scientists must work together across many fields. Geochemists can test the chemical makeup of strange rocks. Materials experts can examine objects to see if their construction is too advanced for their supposed age. Archaeologists can investigate odd carvings or unexplained relics with fresh eyes. These experts must remain open to the possibility that some ancient mysteries could point not just to lost human cultures, but to visitors from far away. The problem is that unusual objects found in ancient sites can be easily misunderstood. People might think they're natural oddities or modern fakes, especially if there's no clear way to prove how old they are or where they came from. That's why it's so important to carefully test and validate these findings using the best science available. The idea that objects from other worlds might be hidden within Earth's ancient history is both exciting and mysterious. It invites us to take a fresh look at old archaeological discoveries, especially the ones that seem strange or don't quite make sense. maybe, just maybe, some of these puzzling findings are more than just unusual human artifacts. This way of thinking encourages scientists to widen their point of view. Instead of only using tools from archaeology or history, they now bring in knowledge from space science, biology, and planetary exploration. When these different fields come together, it becomes easier to imagine that Earth's story could be more connected to visitors from space than we ever thought possible. Thinking along these lines naturally leads to a bold question. What if beings from distant planets visited Earth long ago? And what if they left behind clues, some of which we may have already found, but didn't recognize for what they really are? This is the heart of ancient alien theories. These theories challenge the usual explanations offered by archaeologists. They suggest that extraterrestrial beings, intelligent life from other worlds, might have played a role in shaping early human societies. Some even believe that these beings helped spark the birth of human civilization itself. From this perspective, researchers are encouraged to take a second look at strange artifacts, unusual structures, mysterious carvings, and odd symbols. Rather than brushing them off as myths or coincidences, some people argue that they might actually be evidence of contact with beings from other worlds. Imagine, for example, carvings that look far too advanced for their time or structures, built in ways that defy the known abilities of ancient cultures. Could these be messages from intelligent visitors, lost in time? This idea leads scholars to rethink everything. Maybe not all ancient objects were made by humans alone. Perhaps some were influenced, or even created by extraterrestrials. When archaeologists come across artifacts that don't match the tools, knowledge, or culture of the people who supposedly made them, this new line of thinking offers alternative explanations. It also encourages teamwork across many fields: astronomy, geology, chemistry, and more, so that experts can study these mysterious findings from every angle. They begin to search for clues in places that archaeologists alone might overlook. Could some ancient materials, for example, have come from outer space? This brings us to something fascinating. The idea that space rocks, like meteorites and cosmic dust, might actually carry messages or materials from alien civilizations. Every single day, tiny particles from space fall to Earth. Some are as small as grains of sand, others are large enough to survive entry through the atmosphere and land on the ground. These pieces of cosmic debris are not just leftovers from exploding stars or wandering comets. They might also carry bits of technology, signs of life, or other clues from intelligent beings that once existed far away from our solar system. Meteorites, in particular, are especially interesting. They come from planets, moons, or asteroids that once existed elsewhere in the universe. When these space rocks land on Earth, they often carry strange chemical fingerprints or unusual atomic patterns. Sometimes, scientists find odd microscopic structures inside them, shapes that almost look like tiny machines or tools. This raises an exciting possibility. Could these be parts of ancient alien technology? For example, some meteorites have shown isotopes, forms of elements like nitrogen or helium that are not normally found in nature. These could point to some kind of artificial process, perhaps something designed by intelligent beings. And even though many scientists remain skeptical, some of these patterns have no clear explanation, making them worthy of closer study. Cosmic dust, though much smaller, is also worth investigating. These tiny bits of matter come from comets, asteroids, and even interstellar clouds far beyond our solar system. When collected and studied, they sometimes contain complex organic chemicals, strange mineral shapes, or traces of materials that are not known to form naturally. Some of these particles might even carry the building blocks of life, or fragments of long-lost alien worlds. With new technology like powerful microscopes, advanced lasers, and high-precision sensors, scientists can now study even the tiniest particles with incredible detail. They can measure the structure of atoms, detect unusual combinations of elements, and analyze patterns that might suggest an artificial origin. As this research continues, we may one day uncover stories hidden in the stars, stories of civilizations that lived, built, and vanished before we ever came into being. But the search for signs of ancient extraterrestrial life doesn't stop with Earth. Scientists are now turning their gaze to the skies. Modern astronomy provides powerful tools to help locate potential alien artifacts across the universe. This includes not only looking at stars and planets through telescopes, but also studying strange behaviours and mysterious signals in space that might suggest the presence of something artificial. One example is a star known as KIC 84628552, better known as Tabby's star. Astronomers noticed that this star sometimes dims in odd, unpredictable ways. This strange behaviour led to speculation that something massive, like a giant artificial structure, might be orbiting the star and blocking its light, possibly a Dyson sphere, a theoretical megastructure designed by a highly advanced civilization to collect energy from a star. Instruments like the Wide Field Infrared Survey Explorer, often called WISE, are able to detect heat given off by these kinds of hypothetical structures. If something huge were collecting energy from a star, it would give off a unique type of infrared light. So scientists carefully study these infrared patterns, hoping to spot signs of technology too advanced for natural explanations. Radio telescopes like those in the Allen Telescope Array also play a role. They search the skies for strange radio signals, especially narrow and repetitive ones that might be the product of intelligent communication rather than random noise from space. In addition to watching stars, researchers also study the surfaces and atmospheres of distant planets. By using special techniques like spectroscopy, they can look for elements and compounds that don't naturally appear under normal planetary conditions. If they spot something strange, like a material that requires advanced technology to create, it could be a clue that someone or something tampered with that world. Even the outer regions of our own solar system offer places to search. Scientists study the Kuiper Belt and the Oort Cloud, which lie far beyond Neptune. If they notice patterns or arrangements of objects that look too organised or unnatural, it might be a sign of past alien activity. Telling the difference between natural events in space and signals that might come from intelligent life is one of the biggest and most complicated puzzles in modern science. The universe is full of powerful energy bursts and strange short-lived events that can easily look like they were made on purpose, even though they are probably not. The main reason this is so tricky is because many of the signals we detect from space are unclear or mysterious. Take, for example, something called fast radio bursts, or FARBs. These are super bright flashes of radio waves that last only a few thousandths of a second. At first glance, they might seem like messages sent from alien civilizations, but most scientists think they come from natural cosmic events, like two neutron stars smashing into each other, or violent flares from supermagnetic stars called magnetars. To figure out whether something like an FRB is natural or artificial, researchers must carefully study every detail, like the shape of the wave, how long it lasts, how often it happens, and even how the waves are polarized. One big problem is that the universe is wildly unpredictable. Many signals are one-time events. They just happen and never repeat. That makes them hard to study and even harder to label as alien or natural. Even regular signals can be misleading. For instance, pulsars, which are spinning neutron stars that send out perfectly timed radio pulses, were once thought to be alien beacons when they were first discovered in the late 1960s. But we now know they follow well-understood physical laws. On the other hand, signals that don't follow patterns might raise our curiosity, but still turn out to be caused by natural processes we simply don't understand yet. Another major challenge comes from our own limited technology. Even though radio telescopes and computers are getting better every year, they still might not be sharp enough to catch tiny details that would prove a signal is artificial. On top of that, the Earth is filled with noise, radio signals from human-made satellites, mobile phones, and even space junk. These signals can accidentally look like they came from aliens, fooling scientists and causing confusion. To make things even more complex, any alien civilization out there might be using a completely different kind of technology to communicate, something far beyond what we currently understand. Instead of radio waves, they might be using laser beams, neutrinos, or some other type of signal that we haven't learned to detect yet. If that's the case, we might already be missing messages simply because we don't know how to recognize them. So the real challenge is not just about building better tools, it's also about changing how we think. What does an intelligent signal even look like? How do we tell if something is just a strange cosmic event, Or a message from another world? As we build better instruments and come up with better theories, scientists are slowly getting closer to being able to tell natural space signals apart from possible signs of alien technology. It's a long, careful process that sits at the edge of astrophysics and the ongoing search for extraterrestrial life, known as SETI. Looking ahead, future space missions might uncover even more exciting clues. These missions could lead to the discovery of ancient alien civilizations that once lived far beyond Earth. Thanks to new and more advanced technology, like high-tech spectrometers, robotic probes, and powerful remote sensing tools, we are now better equipped than ever to detect signs of life or technology on other worlds. For example, space missions headed to Europa and Enceladus, two icy moons of Jupiter and Saturn, are preparing to look beneath their frozen surfaces, where vast hidden oceans may contain the building blocks of life. If these missions find things like biosignatures, signs of living organisms, or even technosignatures, traces of past technology, it could mean that intelligent beings once lived beneath the ice of these distant moons. The planet Mars is also an important part of this search. Current missions are exploring ancient Martian riverbeds and lake beds to look for fossilized microbes, tiny life forms that might have lived billions of years ago. If we find complex organic molecules or other traces of biology, it could mean that life once existed on Mars, completely separate from life on Earth. That would be a huge discovery. Meanwhile, powerful telescopes are turning their eyes to planets beyond our solar system, called exoplanets. These telescopes are now good enough to study the atmospheres of faraway planets. Scientists are looking for strange chemicals such as artificial pollutants or unnatural lights, which could suggest that a civilization once lived or is still living there. Finding even a small clue like this would be a major turning point in human history. Another exciting idea is to look for actual alien artifacts. These could include enormous space structures, weird energy patterns, or strange signals that don't match anything we know. As our technology improves, searching for these kinds of remains becomes less like science fiction and more like serious science. It's possible that some advanced civilizations may have lived millions or even billions of years ago and left behind leftovers that we can still detect today, floating in space like cosmic ruins. Looking for evidence of civilizations that might have existed long before humans is not just a scientific quest. It's also an ethical and emotional journey filled with difficult questions. It makes us think deeply about how we study the past, how we respect other cultures, and how these discoveries could change what people believe about themselves and the world. As scientists search through layers of rock and ancient fossils, hoping to find signs of intelligent life that came before us, they carry a heavy responsibility. They aren't just digging into dirt, they're digging into the story of Earth itself, and what they find, or think they find, can have powerful effects. One of the biggest worries is about making mistakes. What if scientists find something unusual, like a strange pattern in a rock or a tool-like object, and too quickly claim it was made by intelligent beings? If they're wrong, it could confuse people, mislead the public, and damage the trust people have in science. That's why it's so important to double-check everything, to use clear and honest methods, and to avoid jumping to conclusions just for attention. Another major issue is how these discoveries affect people's beliefs. For hundreds and even thousands of years, many cultures have told stories about how life began and what makes humans special. If researchers find proof that intelligent life existed millions of years before us, it could shake those beliefs. Some people might feel threatened or deny the discoveries. Others might feel inspired, realizing that humans are just one part of a much older and bigger story. This could lead to new ideas about our place in the universe and help us feel more connected to the Earth and all life on it. But with such discoveries comes the need for respect, especially when it comes to ancient objects or sacred places. If something is found that might belong to a long-lost civilization, who gets to study it? Who decides where it should be kept, or whether it should be shown to the public? These are sensitive questions, especially for local communities or indigenous groups who may feel a deep spiritual connection to the land or the artifacts. Scientists must always work with care, listening to others and showing respect for different cultural values. There is also the danger of greed and exploitation. The excitement of finding ancient civilizations might lead some people to dig up sites without permission, or to sell artifacts for money. This can destroy precious evidence and erase the real story behind it. That's why it's so important to create clear rules and encourage international teamwork to protect these treasures. In short, searching for ancient, possibly pre-human civilizations brings up big and complicated questions. Researchers must be careful, honest, and respectful. They must protect the past, not just uncover it. After all, these discoveries could change how we see ourselves, not just as humans, but as part of a much longer and richer story that spans the entire history of life on Earth. If scientists one day found real proof that civilizations existed millions of years before humans, it would be one of the biggest discoveries in history. It wouldn't just change science books, it would change how people see themselves and their place in the world. For many centuries, people have believed that humans are the most advanced life forms Earth has ever known. We've told ourselves that we're the top of evolution's ladder. But what if we're not the first? What if other intelligent beings, maybe even high-tech societies, lived on this planet long before us? That idea alone would shake our understanding of history, and maybe even humble us a little. It might also change how we look at religion, mythology, and philosophy. Ancient stories about gods, lost worlds, and great floods might take on new meaning. Maybe those myths are memories of civilizations that really existed long ago. Religious teachings that focus on a single moment of creation might evolve into new ideas about cycles, life rising and falling over and over again on this ever-changing planet. This kind of discovery could also affect how we think about our own future. If other civilizations rose and fell long before us, what happened to them? Did they destroy themselves? Were they wiped out by nature? Could the same thing happen to us? These questions might make us more cautious about how we use technology and how we treat the Earth. On a deeper level, it could make us more open-minded. We might start to accept that intelligence and culture don't always look like ours. Civilizations could come in many forms, with different ways of thinking, creating, and living. This could help reduce narrow, human-centered views of progress and success. But then comes a hard question. Should we dig everything up right now? Or should we wait and protect these mysterious places until we're more ready? On one side, exploration is what drives science forward. Using tools like deep-sea robots, satellite images, and chemical scanners, scientists can look in places humans can't easily reach, like under the ocean floor, deep inside glaciers, or in remote deserts. These searches might uncover clues that were once invisible, traces of buildings, tools, or strange materials that don't belong in nature. Every new find helps us build a clearer picture of Earth's hidden past. But exploring comes with risks. Sometimes digging too quickly or without the right tools can ruin a site forever. Once the ground is disturbed, the original context is lost. And if something natural, like a weird-shaped rock, is mistaken for an ancient tool, it could lead to false stories and confusion. When the media gets involved, things can get even worse, with rumours spreading faster than facts. On the other hand, preservation means protecting these sites from damage. It means leaving them untouched so future scientists, with better tools and more knowledge, can study them more carefully. It also helps prevent misunderstandings and keeps the truth safe from being twisted or used for fame and profit. Most importantly, preservation respects the idea that some places may hold sacred meaning to others, and that we shouldn't rush to uncover things just because we're curious. Misunderstanding or exaggerating evidence about possible ancient civilizations that existed before humans can lead to serious problems, not just mistakes in science, but also confusion in society and even political or cultural tensions. At the heart of the issue is something known as confirmation bias, when people only focus on information that seems to support their own beliefs, while ignoring anything that doesn't. This often happens with unclear or incomplete data, which some researchers or storytellers may twist into dramatic tales. As a result, the truth gets lost, and both the scientific community and the public can be misled. When fragile clues, like strange rock formations or odd artifacts, are made to sound more important than they really are, they can create false ideas about history. These misleading ideas may pull attention and funding away from real scientific research. Even worse, they can weaken people's trust in science itself. Things get even more complicated when media outlets or online personalities jump in. They often turn uncertain findings into bold headlines, claiming they found definite proof of lost advanced civilizations. This kind of sensationalism makes things worse. It spreads confusion, fuels conspiracy theories, and creates unrealistic expectations. Then, when the exaggerated stories fall apart under careful study, people feel disappointed or betrayed, and they may stop trusting scientists altogether. But the impact doesn't stop there. These claims can also stir up deep cultural and political issues. For example, if someone says a forgotten advanced civilization once lived in a particular country or region, it could boost nationalist pride or create tension with other groups. On the other hand, if such evidence is ignored or rejected because it clashes with someone's religious or cultural beliefs, progress in science might be slowed down or blocked completely. Some religious groups, for instance, may see the idea of pre-human civilizations as a challenge to their beliefs about divine creation. A person from a Judeo-Christian background, for example, might see a strange fossil or rock formation as a sign from God, not as evidence of a forgotten intelligent race. Meanwhile, some indigenous communities may see those same clues as part of ancient spiritual traditions. In their view, those artifacts could be linked to wise ancestors or mystical beings, making them more open to the idea that humans might not be the first intelligent species on Earth. Cultural stories shape not only how people think, but also how scientific ideas are received. In places where governments control knowledge tightly, or where people don't trust science, unusual discoveries might be quickly dismissed. In contrast, in cultures rich in mythology, where stories of lost cities and ancient gods are common, people may be more welcoming of the idea that the Earth has a hidden past filled with mystery. These beliefs also affect how research is funded and how scientists talk about their findings. If a discovery threatens someone's core beliefs, it might face pushback or even be buried. But in communities that see science as a way to deepen spiritual understanding, those same findings might spark curiosity and open dialogue. That's why scientists must be very careful. When they speak about discoveries that could change how we see our past, they carry a great responsibility. They must communicate clearly, avoid exaggerating what they've found, and be honest about what is still unknown. If they present theories as facts too soon, it can cause confusion and mistrust. But hiding strange findings just because they are hard to explain isn't right either. It might block important breakthroughs. The best approach is to make sure every claim goes through careful checking, peer review, and thoughtful discussion before it reaches the public. This helps avoid mistakes and keeps science honest. Researchers also need to think about the wider effects of their work. Imagine if strong evidence appeared showing that a superintelligent species lived on Earth millions of years before humans. That could shake people's understanding of history, challenge national pride, and even disturb religious teachings. So, scientists must present their discoveries in ways that encourage thoughtful discussion instead of media frenzy. It's important that people learn from these discoveries, not fear them. It's also important for scientists to work closely with historians, archaeologists, and cultural leaders when interpreting findings. When new evidence hints at civilizations older than anything we know, the question becomes, who gets to tell that story? Care must be taken to avoid language that could create conflict between nations or groups, especially when dealing with sacred sites or indigenous lands. When scientists finally decide to share these big discoveries with the world, their goal should not be to shock or scare people, but to educate, inspire curiosity, and open minds. They need to use clear, thoughtful language that invites everyone to explore these mysteries together, while also respecting the cultures and beliefs that shape our world. As we dig deeper into the ancient past of our planet, scientists must act not only as explorers but also as guardians of truth, showing care, wisdom, and respect at every step. Finally, the discovery of civilizations that may have existed before humans raises a huge question. Who protects that legacy? If ruins or objects are found on land controlled by a country or tied to a specific group's history, disagreements may follow. Throughout history, control over archaeological discoveries has often led to battles over ownership, national pride, and cultural identity. Now imagine the discovery of something even older, evidence of a civilization that lived perhaps 10 million or even hundreds of millions of years ago. Such a finding could reopen old debates or spark new ones. Some people might use it to claim they come from a superior line of civilization. Others might feel their culture or religion is being threatened. When we talk about the Silurian hypothesis, we're diving into the fascinating idea that there might have once been an advanced civilization on Earth long before humans appeared, possibly millions of years ago, buried deep in the layers of rock and soil. If such ancient evidence exists, it wouldn't be sitting in plain sight like the ruins of Egypt or Greece. Instead, it could be locked away deep underground, hidden in stone that's been undisturbed for tens or even hundreds of millions of years. This raises the stakes in a big way. If scientists ever uncover strange artifacts, structures, or patterns that don't fit with our known history, things that might point to intelligent life long before us, people won't all agree on what it means. Some countries or cultural groups might say, "That's part of our heritage, it belongs to us." Others might say, "No, this is a discovery for all of humanity. Scientists everywhere should be allowed to study it." And if the discovery happens to be in a region that different countries are already arguing over, the situation could quickly get worse. Even worse, if these finds are seen as somehow threatening national pride or challenging a group's sense of cultural identity, emotions could flare up fast. On top of that, there's another layer of complexity: money. If these ancient sites lie in areas rich in natural resources, like oil, rare minerals, or even fossil fuels, companies might want to dig them up for profit. Others might see them as potential tourist attractions and try to turn them into businesses. This creates a conflict. Should we protect these sites for their scientific and cultural value? Or should they be used to make money? Without clear global rules, this tug-of-war between conservation and profit could end up damaging priceless pieces of our past. To prevent fights and protect the value of these discoveries, we need a clear and fair set of rules that everyone agrees to follow. These rules should promote respect, teamwork, and openness. There are already examples of this, like the UNESCO World Heritage Agreements, which encourage countries to share responsibility for protecting important cultural and historical sites. We should build on these ideas. Involving local communities, scientists from all over the world, and even governments can help create trust. That way, no one feels left out, and the search for knowledge doesn't come at the cost of someone's culture or land. Imagine discovering real proof that intelligent civilizations existed on Earth before humans ever walked the planet. Such a discovery wouldn't just make headlines, it would completely change how we understand where we came from, what it means to be human, and where we might be going. For a long time, scientists have believed that the story of life on Earth is mostly a straight line, from simple creatures in the oceans to apes, and finally to Homo sapiens, modern humans. We've built this story on things like fossils, ancient tools, DNA, and the ruins of long-lost cities. It tells a neat, tidy tale of humans slowly becoming more advanced over millions of years. But what if that story isn't the whole truth? If we were to find signs of an ancient civilization that existed millions, or even hundreds of millions of years ago, long before humans appeared, everything would change. It would mean that humans might not be the first intelligent beings to build cities, create tools, or form complex societies. That possibility would shake our understanding of history to its very core. Such a discovery would force us to ask difficult and exciting questions. Are we truly unique, or just the latest in a long line of intelligent species? Have other civilizations risen to great heights, only to fall and vanish without a trace? If so, why did they disappear? Did they destroy themselves? Were they wiped out by natural disasters? Or did they just fade away, their knowledge lost under layers of rock and time? This would challenge one of humanity's most cherished beliefs, that we are the peak of evolution and progress. It would push us to think about intelligence, not as something only we possess, but as something that might have emerged many times before. Perhaps there were others who understood the world in ways we can't even imagine. Were they more advanced than us? Did they have technologies we've never dreamed of? Or did they live in harmony with the Earth in ways that made them wise but left behind little evidence? If we are not the first intelligent species on Earth, then perhaps our journey isn't as special or as secure as we thought. It would show that even highly intelligent life is fragile. Civilizations can rise, build wonders, and then fall, becoming buried under millions of years of history. This idea would give us a new perspective on our own future. If it happened before, could it happen again? Could we be forgotten, just like they were? It might also make us more humble. Instead of seeing ourselves as the only intelligent life to ever exist, we might start seeing ourselves as part of a much bigger story. A story that stretches across countless ages and includes many forms of life and consciousness. The effects wouldn't just stay in the world of science. They would ripple out into our cultures, religions and philosophies. Many religions and belief systems teach that humans are special, even chosen. But what happens to those ideas if we're not the first? Would people lose faith? Would stories need to be rewritten? Or would we find new meaning in being part of a greater, more mysterious universe? Some ancient myths already speak of the lost civilizations, Atlantis, Lemuria, and others. These stories might take on new weight. What if they weren't just legends, but distant memories of something real? This shift in thinking might also bring people closer together. Instead of dividing ourselves by race, nation, or culture, we might begin to see all humans as one family, one chapter in a much longer tale of intelligence on Earth. We might even start to feel a connection to those ancient beings, whether they were like us or something completely different. If ancient civilizations rose and fell before us, they might have left behind not only clues but warnings. Maybe they struggled with the same things we do: climate change, war, resource depletion, or uncontrolled technology. Their fate could help us understand the risks we face today. Could it be that every intelligent species faces a moment where it must choose between destruction and survival? If so, learning from the past might be the key to building a better future. This discovery might also lead us to think differently about what true progress looks like. Is it just about more technology, more power, and faster growth? Or is it about balance, wisdom, and long-term survival? Looking for evidence of ancient pre-human civilizations isn't just a fascinating idea, it's also full of ethical challenges. Digging deep into Earth's rocks and fossils could damage delicate environments or destroy the very clues we're trying to find. Scientists would need to be extremely careful. Every layer of rock, every fossil is like a page in Earth's diary. If we tear out those pages too quickly, we might lose the story forever. And if we do find something incredible, how should we share it with the world? Should we release everything right away, or take time to check, double-check, and think through the consequences? The discovery could shock people, challenge their beliefs, or even cause fear. That's why communication would need to be responsible, honest, and respectful of different cultures and worldviews. The idea that humans are not alone in Earth's long history isn't just a mystery. It's a doorway to amazing possibilities. It could inspire new ways of thinking, new kinds of science, and a deeper sense of wonder about life, time, and the universe. One of the most complex and fascinating parts of exploring the possibility of ancient civilizations, especially ones that may have existed long before humans, is how such discoveries could affect global politics. If we ever uncover strong evidence that an advanced civilization once thrived on Earth, tens or even hundreds of millions of years ago, it could shake the beliefs and national stories that many countries hold dear. Some nations might feel their cultural history is being challenged or even rewritten. Others might try to claim ownership of these discoveries to boost their political image or support certain ideologies. This is why it becomes incredibly important to make sure that the research is done fairly, transparently, and with the cooperation of scientists and governments from all over the world. The evidence must go through peer review, meaning other experts check the results carefully. International guidelines should be created to protect archaeological sites, and the rights of countries over their own land must be respected. Only through global teamwork can we avoid disputes and ensure that such groundbreaking discoveries are handled with care and honesty. But there's more than just politics at stake. If we really do find signs of ancient civilizations, especially ones that existed long before humans, we also need to think deeply about what this means for the future. How do we choose what parts of these discoveries to preserve? How should we interpret evidence that might not be very clear? Should all findings be made public, or are some things too sensitive to share right away? These are moral questions, and they don't have easy answers. Scientists will need to walk a fine line, searching for the truth while also being careful about how their findings affect the world. They must think about the environment, society, and the legacy they're leaving for the generations to come. As technology becomes more advanced, these ethical challenges will become even more important. The future of this kind of research depends not just on better tools but also on wiser decisions. Looking ahead, future scientific breakthroughs could completely transform our ability to detect and understand evidence from Earth's incredibly distant past. New tools are being developed that can look deeper into the ground and detect even the smallest signs that something unusual happened long ago. For example, scientists are now improving high-resolution isotope analysis, a technique that looks at chemical fingerprints in rocks and soil. This might one day reveal strange patterns that suggest industrial activity or technology, even if it happened millions of years ago and has since been buried or erased by nature. Other exciting developments include better microscopes and powerful methods like synchrotron radiation imaging. These tools might allow researchers to find tiny bits of material, such as special ceramics, rare metals or artificial composites, that could not have formed naturally. If discovered, they could be the silent witnesses of a long-lost civilization. New scientific fields such as astrochronology and advanced geophysical imaging are also beginning to play an important role. These approaches help scientists better understand the timeline of Earth's geological history. Enhanced seismic imaging paired with artificial intelligence could uncover hidden underground structures or objects that don't fit with what we currently believe about how Earth developed. In places that were once considered too harsh or too empty to support life, we might find proof that something intelligent was once there. Even more, as computers become faster and smarter, scientists can analyze enormous amounts of data more effectively. This will make it easier to spot patterns that were invisible before, like unusual spreads of certain elements across the planet that might point to old industrial processes. When we combine this information with climate models and data from ancient environments, we get a more complete picture of how early civilizations might have lived, thrived, and interacted with their surroundings. All these new tools won't just help us find more things, they'll help us better understand what we find. Being able to precisely date objects or match them to specific events in Earth's past will make it easier to tell the difference between what is natural and what might be artificial. Slowly, what once sounded like science fiction could become accepted science. Instead of guessing, we may finally build real stories, based on hard evidence, about the Earth's mysterious and ancient past. To make real progress in this search, we can't rely on just one branch of science. We need an interdisciplinary approach, where experts from many different fields work together. This is especially true for bold ideas like the Silurian hypothesis, which suggests that intelligent civilizations might have existed on Earth millions of years before humans and left only subtle clues behind. Geologists and paleontologists bring crucial knowledge. They study ancient layers of rock, chemical traces, and fossils that may hold evidence of past technological disruptions or sudden environmental changes. Archaeologists use advanced tools like ground-penetrating radar or satellite imaging to search for unusual objects or patterns buried deep in the ground. Climatologists help us understand how ancient climate changes could have affected early civilizations, while astrophysicists explore the impact of cosmic events, like asteroid strikes or solar storms, that could have left signs in Earth's crust. Even geneticists play a role by analyzing ancient DNA to track biological changes that might be linked to intelligent societies, like the selective breeding of plants or animals. Working together, scientists from different backgrounds can develop better tools and sharper theories. By combining methods, like chemical testing with climate models, they can more easily tell the difference between nature's work and something created by intelligent hands. These collaborations open up new ways of thinking and help challenge old assumptions. With so many perspectives coming together, the risk of missing something important is greatly reduced. In short, interdisciplinary research is like assembling a giant puzzle. Each scientist adds a different piece, helping us slowly see the full picture of Earth's mysterious past. It also makes the final result stronger and harder to dispute. If we truly hope to uncover evidence of ancient civilizations, teamwork across many fields is not just helpful, it is essential. If it is ever confirmed that Earth hosted advanced civilizations long ago, It would dramatically change the way we care for and protect our planet. It would show us that complex life and intelligent societies are not new, and that our Earth may be much more dynamic and fragile than we ever imagined. Instead of focusing only on saving the forests and oceans we see today, we would also need to protect the deep layers of the Earth that hold precious records of our ancient past. One of the first changes would be an urgent effort to preserve geological records, layers of rock, fossils and sediments that might still contain traces of these ancient civilizations. These records are like nature's library, and once destroyed, their knowledge is gone forever. New technologies would be created to monitor these sites carefully and to protect them from pollution, mining or construction. Knowing that past civilizations may have altered the Earth's environment in big ways could also change how we view climate and nature. It might show us that Earth can bounce back from huge disruptions, or it might show us just how easily it can be damaged forever. Either way, the lesson would be clear. We must treat our planet with care, and we should learn from the mistakes or successes of those who came before us. This new knowledge could also inspire countries to come together and agree on rules to protect Earth's history, much like how nations today have treaties about exploring space. These shared efforts would help prevent reckless behaviour that could destroy important archaeological or geological sites. More funding would likely go into research that connects geology, climate science, and archaeology, so that we can better understand how past civilizations lived and what we can learn from them. However, confirming the existence of such civilizations would deepen our sense of duty toward the planet. Looking for signs of ancient civilizations that might have existed long before humans is a very difficult task. It brings huge scientific and technological challenges. Unlike human history, where we can often dig up buildings, tools, or bones that are only a few thousand years old, the clues to pre-human civilizations, especially ones that might have existed hundreds of millions of years ago, are likely to be buried deep underground, broken apart, or completely erased by natural forces. One of the biggest problems is the way Earth works. The surface of our planet is always changing because of things like earthquakes, volcanic eruptions, erosion from wind and water, and the slow but constant movement of tectonic plates. These processes can destroy or hide any evidence that once existed. Old rocks are melted down and formed into new ones. Mountains rise and fall. Oceans shift. If any advanced civilization ever lived long ago, their cities or tools could have been swallowed by the earth or ground into dust. Even the clues we can look for, like strange chemical fingerprints, unusual ratios of isotopes or rare materials, are often very hard to spot. For example, if an ancient civilization used metals or made synthetic materials, those traces might now look almost exactly like something formed naturally. That makes it hard for scientists to tell whether something was made by intelligent beings or just by nature. To even try finding such faint clues, we need advanced tools. Scientists use methods like high-resolution spectroscopy, deep earth drilling, and isotope analysis. But these tools have limits. Drilling into deep layers of the Earth is very expensive, and we can only search small areas. Earth's surface is enormous, and most of it remains unexplored at these depths. Another problem is time. Earth is about 4,500 million years old. That's such a long stretch of time that entire continents have disappeared and reformed. Any evidence from civilizations that lived hundreds of millions of years ago would have been through intense pressure, heat, and chemical changes. Over time, even strong materials like metal break down, and many signs would simply be erased or altered beyond recognition. The deeper we dig into Earth's past, the blurrier the picture becomes. Rocks from billions of years ago are rare, and the records they hold are often incomplete. Layers of sediment can be eroded or destroyed. Some may have been pushed deep into the planet by tectonic forces, while others might be missing completely. This makes it extremely difficult to put together a clear timeline or understand what might have happened. Even if ancient civilizations left behind machines, buildings, or other artifacts, chances are high that these objects would be broken into tiny pieces, buried, or chemically changed until they're almost impossible to recognize. For example, if a machine was made from a metal that reacts with water or air, it might have rusted away completely. Its remains could now be nothing more than a few specks of mineral dust. Chemical processes also play a role in wiping out clues. Water that moves through underground rocks can carry away or dissolve important chemical signs. Over time, materials left behind by a civilization might blend into their surroundings so well that they're indistinguishable from natural rocks. Even biological activity like plants growing or animals burrowing through the ground can disturb and destroy evidence. Microorganisms can eat away organic materials like wood or fabric. Unless something is buried quickly in the right conditions, like in a place with no oxygen, it probably won't survive millions of years. The Earth's sedimentary record, the layers of rock and soil that build up over time, is like a book that's missing most of its pages. What remains is scattered and uneven. That means if a civilization once existed in a place that hasn't been preserved well geologically, all evidence of them may be lost forever. Another issue is that we humans tend to view ourselves as the only, or the most important intelligent beings to ever exist. This kind of thinking, called anthropocentrism, can blind scientists to the possibility that a non-human civilization may have once existed. If we only look for signs that match what we expect to find, like steel tools or familiar types of buildings, we might miss entirely different forms of technology. Some scientists also assume that intelligent life is very rare. Because of this, they might not take the idea of ancient civilization seriously, or might avoid funding research into it. Others may unconsciously ignore strange findings that don't fit into accepted scientific ideas, a tendency known as confirmation bias. Even our scientific methods have limits. We rely on techniques like uranium lead or potassium-argon dating to measure the age of rocks. These methods are great for dating ancient minerals, but not always useful when looking for signs of technology. And even methods like thermoluminescence, which tell us when minerals were last heated, can be reset by natural events, making the results unreliable. Some of our best tools, like microscopes, spectrometers, and isotope scanners, can only do so much. They might miss tiny or deeply buried clues. They can also be affected by contamination or confusion between natural and artificial materials. All these challenges mean that even if we do find something unusual in ancient rocks, like a strange chemical or metal, it might be impossible to prove whether it came from a civilization or from a natural event. This is why scientists believe that working together across different fields is crucial. Geologists, chemists, archaeologists, paleontologists, and even astrophysicists must join forces. By combining their knowledge, they can better detect, interpret, and verify potential evidence. For example, a geologist might find an unusual layer in ancient rocks. A chemist could analyze its composition. An archaeologist could offer insights into how it might relate to structures or artifacts. An astrophysicist could consider whether a cosmic event, like a meteor strike, played a role in what's found. New technologies help too. Satellite imaging, for instance, lets us look for strange patterns in the ground from space. Machine learning tools can scan massive datasets to find hidden clues. And advanced scanning methods like synchrotron radiation or deep core drilling help us peek deeper into the Earth than ever before. These innovations have already helped refine our picture of Earth's history, and may one day reveal unexpected evidence of past intelligent activity. Scientists now look for strange isotopes, synthetic elements, or unusual structures that could hint at industrial processes. Some even search for signs of nanoscale technology or radiation damage that could point to ancient energy use. Even if we never find proof of ancient civilizations, the very act of searching pushes the boundaries of our knowledge and helps us understand more about our planet, ourselves, and our place in the universe.